Hello, fellow kids. Welcome to the second Feature Store Summit 2022. My name is Jim Dowling. I'm going to be the host for today. I'm the CEO and co-founder of Hopsworks. Hopsworks, in case you don't know, are the makers of the first open source feature store and also the first enterprise feature store, and recently also the first serverless feature store. So we have a great agenda lined up for you today. We have many of the leading companies who build feature stores, who sell feature stores, who use feature stores. We're going to kick off with Uber, who made the original feature store, Michelangelo Palette. But let's start today by just talking about what is a feature store. Maybe you're new to the space, you don't know what a feature store is, you're here to learn about feature stores. So I'm going to give a little bit of background now on my particular view on feature stores, and then we'll get into the agenda and what we're going to get up to today. So I'll start out by saying, well, what is a feature store and why do we need one? Well, if you're a data scientist and you're working at an enterprise and you don't have a feature store, often what will happen is when you need to train a model, you might get a dump of data from your neighbors, the data engineers, who manage all of the enterprise data. And you get a dump of data, you train a model, you hand that model over the wall to somebody in operations, like an ML engineer, whose job it is to put it in production. And that ML engineer who's going to put the model in production may need to go back and get operational data to make sure the model works. But this isn't really sustainable. And I think at this stage, many people know that the feature store is considered the data platform for AI, which helps solve many of these problems. It brings together our different personas, the data scientists, the data engineers, the ML engineers. And we have this nice little happy family where we can be more productive, putting models in production faster, make sure that the data can be connected to the models, and that the data scientists know which data sources, which features can be used in which models. Now, everybody knows, I think, that this is kind of a very idealistic view of enterprise data. So let's dive a little bit deeper into the details. And here we can see a little bit more detailed diagram of what enterprise data sort of looks like, right? You have applications on the far left and services that are going to generate data. And that data typically will be stored in operational databases. So you might have a key value store or MySQL or Postgres server, a database server. You might also have event-based data stored in Kafka or Kinesis. And this data you'd like to use to analyze your business. You like to see what's happening in the business with all these services and apps. So the data is often fed into a data warehouse. And there's a little bit of glue between there. You have to do ETL or ELT, so extract, transform, and load your data, or extract, load, and transform your data into the data warehouse. And the data warehouse might also be a data lake or a lake house. It's going to be some large place where you have a lot of your data available for analysis. So to understand your business, to understand what's happening in your business, so you can better optimize your business. Now, the data scientist is still in this walled garden, we can see here, getting dumps of data from the data engineer and handing the model over the wall to the ML engineer. So this is kind of not the scenario we want to get into. And we can see that the ML engineer maybe has two different types of operational systems, ML systems to work with. You might have an operational machine learning system, so you have a service or an application that you want to make intelligent, and you're going to add AI capabilities to it. Or maybe you need to have dashboards to build predictive models. So you're going to predict something about the business, or you're going to have what if scenarios of what would happen if we do this. Will this help our sales or help customer retention? And those are analytical machine learning systems. So the world is a little bit more complex than the first slide indicated. And we have another problem here, which is that the current data analytics stack, what we call the modern data stack, the data warehouse, it's very SQL-centric. And data science, as we know, has been very Python-centric. So most of the great libraries and frameworks that we have for machine learning are available in Python. So everything from TensorFlow, scikit-learn, PyTorch, these are all, and Pandas, of course, these are all Python frameworks. And data scientists like working in Python. So to get them to rewrite all of their, feature engineering, model training, and inference pipelines in SQL is maybe not necessarily as very attractive prospect for them. So there is this gap between these two worlds, the SQL world, the data science world, and how do we bridge them together? So the feature store has a role in bridging these two worlds together, because the feature store is a platform where the data analytics people, the data engineers, can feed data or make data available to data scientists, who can then take the data, use that data to create features, to train models with, and then to pass those models on to ML engineers who put those models in production. And those ML engineers who put the models in production need to obviously go back and use the data that's made available from the company via the feature store to the models in production, so that the data can flow to the models. And we can get this nice flow of data from our operational systems all the way over to the operational ML systems and analytical ML systems. Now, there's one other little piece of detail, which is a small but important piece of detail, is that real-time data, if you're going to build real-time machine learning systems, will need access to real-time data. So the data that flows from your operational layers, the event-based data, will have to go directly to a feature store. It won't be able to go via the data warehouse at Data Lake, because it'll just slow it down too much. It won't be real-time anymore. It'll be less than real-time. And the feature store, it may be a platform where we're going to store data or features for machine learning. It may be just a platform that you use to access them, and the feature store then offloads the data storage to other databases. And we'll see today there's going to be different views on this. We're going to have panels to discuss issues such as this one. Should the feature store manage the data? Should it provide virtual access to data? And how should it interact with the operational and analytical machine learning systems? And what kind of APIs should be used to access the feature store, to write data to the feature store or to read data from the feature store? And then how do we do real-time machine learning with the feature store? And then finally, the feature store is also considered like a data warehouse for machine learning. It's where your data is available for machine learning. So the features that you might want to use to train a model with, you should be able to go in there and browse them, find the ones that are good, and use them in your training and inference pipelines. So the feature store enables these features to be reused across many different models, which saves you writing new pipelines for every single model you're going to put in production. So it does help bridge this gap between data science and the modern data stack. But what it also does is it enables you to rethink how you build machine learning pipelines. So if you've taken a course in machine learning, and many of you have, I'm sure, you'll have probably been given some sort of static data set, and that static data set is a well-known data set like MNIST for deep learning, or maybe it's the Arize data set or the Titanic data set for tabular data. And then you create some features from the data set, you train a model, and you evaluate the model, and you're done. Okay, and this is, many of us will know that this is not how it is in the real world. So in the real world, new data always arrives. There's always going to be new data. If there is no new data, why do we have a model? We need new data to give the model a purpose and enable it to create value. And with the new data coming in, we always have to create features, make sure the data quality is good enough. We're not going to be given a pristine data set that we get in our courses. And then when we train models and evaluate them, we also need to have an inference pipeline. So whether it's an analytical machine learning system with a batch inference pipeline or an online machine learning system with an online inference pipeline, you still have to have that as a program that takes the new data coming in, computes the features, uses the model to make predictions, and produces output. And in the classical case, you don't do that. So what the feature store does is it's a new platform, a new capability that's introduced into your AI stack that enables you to restructure or refactor your machine learning pipeline. So no longer need to have this single monolithic pipeline, which goes from raw data to some predictions or some evaluation of your model. You can now have 3 different pipelines, which is great. We break it up into 3. We can have a separate feature pipeline, which runs at the same cadence as your new data arrives. So if the new data arrives every hour, we can run the feature pipeline every hour, create new features, and make them available in the feature store. If we have historical data, we can use this feature pipeline to backfill, to take that historical data and backfill it into the feature store so that we have features available for data scientists to run training pipelines. And training pipelines often run on demand. They're not necessarily on a schedule. If you've got a production system, new data will arrive at a certain cadence, and your feature pipeline should match that cadence. If it's real time, it's going to run 24/7. But if it's a batch system with new data arriving every day or every hour, then your feature pipeline should run every day or every hour to make sure that the features are fresh and kept available for predictions. So the training pipeline often doesn't have to run on a schedule. It can run when your model degrades, maybe when you need to rerun it because new data has arrived, or there's many different reasons why you might rerun your training pipeline to create a new model to improve the accuracy because you have new features that you want to include in your model. But typically, we don't see it as an operational system in the same way as the feature pipeline is part of an operational machine learning system. And the other operational part of the machine learning system is the inference pipeline. So whether it's a batch or an online inference pipeline, it doesn't really matter. You're still going to have this as a system, which is going to have to generate predictions that will be consumed by some downstream service or dashboard. And those predictions will need to be there, right? So if you're building your business around this capability, so if you're adding intelligence to existing systems, so operational systems, or if you're empowering your business leaders with dashboards to help them inform their decisions, if that data isn't there, that might be a cost to your business. So inference pipelines are production level. They can run on a schedule, can run 24/7. But the fact that we've now separated out our monolithic pipeline into 3 different parts, I mean, we can run them all at the cadence they need to run at. The operational parts can be made operational, and the parts that aren't operational, such as training pipelines, can be run as needed. Now, the other area that's grown quite a lot, I think, in the last year that's relevant for feature stores is what we call data-centric AI. So again, if you've taken a course in machine learning, you'll probably have done some work on things like optimizing hyperparameters, maybe changing the learning rate or the model architecture to improve the performance of your model. And these are typically the steps you would take. Add regularization to your model. Look, the accuracy improves. Great. Excuse me. Data-centric AI takes a different approach. The basic idea is, well, can we improve the performance of a model by improving the data we use to train the model and the data we use for inference? So we're optimizing our features now rather than necessarily optimizing the model itself. So we can do things like improve the feature data quality, make sure that we don't get any garbage in, because garbage in means garbage out. And if we can improve the data over time, if we can have a system that can collect data, so if we have a feature store that's providing features to our inference pipeline, and we can take those predictions, so the predictions plus the features, and feed them back into the platform, we collect more data over time, which can enable us to have more data to train models with. And we know that machine learning models perform better when they have more higher quality data. Now, last year when I introduced I gave this kickoff for the first Feature Store Summit, one of the things that I introduced was this notion of history and context for models. So when you're building online applications in particular, we often tend to build stateless applications. They're easier to manage, easier to scale up and scale down, and they are connected to some database at the back end. But if we want to make an online application intelligent to help it make intelligent decisions, we need to give it not just the information it has available in the requests that come in, but it may need to know history and context. So if you're an online retail application, a user can click in and maybe browse to a few different pages, search for something, add something to a cart. We have some information for that session, and that information we can use to make predictions. But a machine learning system is so much more powerful if we also give it history. So has this user visited us before? If they have they bought stuff? Have they bought this product or anything similar? And also context. So, what's trending right now in the store? What are other users looking at? Is there any rush to buy certain products? So history and context are very important, powerful concepts for machine learning models because they enable you to make richer decisions with more data. Now, if you're familiar with Yann LeCun, he won the equivalent of the Nobel Prize, the Dijkstra Award for computing, for his work on deep learning. He's very well known. He invented many powerful concepts in machine learning, such as CNNs. Now, Yann LeCun this year came out with something quite controversial and said, here's a model for building what he calls autonomous machine intelligence. You can think of it as being, an intelligent system. And he identified some core components of that system. So he said, you'll need a world model that you build up over time. You need to have some form of intrinsic reward model as well. And then there are other parts, but one of the key points that struck out to me was what he called short-term memory. And he called it key value associative memory. But I really call it the feature store. So, the feature stores come a bit, and I think if we're part of Yann LeCun's model for future autonomous machine intelligence, then we have a very important role in the AI space to come. So I'm going to talk a bit now about what we're going to talk about during the conference. So we have a bunch of talks today. I mentioned the Uber are going to be our keynote to kick off. And then we have some other talks from Hopsworks, from Doordash and LinkedIn. We're going to have panels. So the first panel will be moderated by yours truly, and we're going to talk about APIs for Feature Store. I'm really excited about the panels. They're going to be free form. If you want to ask questions, you can ask questions in Zoom as we proceed. You can ask questions. There's a Q&A button at the bottom. And we'll try and take those at the end of the talk. There's also a Slack, we'll get to that later, where you can ask questions that speakers will answer. But the structure of today is that we have a number of longer talks. So again, in the second, after the first panel, we're going to have then Disney, Airbnb, Sinan, who's an author of a Manning book on feature engineering, and then a man from Arize. They're going to talk about their different experiences with feature stores. And we're going to have another panel then, and it's going to be Patrick from Validio who's moderating about data quality in feature stores. And then after that, we'll have Stefan, who'll talk about Hamilton that was developed at Stitch Fix, Richard from American First Credit Union, Achint, who's going to talk about their feature store at Scribble Data, and Simba Kadar, who's going to talk about their feature store, Featureform. And we'll finish with that session with a panel moderated by Sarah Catanzaro, who's well-known in the data Twitter sphere. And she's going to talk about primarily how do we make feature stores become part of the productionalization of machine learning models. So feature stores, I think, have matured quite a bit since that original Uber publication on feature stores. And I think there's an acceptance that it's now a key part of any production AI stack. And then how do we make it, if it becomes really part of that, how do we make it sink in and become invisible? So we also have then a number of lightning talks, and we have a couple of longer ones. So Gaurav from AtScale, who are one of the gold sponsors here, and Lulu from dotData, also gold sponsor of the conference, are going to talk. And then we have some talks from Ravi at Open DataOps Foundation, Greg from Sumatra, Sarah from Berkeley University, Lou from 4Paradigm, and then I'll finish off at the end, and I promise I won't hold that too long. So a little bit about the conference. It's organized by Hopsworks. I mentioned I'm CEO and co-founder of Hopsworks, and we make a feature store, the first open source feature store for machine learning. Now also the first serverless feature store for machine learning, the only one currently. And we also have a lot of sponsors and partners. So AtScale and dotData are gold sponsors of the conference. Thank you to them. And we have then sponsors such as, or partners such as Infuse, ODSC, NumFocus, Data Clubs, Data Talk Clubs, AI Sweden, The Sequence, Big Data Community, and Celtic Next. So we have a Slack. If you haven't joined it, please join the Slack. It's called featurestore.org.slack.com. You'll get a chance to ask direct questions to the speakers at the end of each session. So there's a bunch of different channels in there. I think you can probably use the general channel to ask questions. But it's an active Slack. There's quite a lot of users on it. So please join it. And it's a really great way to interact with the community, the people who are working with feature stores, where you can ask questions about feature stores in general. So with that, I'm going to kick off by introducing our first keynote. And the first keynote, I'm really delighted that we have Amit Nene from Uber to kick off the second Feature Store Summit. You know, if you know the history of Uber and the history of feature stores, you'll know that, for example, the first feature store blog post or first time someone used the term feature store was when Uber in 2017 released a blog post about their platform called Michelangelo. And the palette is the name of the feature store in the Michelangelo platform. And that led to, I guess, just general interest. It piqued my interest. You know, we started work on it almost immediately after reading that. But it's taken a while, I think, for the feature store as a concept and now as a platform to really, you know, make strides in the machine learning space. But a little bit about Amit. He talked last year at the conference, but I think he had a scheduling mix, so we would have kicked off last year. But because of the scheduling mix, he had to talk later on it. This year, we're delighted to have him kicking off the whole event. He's going to talk about how they use Palette, their feature store at Uber, accelerating ML. And Amit himself he's both the architect of this Palette feature store, and he's also the manager of the feature and embeddings infrastructure team within Michelangelo and the ML platform Michelangelo at Uber. So hopefully, you know, they've been ahead of the game on many of the innovations in this space. So maybe we'll get a little insight into what they're thinking about. Amit has also led teams in the areas of real-time decision-making for fraud. So he has experience also at application for feature stores. So with that, I think I'm going to hand over to Amit. Are we there, Amit? I think my sound is slightly off here. I'm going to stop sharing my screen. So Amit, if you're there, you can take over sharing of your screen. 1 second. Okay, I can't hear anything, sorry. Sorry, okay. So just a couple of reminders. You can ask questions in the Q&A button at the bottom. And you can see there's two different buttons. There's a chat button and a Q&A button. I would encourage you all to use the chat button, the Q&A button, not the chat button, because then we can collect all of the questions and answer, deal with them in a structured manner. I have an issue with my sound here. Oh, no. Is he here? Okay, so while we're waiting to get Amit to connect, okay, so Amit, we can't hear you currently. I think he's online. We've heard he's online. What I'll do is I'll just briefly
Can you hear me now? Can you hear me now?
Yes, we hear you.
Yeah, yeah. So I've been struggling to get the video on. I think it keeps saying that the host, you cannot start your video because the host has stopped it. So maybe there's some setting on your side.
I think video is a Zoom. So we're using Zoom here, by the way, for people on YouTube. I think if you can share your screen, that will probably be enough, Amit, for the moment.
Okay, got it. Let me do that. Yeah.
We got someone on the Q&A. Probably we can. Are we doing multiple? Okay. Great. So we're doing it live, by the way, folks. So this is all live. This is the beauty and joys of doing things live. So I'll call you out, Amit, if you get to time, just that you know. Great. Over to you, Amit, please.
All right. Hey, thank you, Jim. And thank you for the introduction. I think Jim already introduced myself. My name is Amit Nene, and I play like a dual role in Michelangelo platform team. I've been doubling as the architect of the Michelangelo feature store for the last few years, and also running the features and embeddings team within the platform. So today's talk is about the palette feature store and how it has been helping the entire ML lifecycle across various stages of the ML lifecycle at Uber. So to begin with, let's talk a little bit about the history of the feature store. We coined the feature store, as Jim mentioned, back in 2016, and that's when we actually started work on the feature store. We knew that building new features was one of the most time-consuming parts of the ML lifecycle. So we started with a vision of creating a crowdsourced as well as a curated repository of shared features. To a great extent, that continues to be our team's goal. Over time, the feature store took shape as a dual data store system that would manage features for training and serving for the user without having them build ad hoc data pipelines or worry about online-offline consistency. Then over time, we built convenience support in the feature store to author feature pipelines using the most common technologies available at Uber, and shared about our work in the well-known blog that Jim talked about back in 2017. We then started onboarding most of the mission-critical use cases at Uber and had to really focus our energy on scaling the real-time serving stack. Then, during the pandemic in 2020, a surprising thing happened. While most of our ride-sharing business was down, there was an explosive growth in our Eats business, Uber Eats business, requiring us to take the online serving stack to yet another level, to scale to serving millions of queries per second at very low latencies and with a very limited hardware budget. So that was a very challenging time. But having tamed the whole reliability and scalability problem over most of 2020 and 2021, it has allowed us to focus on many new initiatives, such as building an ecosystem around the feature store to support functionalities such as feature quality, automatic feature selection, feature monitoring that I'll be talking about shortly. More recently, we have been also building brand new feature store APIs and metadata to support end-to-end data lineage in the system and support better modularity and extensibility. We're also making embeddings the first-class citizens of not just the feature store, but also Michelangelo, which is currently work in progress. So with that, to really appreciate the role that the feature store plays in an end-to-end model development lifecycle, it'll be helpful to walk through a typical user journey. So oftentimes we can have a ML engineer or a data scientist who may want to create features such as number of trips taken over the last 10 days, number of orders from a particular restaurant, average rating of a user. The first thing that they want to do, they know that building features from scratch is one of the most time-consuming tasks. So often the starting point is looking for existing features. And that is what we call feature discovery, which is the first phase. And of course, you may not always find the features that you're looking for. And in many cases, you have to build new features or embeddings from scratch from the upstream data, which is what we call the feature extraction phase. And the feature store offers out-of-the-box support for that. Once the feature pipelines are built, it's time for model training. And what the feature store offers here is what we call as the feature preparation stage, which is essentially generating the training data from all the underlying labels and joining them against the feature tables. And the feature store supports this and at a very large scale. And once a model is trained, it is ready to be deployed in production. It's evaluated and then deployed in production, which in Uber is typically done in real-time environment. So the feature store plays a huge role here because it needs to support a very high throughput. Like I said earlier, millions of queries per second. And often because of the inferencing is used in real-time application, the latencies are often, the P99 latencies often are sub 100 milliseconds. And having deployed a model in production, we need to continually monitor the model. And monitoring a model is not just about monitoring the model score, but actively monitoring the feature and a drift in the feature distribution, for example, or a drift of the feature distribution relative to the offline training data. And finally, features over time always get revised. Features get shared across multiple models. Features are deprecated, and a feature store supports management of this life cycle. So let's go a little deeper into each of these phases to see the feature store in action. The easiest way to look for features in the Palette feature store is obviously to go through the Git repository of feature definitions. And it's organized into like 3 layers. The very first top layer is the entity layer, which is the primary entities associated with the features. These are things like ethers, drivers, trips, and so on and so forth. You may also have the next level, which is a feature group, which you can think of as the logical table of individual features. You go looking for the features that sound like you may be interested in. You deep dive one level, you go to the feature level, which is essentially a logical column within a feature group. There is also metadata associated with the feature that you may want to look at when you're choosing a feature, such as the keys associated for lookup, the feature extraction ETLs, the online dispersal information. Another common way to search for feature is to use a keyword-based search rather than going through the Git repository. In this particular screenshot, you can see ML features at the top here. I typed the keyword ether, and a 58 results, 58 features popped up here. So I can then go into the individual feature definitions and see if it is indeed the feature I'm looking for. Oftentimes, it's hard to tell whether a feature is indeed what you want by just looking at the feature definition. And you really want to understand what the upstream data pipelines are that are feeding data into it. To make it easier to browse through the lineage of pipelines, we've integrated with Uber's lineage system. In this screenshot, you see a typical flow of how a feature pipeline, how upstream data turns into a feature pipeline. On the left-hand side here, on the top, you have your typical sort of business tables or warehouse tables, your dim fact tables. In the middle layer, you have typically staging layers, which join the above data, the upstream data, or perform pre-materialized aggregations over various different intervals of time. And on the right-hand side, you have the feature store tables, which are not only extracting features, but generating point-in-time snapshots that will then be used later for training as well as dispersal to the online store. Now, the whole process of manual discovery may get tedious, and in some cases, it may not even be obvious if a feature is suitable to a model unless you throw all the features at the model and try to train it. To solve this problem, for our advanced users, what we have done is we have supported automated feature search through Michelangelo's AutoML tool. So the way this works is an ML user can bring an existing model, and the AutoML tool will inspect its labels, the features, its keys, and go looking for feature store features that are relevant to our target labels. What it ends up with is recommendations of new features that then the modeler can add to the existing model. So this very much reminds me of what Jim mentioned earlier about data-centric AI. So this is one technique where you can sort of, the AutoML tool goes looking for additional signals from the feature store to enhance the performance of your model. So on to feature extraction. So of course, like I said earlier, if you are unable to discover features, it's time to build new features. And batch computed features are one of the most common ways of building features at Uber. And specifically using batch and some sort of SQL, specifically either Spark SQL or HiveQuery at Uber. So the way the feature store simplifies this, the productionization of feature pipelines, is by allowing a self-service feature authoring interface. So a user comes and just enters all the definitions of the HQL file, the feature definitions and types, and the online configuration. Once the data is just checked in, the feature store will automatically generate all the pipelines. It will start generating the feature point-in-time feature snapshots, ingest it into the offline store. It will auto-generate the dispersal pipeline. It will continuously take new data as it comes and copy it to the online store. So the online store will always contain the latest snapshot of the features, whereas the offline store will contain historic data for the purpose of serving, for the purpose of training and offline evaluation. So one thing to note is that the automation here is one of the key accelerators of the model productionization process. In addition, the self-service interface greatly accelerates model development velocity. Because of this, given any week, we see dozens of commits from our users. Moving on to real-time features. A model may need real-time features often. These are features whose values need to be captured at a smaller grain of time, whereas batch features are computed daily. The grain of time here is often seconds or minutes. Now, building production pipelines for near real-time feature extraction is a slightly more complex process. Not only do you have to productionize the real-time pipeline to ingest data into the online store at the bottom here, but also generate a pipeline to log the data from real-time to the offline store, so you have enough data for training. And optionally, you need to build a third pipeline at the top here to bootstrap the computation. Essentially, this involves back computing the data against historical events to produce the features for the first time you're training your model. To make things worse, online and offline pipelines often use different compute technologies. So ensuring that the data is semantically consistent online and offline is a pretty challenging problem to solve. Second, you may not always be able to express the complex processing that you can more easily do with batch processing. So that is one sort of downside of using real-time features. Now, one thing to understand is the complexity of the real-time features ecosystem can make feature iteration an extremely cumbersome process. Each time you go through this process and you find that this is not a feature that you want to use, and you pick a new feature, you have to go through this process all over again. So there are two key things that have allowed us to cut down this complexity and dramatically reduce the model's time to launch. The first thing is automation. Automating these various pipelines, ensuring that the online and offline data is consistent. That is the first step. B, choosing the right infrastructure to ensure that there is online and offline consistency. In our case, we chose Athena X, which is the homegrown streaming SQL solution available at Uber. And we've worked with the data team to set up this bootstrap pipeline, which ensures online and offline consistency. Now, feature onboarding is the same as batch features. User goes and checks in their code here to the feature spec Git repository. Once the code is committed, the pipelines are kicked off, and the data starts ingesting into the offline and online stores. Moving on to model training, we have our production pipelines ready, and it's time to start training the model. The first thing we do before kicking off the model training is to make sure that the feature store data is clean and does not contain errors. The one detail I left out in my previous slide is that right after we onboard features, we kick off these data quality pipelines that then produce test results and record it in a data store for use later during training. We also automatically page the respective on-calls so that the data is repaired right away versus waiting to do so at training time. On the right-hand side of this picture, you can see the screenshot. This is a screenshot from our, at the time we kick off the training job. We kind of run 5 tests in this case, and you can see there are tests around duplicates, like there are features with duplicate keys, which is something we don't want. We have things like missing partitions, null features, and so on and so forth. So the key thing to the takeaway from here is that taking care of such low-hanging fruit can save ML developers hours or days of time otherwise spent debugging and resolving issues discovered during training failures. Having trained the model, it is having actually validated the data from the model, it's time to actually kick off the trainings. The feature store plays a big role in the first step of training, which is feature preparation. What this involves is joining all the training data containing the labels against the various feature tables that the model is using, and spanning several months of data using what is known as point-in-time joins. What that means is that the labels will be joined against the values of features observed exactly at the time of the label. Now, we've seen in some cases, the model, the feature join can involve joining like hundreds of terabytes of data, and this can make the process very inefficient. So it is critical to accelerate, to optimize the system to accelerate the velocity of model training. And in our experience, the key to cutting down this cost is to optimize the underlying shuffle operation, which is what Spark uses to implement joins. We've also introduced a special on-storage data layout called Delta Store to incrementally compute point-in-time snapshots to reduce the amount of data joined during feature preparation. In addition, Michelangelo provides a DSL for performing lightweight transformations or model-specific feature transformations. This provides the users the flexibility of quickly iterating over model features. Say you have a feature which is seconds, you want to turn it into milliseconds, you can do quick transformations using the DSL, and this avoids having to backfill months worth of data if you had done this at the ETL or the data layer before ingesting into the feature store. So again, this is one of those things that helps boost developer velocity. Moving on. Now, once the model is offline evaluated, I should have mentioned that the offline evaluation uses the same exact structure. We use the offline testing data or validation data, joins, offline joins, and evaluate the performance. And to see it's once it's like deemed optimal, it's time to actually deploy it in production. And production, in our case, majority of the times is a real-time system. You can see from this screenshot, the architecture is very semantically identical to the offline system. Instead of the offline store, you have the online store and a caching system. It's on Redis. Cassandra is used for online store. Instead of the labels, you have the context, that is the keys being passed from the upstream service. The feature assembly is not a full table join, but just a few rows of features joined together using the keys passed in. And then DSL is applied on those joined features. The DSL works in a way where the code is designed to execute symmetrically in online and offline environments. So the exact same transformations are performed even at inferencing time. And the final feature vector is passed on to the inferencing system. Now, one of the key things that at Uber, at least, we end up serving millions of queries per second from the feature store. So planning for capacity is a very crucial step in being able to launch the model in a timely fashion. So requesting the use of inordinate amount of hardware to support this throughput may end up delaying the launch because oftentimes the hardware is not available. So towards that end, we follow a process that takes the model's access patterns, features used, size of the feature tables, and apply various optimizations and plan for various feature optimizations to come up with the best estimate of Cassandra and Redis capacity for online serving. Now, our eventual goal is to fully automate the capacity estimation process and also automatically provision the underlying storage. One other thing I'll mention is that has helped us to accelerate the whole deployment process is the use of shadow testing environment. If you're able to clone a percentage of the production traffic and run it against the inference server and the feature store to test the system at a reasonably high scale without affecting or causing outages in the upstream business flows. Now, successful testing in a shadow environment provides us with the confidence of then graduating this model to the actual production environment. Now, let's say the model is now deployed in production. It's not done. We are not done yet because we need to continuously monitor the performance of the model and make sure that it is not drifting away. And one of the key things we need to monitor is not just the prediction score, but also the feature store features, and specifically whether the distribution of the features has drifted away from a baseline. And the baseline that we use is often constructed from a historical sort of inferencing data or a model training baseline. And we try to detect this drift between the online distribution and the baseline distribution in near real time. So within a few minutes, our system will tell you that your features are drifting away. So just as an example here, you can see for this particular feature, this is an actual screenshot from an actual production feature. You can see that the training baseline and the online baseline on the left, you can tell that the feature is way off the baseline. The palette feature store or two kind of directly implements its own monitoring, but it does so in an offline manner. It that monitoring is mainly done to sort of ensure that the data has a good distribution, predictable distribution at training time, but also before dispersing data to the offline store. So the takeaway here is that the two systems really complement each other, the real-time system and the offline system, in a way that to ensure that the feature outages are detected in a timely manner and potentially avoiding several days of outages. Finally, I'll talk a little bit about the evolution of features.
We'll have to kind of go through it a bit quick. We're kind of run out of time.
I'm wrapping up.
Right.
Yeah. So finally, we'll talk about a bit about the evolution of features. We observe that over time, features get organically adopted across multiple feature models and maybe revised to newer versions. So it is really important not just to maintain a lineage with the upstream data pipelines that you saw earlier, but also to the models using it. So that when a model is actually, when a feature is being removed, we go through this two-step process where we first deprecate, soft block the training, and then eventually when all the feature references to the models are removed, we can actually safely remove the feature. Really very quickly, just to sum up how the feature store plays a role in accelerating end-to-end ML, we saw how feature discovery support in the feature store can accelerate the search for features, and also specifically through automatic feature selection. We saw how automation plays a big role in speeding feature extraction. We saw how feature federation and scalability in joins is critical to speed up training. We saw how a good process for capacity planning can speed up model deployment and shadow testing. We saw how near real-time feature monitoring via the prediction logs and offline feature store monitoring work together to prevent potential outages. And finally, we saw how a feature store can help you manage the life cycle of features and evolving features better. So thank you. I think I'm at time, so most likely I'm going to take the question.
Yeah, thanks a million, Amit. That's been fantastic. There are a load of questions, but we've no time for questions, unfortunately, to answer live. So what we can do is you can jump over to the Slack. All the questions will be posted on the Slack, and you can answer them offline. And you're back in a little bit for the panel as well, which will be very interesting.
That's great. All right. I'll hop off to Slack now.
Great. Thanks a million. And please, everyone, just jump over to Slack and ask questions for Amit there. Okay, now we're going to jump on to the second talk. It's by colleagues of mine from Hopsworks, Fabio Busso, VP of Engineering, and Moritz Meister, who's the head of the feature store. And they're going to talk about experience building Hopsworks over the last 4 years. So it's been around nearly 4 years already, which kind of time goes fast. But over to you. I think Moritz is going to kick us off here.
Yeah, hey, thank you for the introduction, Jim. My name is Moritz. Next to me is Fabio, our VP of Engineering. And today we would like to share the learnings that we've had over the past 4 years building Hopsworks Feature Store, and also share a little bit what's next, what's after this. So let's take a step back and look at the problem that the Feature Store is trying to solve and recap a little bit before we dive in. Looking at how machine learning applications are deployed within enterprises, and also what kind of or how they generate value for the business. The first step is usually this kind of what we call laptop ML or artisanal ML, which means basically someone in the business is using a machine learning model to do, for example, a predictive forecast of sales or cluster the customer base in order to get a better understanding of the business. But the higher value business use cases are actually the ones where you have to take your machine learning model and operationalize it. That means either users are directly interacting with the machine learning model through your product, you so-called operational ML models where you do inference at real time, or more in a batch analytical fashion where you create batches or compute batches of scores every night or every week, and then use those in your product or in customer communication to improve the business. So what is actually the data problem, and where is the Feature Store trying to help? And that's actually jumping from that artisanal ML to the operational trajectory, right? And that's often called the data problem. Over the past 4 years, we actually saw, and when we talk to customers and other companies trying to build feature stores, that it actually splits up into 2 challenges. One is the data write challenge, or how we call it, and the other one is the data access challenge. With data write challenge, we mean writing the data into a centralized storage where it's available to those use cases, and oftentimes those use cases have different requirements than let's say a traditional data warehouse can give you. So for example, for operational ML, you want very low latency on feature vector lookups, which a normal data warehouse usually can't give you. And then the other challenge is actually that we discovered is the data access, which means once you have all the data in a centralized storage and you're able to reuse it, you also need to be able to make it available to especially data scientists in an easy way, so that they can train their models and develop those ML applications in the first place. So when starting to build the feature store, the first tool that comes to mind is Spark. And that's also how we started, because it's a multi-storage engine, it's scalable, so it has a lot of the properties that we're looking for in order to write data into the feature store. So when we started out with Hopsworks 4 years ago, we were mostly aiming to tackle the problems of the pain points of data engineers. So reading data from different storages, performing feature engineering in a scalable fashion, and writing the engineered features back into the feature store to make them later on available to data scientists. And then around that, we built a lot of functionality, such as orchestration or integrating with orchestration, Airflow, providing support for different languages, so Python, but also when you use Spark, you might want to use Java or Scala. Like I said, different storage connectors, adding statistics to make the data more descriptive for the data scientists later on, but also tracking lineage. And then later on, you also want to add online storage, which is the low latency storage that gives you access to the features for real-time serving. And with that, we also worked on a writing pipeline to the online feature store for streaming applications. And then throughout the last year, actually, when we got closer to the data scientists, we realized that data scientists still want to use Python, right? And Spark might be overkill, especially when you want functionalities like point-in-time joins. You might want to have the scalability of Spark, but you don't want to put the burden of writing complex SQL queries on the data scientists. So the challenge we faced in the last year, or the effort we made in the last year, was providing Pythonic or Python first APIs to this functionality with the scalability of Spark. And then with that, since we focused more on Python, we were also able to integrate tools like Great Expectations that come more from the Python world to provide, for example, data validation, but also adding pure Python transformation functions, which actually lead to reusability of features. And then if we look into the future, so now that we have the data challenge or the data problem under control, the next step will be actually writing prediction services and also closing the loop. So tunneling back predictions and feature values from the prediction service back into the feature store to allow analysis on that, or to further improve the models and provide this machine learning flywheel that we often hear. How does this look like in Hopsworks in terms of abstractions? So in the first effort, as I said, we wanted to make also feature engineering pipelines more accessible to the data scientists, because what we saw is that also data scientists want to go in and maybe make small variations of features and be quick in publishing those features to the feature store. And for that, we took our write API, which is essentially the concept of feature groups. So you write to feature groups, and we made that also a Pythonic experience so that data scientists can easily go in, modify features, but also interpret features better. And then the other side in the last year is the feature view that was added, and that is basically the API to consume features from the feature store in a completely Pythonic fashion. That includes transformation functions like normalizations and one-hot encodings, but also getting training data in certain file formats in case you want to use a different, in case you want to use a training framework that requires, for example, TF records or NumPy files. And then also point-in-time drawings, making those accessible through a Pythonic API. So yeah, and then to dive deeper into how this looks like in Hopsworks, Fabio will take over.
Okay, thanks, Moritz. So let's have a deeper look on how we actually solve the data write challenges and the data access challenge from a code perspective, right? So back at the beginning, we made a really strict decision of actually going for data frames API and not actually implementing a DSL. There were a set of reasons to why we choose that path. Essentially, the first one is flexibility. We wanted Hopsworks to be able to address a wider range of use cases, from NLP use cases to anomaly detection, forecasting, and so on and so forth. And that requires slightly variation of different data engineering practices and so on and so forth. And that's basically allowing us to have a better approach using data frame API and the wider range of libraries that are already out there. The second one is user experience. We didn't want to actually having users having to learn an additional DSL that is only applicable to Hopsworks. We wanted that to bring their own knowledge of how to work with Pandas data frame or Spark data frames and be able to actually apply it in Hopsworks directly without having to learn new tools and new frameworks and so on. And finally, it was a practical approach to basically say a lot of our customers and users already have existing pipelines. So we don't want them to, when they want to adopt Hopsworks, we don't want them to go and having to rewrite those pipelines. We want to be able to pick them up and just plug them into Hopsworks and off they go. There's another details, like practical details of why the Python as a first-class citizen Hopsworks 3.0 and why Spark is not suitable for data scientists. But we saw working all these years with data scientists that there are certain challenges when using Spark. One of which is actually resource estimation, and Spark has a lot of knobs to tune, and it's really easy for you to blow up your Spark application if you don't really know what you're doing, or if you're trying different things. The second one is debugging. Spark has a lazy execution model. You assemble a bunch of operations, and then Spark does a bunch of stuff, and you have don't have much visibility into the existing thing. Not as much as, for instance, Pandas, where you're basically doing interactive changes and so on. And then there's a practical things that the tools don't match essentially, right? So all the tool for training models, serving models, are all Python centric. You don't have a Spark context available, so it's really hard to work with this thing. So that's why we invested a lot of time and effort into the bringing a Python centric experience. How does it look like? If you see here, for instance, we have first set. We have a plain Pandas data frame manipulation. We're doing some Windows aggregation here. Whether this is a new code that you're writing or existing code that you already have, you just plug it in, call the get and create feature group. You attach a bunch of metadata, whether it's a name, description, version, primary keys, if you have event time, and so on and so forth. And then at the end, you basically say, I can write this thing to the feature store, and the feature store takes over and writes it to the online, offline feature store, depending on what you need and what's your use case. What as Moritz was mentioning earlier, right? When you adopt a Python-centric API, then you can easily integrate with the wider range of libraries that are already existing. One of which is Great Expectation, right? So we added support for Great Expectation, and we actually do it before we write, like the get expectation is necessarily executed before we actually write data to the feature store. What that actually enables that all the data that you are sure that all the data that lands in the feature store is actually clean and respects your validation, right? And like there is nothing. The way you use it essentially is in the pure get expectation slide. You define expectation suite, you attach that expectation suite to a feature group, and before every time you insert the data, the expectation is validated, and then Hopsworks does a bunch of like metadata management. For instance, there tracks which expectations we attach, when they've been run, whether or not they've been successful, and whether or not you have actually ingested data to the feature store. On the other side, so that was the data write problem. So how do we actually enable data scientists to actually use data and build prediction services and then deliver prediction services? So we introduced a new concept in Hopsworks 3.0, which is the feature views, right? So it's a Python-centric API to be able to access, and I'm going to show you in a second, access features, and I'm going to show you in a second how you can work with that. It's Python-centric. There are a bunch of different reasons for that. First of all, as Maurice was mentioned in the beginning, all the ecosystem from training model and serving model is all Python-based. So we need to have a way for data scientists to actually stay in Python and access all this feature data that is available in the feature store. The second aspect is that we want to make sure that we integrate with those, like the TensorFlow, PyTorch, and all the rest of the ecosystem by allowing you both to return, both to access the feature data as pandas, but also as files, and then also as files specifically in the file formats that are required. Whether it's specifically, like for instance, if you use TensorFlow, then you might want to access data in TF records. There are a bunch of other additional functionalities that we added. One is, as Maurice was mentioning earlier, point-in-time joins. So if you're using features from a bunch of different feature groups and you're using you're reusing those features, oftentimes those features are written with different resolution, which makes when you're joining them together, you have to make sure that you're joining them in such a way that you're not leaking data from the future, essentially. And that's a complex problem to tackle. That's a complex SQL query to write. So from Hopsworks perspective, we provide user like a pandas-like API to access those features. And I'll show you in a second the example and be able to actually retrieve that. And finally, one additional point is transformation functions. As Maurice was mentioning, transformation functions for us is everything that happens after the data is written in the feature store. And that's often for instance, normalization, imputing missing values, or for instance, one-hot encoding, and so on and so forth. All this happen after the feature store, so at the retrieval point, to allow features to be reused across different models in a different subset of feature data, and so on and so forth. And finally, I was mentioning earlier, Spark is oftentimes not present in training model, but also not serving. So we don't have a Spark context available. We cannot rely on Spark. And so we need to provide a Python-centric API. So how does this actually looks like? If you're looking at a code perspective, we retrieve feature data from the feature store. We retrieve the metadata objects for the different feature groups that we want to deal with. That's the first couple of lines. We assemble in the query object to actually query the data on the feature store. We do that with this pandas-like API, and behind the scene, Hopsworks is going to transform this in a point-in-time correct join, and it's going to execute that on behalf of the user. And finally, the last step is basically creating the feature view object and registering the metadata with Hopsworks. And here you just give it a name, like the query that you want to use. If you want to have the labels that you're gonna use to predict, and if you have transformation functions, which transformation functions you want to apply. Hopsworks comes with a set of transformation functions, but we also are flexible and support like user-defined ones. And then the feature view is actually registered. What feature view actually gives you access as data scientist, actually, it's what we call one API to root them all. It gives you access to both trained data. So for instance, from a feature view, you can generate a trained data set. You can either, you can specify the file format. So as mentioned before, if you're running TensorFlow, you want to get in TF records. You can split it up in different ways and actually generate that static files that you can then use to train your model. You can also get back a training data set as a pandas data frame, so you can just use it directly to actually train a specific model. You can, after you've trained the model, you can use the same feature view to do either batch predictions or real-time predictions. So if you're doing batch prediction, you can specify, for instance, a time window. So you train a model for the first, 11 months of the year, and then you want to be able to make a batch prediction for the last month of the year. So you can basically specify time intervals for which to retrieve data from the feature store to be able to actually do a prediction. And the last part is actually the real-time lookup. So like powering what we call like prediction services, allowing you to actually build a real-time application to actually make those predictions. And the way it works actually, from our perspective, like Hopsworks is integrated very well with KServe, but it actually gets integrated with any other serving framework that you have available, even if you have built your own. That's pretty trivial to actually do. To integrate Hopsworks with, and essentially what happens is that you make a REST call to KServe on the Hopsworks case, and the KServe is going to run this predict method. There's actually two parts of here. The first part, we're actually setting up the prediction service. So you're basically just loading the model, but also loading the feature view that we actually need to use to retrieve that information. And then if you see from line 25, we're actually doing the prediction here. We're going to the feature store. We provide, in this case, we're doing fraud detection of credit card transactions. So we're providing, we want to look up the credit card feature data, and we want to be able to retrieve that. And so this is going to go to the online feature store. It knows, the feature view knows all the features that are needed, retrieves them, and it passes to the model to actually make the prediction. And finally, there's a small plug. If you want to try it out, Hopsworks, you can just go on up to Hopsworks.ai. It's our serverless offering. You can just register for free, and you get access to a fully fledged Hopsworks platform to be able to build your own prediction services. There is a course going on that Jim is running that you can actually subscribe and learn all about like serverless and essentially. That's everything.
Thanks, Fabio. Thanks, Marth. That's great. So we have a couple of questions. We have a little bit of time for the questions. So we have Sai Girish asked the first question. This is Great Expectations used before pushing the data into the feature store or after pushing the data into the feature store?
Yeah, I can take it. So that's what Fabio was explaining, that actually we want to avoid bad data gets into the feature store. So that's exactly why we run it before it's being written into the feature store. So there's a bunch of policies you can specify. So either you can say ingest the data no matter what happens, and you just get a validation report, and then you can trace back later and look what was wrong with that batch of data. Or you say reject everything as soon as one of the expectations fails. And then when you get back that result in the API, you could take your data frame and dump it somewhere else into a temporary feature group or into some temporary storage, so that you can later on take a look at it again and see what went wrong. Our approach is here that we want to avoid those garbage in, garbage out situations, because basically, once bad data is in the feature store, what is your data scientist going to do when he tries to build a model, right? He wants to get a feature, and then Great Expectations is going to tell him the quality of the feature is not good or not enough. What is he going to do, right? He cannot kick off the whole feature engineering pipeline again. So the goal is avoid.
Right. We'll take one more question, and then we'll have to take the other ones on Slack. Actually, there's two interesting ones. If you can answer the first one quickly, then we can get the second one. So the first one is, how difficult is it to convert your programs from pure Python into Spark? That's by someone who's anonymous.
I mean, it really depends what you're doing, and it really depends on the knowledge of the of your Spark knowledge. That's not like from our perspective, from Hopsworks perspective, it doesn't really matter how you write your program. At the end of the day, you just have to provide the data frame, and it's the same API if you're providing a Spark data frame or a Pandas data frame, and we take care of that from that perspective.
And then one last quick one, again, has to be quick. Transformations after feature retrieval, does that increase latency? Why would I do it if it increases latency?
To increase usability. And it depends on your writing, and depends what your obviously what your latency requirements are. But if you are segmenting your feature data into different subsets, or you might have a model looking at the past 5 years of data, you might have a model looking at the past 10 years of data. If you are normalizing those two models, like you're normalizing features for those two models, you can't reuse the same normalization. So that's why we do it after, when you're actually retrieving the data from the feature store. And so when it's like real time, we already have pre-computed all statistics. We're not going to go and compute it every time. So we just have it's just a matter of applying those statistics directly to the data coming in.
Okay, thanks. I think actually Amit mentioned it already. You called them model-specific transformations. I like that term. I'm actually using it in the course, in the Feature Store Service ML course. There's a lecture on it today where I talked about model-specific transformations. So transformations after the feature groups. Okay, that's it. Thanks, guys. It's been brilliant. And you'll jump over onto Slack and answer the questions that haven't been answered yet, I hope.
Yes.
So we'll move on. So the next talk is by Brian So from Doordash. Brian is a machine learning platform engineer. He leads the development of their feature store, and he's previously worked as a machine learning data scientist with a focus on forecasting. We actually had two potential people from Doordash who wanted to talk, but Brian won out the battle of the speakers. Brian, are you here? Can you hear me?
Yeah, getting my presentation set up. But yeah,
I can hear you great. So can you share your screen and then go ahead?
Yep, sure. Hold on, the presentation mode isn't quite cooperating.
Okay, share screen, the big green button. Okay,
yeah.
It says you've started share screen share.
Oh.
There we go. We're looking good.
Can you see it?
Very good. We can see it. Just click on slideshow and we're good to go.
Oh. Awesome.
Over to you.
Hi. Hi. So I'm Brian. I'm the head software engineer for the Feature Store at Doordash, and today I'm here to talk to you about our journey from moving to a single service that pipelines features to a single node on Redis, to a cluster, to a fleet of Redis clusters, and Cockroach DB service, including an all-encompassing feature store service called Fabricator, and some of the growing pains we encountered along the way. Cool. So today we're going to be talking about what caused our hypergrowth and some of the factors outside of just Doordash pure delivery growth volume, our overall architecture, how we interact with our offline stores, and Redis with Elasticache, and some of the limits we've discovered as we've grown out to scale, and kind of what we've done with Cockroach DB as an online store afterwards. Cool. So what drove our growth on our feature store? Well, part of it was trying to make things easy. This is like a core part of our engineering culture. So a year and a half ago, we heard from our data scientists it's too hard to ship features. So we engaged in an effort to really simplify that process for them by building an all-encompassing service called Fabricator, which I'll get into later. And a big part of it that made it pretty successful is that we made it easy for data scientists to feel safe to deploy features. We added a bunch of guardrails that protect against failure and abstracted away a lot of the storage concepts for data scientists. And additionally, there was a large expansion of scope in our business around the same time. So we went into groceries, convenience, and alcohol. And a lot of this just meant that there's a lot more narrow use cases that required a machine learning model and consequently more features. And this just really ballooned how much data we needed to use. And yeah, lastly, there's been a lot of industry advancements in the last few years, and there's just so much more data available now than we had before. And then so with advent of technologies like Spark and PyTorch and distributed training, it's just become so much easier to train larger models that pretty much a a data scientist's ability is just limited by their imagination and how much money you're willing to spend to train a model. Cool. Yeah, so this is kind of a brief architecture map of our service, but in general, our user really interacts with two parts of our service, Databricks and Python, and our feature registry, which is on GitHub and connects to a backend database that serves as an RPC that gives metadata to all of our other connecting services. This is the workhorse that really gives us the ability to have a fine, like end-to-end connection that makes things consistent across services. For the most part, our users are working in Python and PySpark on top of Databricks notebooks, in addition to some local development. We opted to use Dagster for our orchestration over the standard Airflow, just because we found that the user interface really empowers users to backfill and manage their own features, and it gives them a nice way to look at things. And it also provides a lot of manual queuing and concurrency options, in addition to like tighter integrations and custom job kickoff sensors. And lastly, we also store most of our data offline on Snowflake and S3. But for the most part, we've generally opted to store things on S3 because it makes it easier to plug in another service and horizontally scale reads to that service, whereas moving directly through a Snowflake warehouse is a little bit less desirable since the scaling isn't quite as in our hands. And we have a feature service that pipelines in real time as soon as partitions are published from S3 to our online databases, which are now running on Elasticache with Redis and CockroachDB. And to read from our DBs, we have our internal prediction service called Sybil, and it reads from the feature registry so it can figure out exactly how and where to read a given feature that's called for a model. And all of our caller services really only interact with Sybil prediction service. Cool. So I mentioned Fabricator real briefly. So what is it? Fabricator is our internal declarative framework that handles feature engineering, our feature registry, and our online and offline storage. It's a pretty all-encompassing internal framework, and we're not sure if it's a service, a platform, or anything like that, but it pretty much handles almost the entirety of the model development side. So this is an example of kind of how our DSL works. We generally opted to kind of make things as simple as possible. And so we tried to be flexible as well. So if you look, there's effectively two ways that a user can create features here. Either they can just input a simple SQL script and into their YAML file with whatever upstream tables they need to reference and how they want to store it. Or they can, for the more advanced use cases, attach it to a Python script where we have some custom libraries where they can wrap it into a shell and a class. And what this enables us to do is manage the input and output of every data frame going in. And so we support both pandas and PySpark data frames and some other arbitrary ways to load data as well. And because we have this managed environment, we're now able to register all of the entities, the columns, and schemas are known to every other service. And with this also lets us create a pipelining service that's really simple and optimized for most every use case we have. And with just one line of code, our users can deploy their features to be available online. And all it really takes to register a feature is to just list it into a YAML file. And it will then be available to all features within a few hours or so. I mean, to all models within a few hours or so. And if you want to read more about Fabricator, there's a link below. Cool. And so a lot of our offline store just really works with one simple API call, just called get features. We've tried to make this as simple as possible, but effectively you can just list the names of all the features in a list that you want. And because we store all the entity relationships for a given feature in our registry and where they're stored, it'll just communicate with our registry and figure out how to pull all of them from S3. And in the background, we'll automatically join every entity and date as much as possible and return the minimum set of data frames based on the relationships. And because most of our offline storage is partitioned by dates or arbitrary time windows, we can join all of these automatically in the background. And we also allow options for custom joins and custom windows to retrieve, making things pretty simple to just pull. And just because everything runs on PySpark, we can just load up a ton of parquets real quickly. Cool. And now to my favorite part, talking about our journey from a single Redis cluster to using CRDB as one of our secondary backends. So for us, a lot of our guiding principles for online storage are largely reliant on availability, and resilience to failure. This is a core concern of ours because I guess maybe speculatively on my end is that on the early days of DoorDash, we just really tried to focus on keeping people happy. And I think one of the outcomes when you have really bad ETAs, either due to feature store timeouts or something like that, people get really angry when they're hungry. And I've personally been angry when I've had a bad ETA prediction. It's just like, there's nothing like waiting 30 extra minutes for your food. And so part of this design is also like, just how can we have a low latency retrieval on thousands of keys in a single request? And how can we make this cost effective? So we did a few benchmarks. We've had a couple of different iterations on what feature stores we use for our backend. But for our first iteration, we settled on Redis with Elasticache. So we did a benchmark on a few different databases that we thought would be relevant and would fit our use cases. And Redis came out way ahead from the others from virtually every perspective, from a latency perspective. And CockroachDB came in a close second, but it was we just thought Redis would be a better fit for us initially. And part of why we used it is that it can scale horizontally and vertically. You can switch node types and all these things, and just the throughput is just incredible. It can read replicas, and you can restore from backups, and it can support an extremely high QPS. And to this day, I think if you have a super high QPS load, there's not really an alternative that you can stack on top of it that would even be more cost effective. Cool. So our first iteration, you can see there's some sample data there where it's a sample table of a couple features and their attached entity. At first, we stored everything in a simple key value where we concatenated the entity with the feature name and just stored the value there and set an expiration for every key. And what we found is that while it performed well, there was a move to get even faster. And that was just the new challenge for our team. So we did some research, explored some other databases again, but Redis continued to win out. And we eventually ended up moving to a Redis hash map to store our features, where all the features for a given entity would be stored under a hash in Redis. And then we would set an expiration at the hash level. And this resulted in huge gains in performance and cost savings. We were able to serve features at a fraction of the cost and got huge wins as well, where I think we saw pretty ridiculous gains in overall latencies. But this ended up introducing some problems as well, and not everything was as great as it ended up being. So around the time, we just started experiencing huge growth in our platform, largely because we've made it super easy to develop features with Fabricator. We were seeing that we would need to upscale our Redis clusters pretty much every 2 weeks, and the native Elasticache functions just didn't cut it. So when you hit around 70%, 40% utilization across 100 nodes, scaling up a cluster using the native functions can take upwards of 12 to 24 hours, during which you'll experience higher latencies, drops in availability and performance. And while you can use a separate client and have some settings on your Redis client to mitigate this, it's just not ideal, because you now put yourself in a state where for 24 hours, you might not be able to take any action on your cluster if there's an outage or anything like that. So we eventually invested some resources in figuring out how we can have scaling operations with no downtime. And this constituted spinning up a cluster from the last snapshot for a given one, backfilling all features, and then redirecting traffic to the new cluster. This ends up being expensive as well, because you also need to double provision your cluster for a few hours, maybe a day, for as long as it takes to get everything ready and good to go. And this also ended up being a super manual operation since it's not something that you can automate well. So this ended up eating up a lot of our dev time. So I think after doing tons of these operations, we just figured we need to do some more. And lastly, storage is really expensive when you're storing everything on memory. Effectively, your cost will only monotonically increase, even though the number of predictions you make will not be going up as well. So secondly, hash keys are pretty expensive to create in Redis. And because we were creating many new entities with the new verticals that wouldn't be as feature dense, a lot of the cost savings we had were starting to vanish. Embeddings are also exceptionally expensive to store on Redis because one character is 1 byte, and even if you compress an embedding, some embeddings can be hundreds of characters long, making it 100 times more costly compared relative to a single binary feature. And next, provisioning storage predictably is pretty difficult just because you want to have every Redis cluster in a sweet zone where it's safe enough to deploy new features, but it's also free enough where you're not just wasting money. And so sometimes you never really know when a model is going to ship. So over provisioning wasn't just really on the table there. And we experimented with having a pretty aggressive eviction behavior so that we're not constantly uploading values that aren't being used or they're just kind of hanging around. But this ends up being problematic because if your upstream tables are not reliable, you can end up in a situation where you just start seeing values evict from the feature store, and you're not necessarily sure which ones are falling off, and models will all drop off in performance because a subset of values are no longer being sent to the online models. And so we decided we needed to try something new and explore around some more. So that's where CockroachDB came in as our alternative. So we opted for going for a hard disk-based store. I don't think we could have squeezed out that much more performance out of Redis. So we did some research, and why did we end up choosing CockroachDB? For us, it was the best performer in our last round of benchmarks. Maintenance operations on CockroachDB are virtually seamless and result in no downtime. You can, in theory, use it as a multi-region database, but I think cross-VPC data transfer rates make that a little bit less viable unless you can really figure out how to intelligently partition your data. It can automatically auto-scale and respond to skewed usage on a single node. So if data on a single node is running too hot, it'll automatically bisect and distribute the traffic until traffic is evenly balanced across the cluster. And because there are many replicas for a single range, it recovers nearly instantaneously from node failures. And the flexible indexing scheme really supports a wide variety of storage options. And lastly, it uses PostgreSQL, so it's pretty easy to onboard and kind of figure out. But that's kind of not what we ended up finding out, though. But what makes CockroachDB different is it uses this concept of ranges. So if you look at that sample table on the left, the primary key is a fake composite of, I guess, the entity key and the feature name. And primary keys are stored sequentially and chunked into ranges, where a range has the start and end value of the composite or primary key. And those ranges are then randomly distributed across nodes. There are multiple copies of a node, and there is one leaseholder that manages all the locking and distribution and managing when replicas get what. And this allows you to scale your read replicas independently from your writes as well. And then so you can also run a follower mode to have decrease the consistency, but increase the availability, making things pretty performant. And the most important part of this is that because keys are stored sequentially in ranges, that this really gives you lots of options for performance. If you're able to design your data in a structure where you're uploading and reading a bunch of values from the same range, whereas for a hash sharded index, it means that one query with maybe 100 keys will probably go to 100 different nodes if you have 100 nodes in your system. Whereas in this case, it could just go to a single node. Cool, but it wasn't all sunshine and rainbows. It was actually really hard to get this project off the ground. I think from the start of ideation to the end, we ended up taking something around like 9 months to get to a place where we're pretty happy with the performance. So yeah, I think this is something that comes with Cockroach DB that's wasn't intuitive to me at the time, but I guess is obvious in hindsight. But because of the range concept, all tables start on a single node because there's only one range when you create a table. There's a bunch of ways to get around this. You can either pre-split your table into the known ranges, but this isn't as viable unless you're very confident of the distribution of your data and where it'll all go as you upload it. Or you need to slowly throttle your uploads and scale them as you go up until your table is fully saturated. And if your table isn't big enough, it may never scale out that well in the beginning unless you start manually splitting some ranges. So that graph there just shows how the CPU starts when you start uploading values to CRDB. You're effectively just maxing out one node until it splits enough times to hit every node in the cluster. Cool, and this might seem dumb, but more keys, more CPU. But like to elaborate on this point a little bit more, so if you kind of look at those charts there, it shows the relationship between QPS and CPU, and those actually have almost nothing to do with each other. One of the things we found out early on is that some features, like let's say a consumer-based feature where there's many more consumers than there are stores, will be spread out across more ranges. And one of the things that needs to happen during a write is that it needs to load up the range and make it ready for writing on. And so what we found is that the more ranges that are being activated during a given write, the lower the QPS would drop. And this was a significant constraint on our upload throughput. So now our main cost barrier was no longer storage or anything like that. It was actually how much compute do we need to upload all the values in a given day in a timely manner. And at this point, we're not that much cheaper per value than Redis. And this was like pretty frustrating for us just because we didn't really see this happening in the original benchmarks. And I guess everyone has an experience with this where the benchmarks rarely line up with reality and how things end up going in general. So we did a lot of optimizations here and tried to figure out the best way to get things going. And because of the sorted nature of the keys, one of the key things you can do is sort your data before uploading. Although doing a full sort in Spark is generally a bad idea because you just end up offsetting costs that would go into the online storage cluster into Spark computation costs. So you can just partially sort the partitions from S3 before uploading in like a partial sort. And then you want to batch the rows into groups, shuffle the batches so you're not hammering the same node at the same time, and then updating the entire row and not a subset. And this ends up being super important and the biggest performance gain you can get out of this. Because when you in the query plan, when you just update a subset of columns, it'll actually perform a read in the background. And in general, if you just replace the entire row, it'll get rid of that read completely since the database doesn't really need to figure anything out at that point. Cool, and so we ended up learning some of the same lessons we learned with Redis twice. I wasn't around for the initial set of Redis changes, but given a set of 2 ETL tables here, you can kind of visualize what we're doing. On the left is our old format where we had a simple composite key value, and we're just mapping a single value to a single feature and entity pair. And this ended up working okay for a bit, but it created a significantly higher number of ranges. And just because the number of writes was our biggest limiting factor, it just ended up creating too many ranges and it wasn't as performant. And we're trying to figure out how can we reduce the number of rows we need to write to get things going. So we initially opted to avoiding using the JSON map in Cockroach DB since some of the main guidelines are to have your JSON maps be less than 1 megabyte in the value column. So we're concerned that if we were to attach hundreds of features to a given entity, it would balloon that and just completely torpedo the performance of the database. But we figured out that we can eke out a lot of extra gains by grouping feature columns just to their source format. or the table that they're stored in. And this way we could update multiple rows at a time for a given value and store them together and make things pretty dense, but not making them too large so as to create huge JSON maps. And this is kind of where I realized that you're always going to be making some kind of performance trade-off here, just because read performance is always going to be at odds with write performance. Fundamentally, you load a table at a time, and one table will just be a bunch of entities grouped together for a few features. But when you're calling things for reads and for creating inference in real time, what ends up happening is that you call one entity across hundreds of tables. So you've got to pay the piper somewhere. But yeah, this was actually a huge gain for us. And after we implemented this, we saw that we had a 50% improvement in our P99s or P39s, and our upload compute usage went down by something like 60 to 70%. And we're still not sure if we've saturated or gone up that high. And this is without even optimizing any of our input tables to become denser and have more rows. But overall, this was a huge win all around. And we're now at a point where we're pretty happy with the relative Redis latency trade-off, and because we're storing values at something of a fifth of the cost with these changes.
Brilliant. Brian, we're out of time. I don't know if you have anything left to present, but we're you can quickly wrap up very quickly.
Yeah, there's not much left, last slide, but yeah, we're looking forward. We're hoping to take advantage of indexing to create features on demand and getting really smart about our storage and upload patterns.
And there's going to be questions in the Slack, if you can jump over to the Slack, and there's a couple there I can see, and I have loads of questions, but I'll have to skip them. Thanks a million, Brian. Really interesting, hardcore performance engineering there, folks. And we're going to move on. We have David Stein and Xiaoyong Zhu. David is tech lead at LinkedIn. He is the original architect of Feather, their feature store, and he's still continuing to contribute to the platform. And Xiaoyong Zhu is a principal data scientist working in Microsoft Azure. And his background is in distributed machine learning and MLOps infrastructure feature stores. So David, Xiaoyong, are you there?
Yes, can you hear me?
Very clearly. Great.
Yes.
So I'll hand over to you guys, and the floor is yours.
All right, super. Are you able to see me as well?
You're not sharing your screen yet. I can see that you're up next. So if you press the big green button at the bottom that says share screen in Zoom, hopefully we'll get there.
All right, let's see here.
There we go.
Where are we now?
Yes.
Okay, good. Hello, everyone. My name is David Stein. I'm an engineer at LinkedIn, and I will be telling you all about Feather together with my colleague Xiaoyong. And yeah, we'll get started. Okay, so Feather is the feature store that we've been building at LinkedIn for about 6 years. It's supporting a large number of ML use cases at LinkedIn, actually most of our ML use cases at LinkedIn. It is open source as of this past April, and we have a deep collaboration with our colleagues at Microsoft Azure. And together we've set up good support for Feather on Azure. And we also recently announced that Feather has joined Linux Foundation, AI and Data. And so we're thrilled to get to talk to you today about this exciting project that we've been working on. So for the agenda here, you've probably all already know and can see from the different talks so far today, there are a lot of different solutions in this space. There are a lot of different ideas around what feature stores are supposed to be. And so in this talk, we're going to focus, at least for the first part, on some of our ideas behind Feather and feature stores, and how we think about feature stores. We have been doing this for a while, and we've deployed it for a lot of cases, and we've seen a lot of things. So we wanted to share why we built Feather, what we think a feature store should be, and we'll also talk about how Feather is used at LinkedIn, and also how Feather can be used on Azure, and we'll have a demo for that. Okay, why we built Feather. So to summarize, getting features into ML models should be easy. Should be easy. Getting features into ML models should be easy. There's obviously a lot more to feature stores than just this, but I think this is like the core item. When we started, it was not easy to get our features into our production machine learning models. The goal of Feather is to make that easy. And I'll talk about this thing that many folks may not be expecting as the next thing to say. I want folks to think about music streaming apps like Spotify or Apple Music. And you might be wondering, like, what do music streaming apps have to do with feature stores? I would argue that there's an analogy that is actually pretty good that I think conveys the way that we think about what feature stores should be and should become. Anyone who is old enough or has been around for a while listening to music probably remembers, like 10 to 20 years ago, what it was like listening to music before the age of the music streaming services. And in my experience, it was something like this. You would have to go manually get your music files from various sources, various sources, convert them into a format that your particular device you want to use can play. You need to load them onto your device, which may be different depending on the context. And then you need to worry about a bunch of things like whether you have enough storage and whether the bitrate is any good and that the quality will be good, about compatibility. And that was what we had to do all the time, like in the early 2000s. And now we just ask the virtual assistant to play the song. So I was thinking about this the other day. It's like we have solved this problem in the industry. So it's like, congratulations to Spotify and Apple Music and their competitors. We kind of have made this easy for humanity. You can just like ask the virtual assistant to play your song and you just get it. And the analogy here that you maybe by now can guess is that the sorts of complex workflows we saw for getting features into ML models at LinkedIn before Feather were kind of similar to this. You have to write jobs to get your entity data from various data sources. You have to convert and extract, aggregate, join into whatever the format is that your inferencing engine and training system needs. You need to actually then load your data into the model framework, which may be different from training and serving. You have to worry about scale, performance, leakage, training, serving, scoop. We want to change that, right? We want it to be like, you just import the feature by its name into your model code. And then if it doesn't exist yet, you just define and register it using a simple API. So we want feature stores to become like the music streaming app of data dependencies in machine learning. So this hopefully kind of illustrates the challenge we observed and why we built this. Feature preparation at scale with lots of entity features that need to be fetched and joined is really complicated. We're hearing about this a lot in the various talks. There are a bunch of things that need to happen. I don't know if you can see like what I'm pointing at with like my mouse here, but we have raw data, we have users, basically everything in this circle used to be like what individual teams would have to focus on as a large part of their work to do production machine learning at scale. And that's a lot of complexity that ideally you want your ML teams to be focusing on actually the modeling and on the feature engineering. So we replaced that like this. you have, your feature store as your kind of common data layer between, that unifies the training and the inference service contexts, and makes it so that you can just define your features and then get them by name and not have to worry about all of that stuff anymore. Another way to think about what the feature store is I like to think about it like a package manager, but for machine learning. The section at the left that everyone sees something like this at the top of their Python code, it's like, it's hiding a lot of complex stuff, actually. So the era before we had nice package managers and libraries and software engineering, I wasn't really that aware of it, but from what I understand, like going to have to manually get all of your dependencies and link them together is hard. It's easy what we have today, where we can just import the packages. And this is how we envisioned the role of the feature store. You can just import your features into your model code and use them. So for time, I guess I have to kind of hurry up here. So this is sort of speaking to what a feature store should be. The principal use cases of the feature store are to develop features based on the raw data using simple APIs, deploy features for training and for online model inferencing, and then to be able to manage features, monitor them, and share them across teams. So we break it down in this way. Even the term, the feature store, the way that we think about how this should look is there are producers and consumers of features. The abstraction kind of works like you put the features in, you define features based on raw data sets, or sometimes based on pre-computed features from other systems. You have a set of primitives and tools that you can use in order to define the features. And you can also define or develop features based on other features that are already present in the feature store. And then you get features out, which is kind of like we were talking about, just getting them by their name, but with all of the details around how that is supposed to work in the training and inference contexts just figured out for you, like backfilled point-in-time correctness for training and to be computed and stored for efficient retrieval for online inference. Getting a little bit to Feather at LinkedIn. Feather is one of the pillars of LinkedIn's machine learning platform. A kind of motivating picture, I think, of how Feather is used here is at LinkedIn, we have a training orchestration platform that has been discussed in some LinkedIn engineering blog posts, where users can write model training workflows, basically, that produce models on a scheduled basis or on an ad hoc basis and can load them into a model registry for deployment into online and production. There's a human that gets to then push a button to deploy models into the production inference services. And there are safety mechanisms, just as one kind of important example of how the feature store is used, that checks to make sure that the model's feature dependencies are present. And then if they're not there, you don't allow the deployment, right? You want to make sure that the data and the feature definitions and the metadata are deployed first, so that you can know that the model will be able to run in the inference service safely. So a lot of what happens is we're making it so that you can drive most of the machine learning development and deployment process without having to really change any of the code or any of what's happening at the inference service, at least in the ideal scenarios. A little bit more about Feather at LinkedIn, hundreds of models, thousands of features, many kinds of entities. LinkedIn has written a lot about the economic graph and petabyte scale. Our timeline, we initially proposed the project in 2016. We've been building it really in earnest since 2017. Broad and then like majority adoption within LinkedIn by 2020. And in 2022, open sourcing, we have the Azure collaboration and joining Linux Foundation. I want to make sure we have time for the demo, so I'll probably go through this stuff really quickly, but we also talk about this in the blog post. We've seen improved productivity from faster experimentation with new features. We cite from weeks to days. There's improved performance. It's interesting. There usually is like a tension between abstracting over things and actually optimizing them to make them faster. Usually what I think we kind of hear in the industry, right? If you are adding abstractions, you're risking that something can get lost in the middle, so the performance may not be as good. But we actually found that using kind of the automated feature pipelines that are produced by Feather, it's much easier to optimize those most of the time, because the large set of manually crafted join jobs for a particular team, would be very difficult to keep optimally running. So the general solution that we have in Feather has been outperforming those that it replaced. And it has also improved collaboration, made it easy for similar projects to be able to use similar features, whereas in the past that used to be much more complicated to do. I'm now going to hand it over to Xiaoyang to talk about Feather on Azure. And I guess, Xiaoyang, I'll stop the screen share and let you take over.
Thanks, David. Let me share my screen. And before I actually talk about the demo, I really want to talk about the architecture for Feather. So as David said, we built a lot of connectors for the cloud services to make it more enterprise ready. So Feather is integrated with Azure and also with AWS. So here's the architecture where a user comes in. There are two sort of interfaces that users can expect. One is the Feather UI, where it's like a web portal, and the users can explore all the application, all the features registered, all the projects and entities. They can also explore, they can also manage all the access control, which I'll introduce later. After that, they can also go through all the Python command to actually define the features and to get features from different registry, and to reuse all the data and features from different sources. Currently, Feather supports different offline stores, such as like data lake type storage, for example, like Azure Blob Storage, Azure Data Lake, S3, or like Databricks, or those kinds of data lake specific format. Feather also supports tabular sort of offline store, for example, like SQL databases and SQL data warehouses and Snowflake. Aside from that, Feather also supports like streaming sources, Event Hub or Kafka. All the features can be streamed through that and put that into Feather. And after that, Feather will do a centralized compute, which is based on Spark. Currently, Feather supports Databricks and Azure Synapse, so you can use all of those Spark services to compute all the features. And then you can also materialize the feature to online stores such as Redis or Cosmos DB, depending on your IT setup. And then you can retrieve all the Feather features from like a Jupyter Notebook environment, from like Kubernetes, and from different environments. Aside from that, Feather also, because Feather is enterprise ready, so it also supports like enterprise like key value systems, for example, like Azure Key Vault to store your secrets, as well as like AWS Secret Manager. That's for the major workflow. And for the Feather UI, basically we have like a REST API, so user can either call those API directly, or they can interact with the API through the Feather UI. And on the backend, it's the feature registry, which is based on Apache Atlas or SQL Server. That's sort of the high-level architecture for Feather. And then let me jump into a quick demo. So the first step is to provision all the resources for Feather. So there's a long documentation for that. I'll just skip that. Basically, the key idea is to run through a couple scripts and hit this button called deploy to Azure, and we will provision all the resources for you. So after that, you should be able to see a Feather UI. And in the Feather UI, you can explore like there's a home page. You can explore different projects and different data sources. For example, I have a couple projects here where I can see I have registered a couple, and then I can also take a look at all the data sources for different projects. And then the most important thing is to see the features. For example, I want to see all the certain features in a certain project. In that case, I'm going to this feature page and look through all the features that's available. And what's nice there is that I can also see the lineage of the feature, so that I know that's where this feature comes from and how this feature they are derived. As I can let me just show that real quick, so that I can see that in this project we have a couple of sources like the purchase history data and the product profile data and the user profile data, and then we have a couple of we call it anchor features, which means the base features where it's defined directly on the source. In that case, we know that there are a couple features called the total purchase for a certain customer in the last 90 days. We know there's another feature called the product quantity. And then what's nice in Feather is that because Feather really encourages feature reuse, so we have a concept called derived feature where you can define features on top of others features. In that case, I know that there are base features, and then there's also derived features called users purchasing power, where it's based on where it's the definition of this feature is based on those two prior defined base features, which is like gift card balance and whether the user has the valid credit card or not. I can also explore the definition of the feature so that I know that this feature called user purchasing power is defined by the user gift card balance feature plus whether the user has a valid credit card or not. So after all of those, as a feature consumer, I'm very confident that I can reuse those features. But before getting into the details on the Python scripts, let me also show that Feather also has enterprise readiness, which means that Feather has RBAC control built in. Basically, everyone can manage, IT admins can manage all the features in your feature store in a role-based access way. In that case, you can see that there's a web page called management, and you can see the different roles here. For example, you can see like as an admin, I can manage all the features for all the systems, and someone could only have access to like a single feature or single project, and that's supported. And folks can also we can also make sure that folks only have read access or write access, just to make sure that Feather is enterprise ready and all of those features they are protected by the access control system. So going back to the feature consumer. So after we've seen all the derived features and base features that we've defined, so as a feature consumer, the thing I want to do is that I really want to consume those features. Because as a feature consumer, I know that I'm working on this table where I have a couple of observation data that I care about. I have user ID, I have product ID, and I have a couple of feature tables such as the user profile data and the purchase data and the product data. That's and all of those, they are available in the UI, and I just want to use those. So the first step is to, of course, install Feather and import all the packages there. So after that, because Feather adopts open architecture, and you need to specify which kind of endpoints you are trying to use. For example, I'm using Synapse here, or I'm using Databricks here. I just need to specify the endpoints for those systems. And because Feather use Key Vault or those kind of cloud-based secret management system, so you actually don't have to put the password there. All the passwords, they are stored securely in your secret manager, and you can just you don't have to store all the you don't actually need to store the password here. So after that, I specify a couple of settings for the endpoints and initialize the Feather client. So I want to explore the data set a little bit. So I want to read the data from in pandas and take a look at the user ID and product ID and a couple other columns. And then take a look at all the other feature data, like the gift card balance, or the purchase date, or the purchase amount, and the category and the state. So the first thing for Feather is that we actually let me switch to the consumer demo.
Sorry, Jae-Young, can you
So-
move through this quickly? Because we're kind of out of time. So you have to kind of just
Sure.
go through the main parts, I guess, very quickly.
Sure. So what you
Thanks.
need to do as a feature consumer is that you just need to call this API called get features from registry. So you already explore the UI and you just get the feature by their names based on what David just talked. So it's like a streaming app. So you just call those call the features by the name, and then Feather will kick off a job with this API called get offline features, and you can just download the featureized data here. And in that case, you can see that we have user ID and product ID, and we have all the features that we just want to retrieve from the feature store. We have the total purchase, the product price, and everything here. And after that, you can train a machine learning model. And then you can just after you feel comfortable with the features, you can just materialize the features into an online store. In that case, you materialize those two features by their names, the user's age and the gift card balance. After that, you just call this API, which is get online features. And in that case, Feather will just retrieve the features by their names in the online storage. In that case, you can see that we are getting the features for customer 1 and 2 and get their features correspondingly. Of course, you can define the features in a more Python way. Due to the time constraints, I will just skip that. But basically, you can define the features based on their windowing, aggregations, and based on the point-in time correctness. So all of those resources, they are available in the Feather GitHub repository. So feel free to check it out. Right. Thanks for the invitation here, and that's all for this part.
Thanks, Xiaojong, and thanks, David. And I think this is a great lead-in because you've been showing us the API for Feather, and we're now going to have the first panel of the day. And the first panel is about APIs for feature stores. And we can see there that for Feather, we have a kind of an imperative API where you can write some code in Python. But the featured stores didn't really begin that way, so the original Michelangelo, and hopefully people are ready to join the panel. I'm moderating the panel, by the way, and we have Amit should come back from Uber, and then we have Moritz from Hopsworks, Brian from Doordash, David and Xiaojong from LinkedIn and Microsoft, respectively. So hopefully everyone's around. I haven't seen that. Hopefully you can share it, and we can just share that. We don't need to share a screen at this point. We can actually just see each other, which is kind of crazy. We're not talking it into the ether. I'm going into gallery view, so that works a lot better. Okay, it looks like everyone's here. There's some other people who are, hopefully there's some other people who are speaking later who are here as well. We've Amit, Brian, Moritz, Xiaojong, and I think there's David joining as well. Yes, no, he's not. I don't see her.
I'm here.
You are here. I'm blind. Sorry, I can see you very clearly. Okay, so so just a little bit of background on this panel before we get started. The basic idea was that feature stores came out. If we take the starting point as Michelangelo, they introduced the concept of a feature store around what I would call a domain-specific language. It's a well-known concept. So it's not a general purpose programming language, but it's a way of defining features in some syntax that you develop, and then it compiles into some code which is executed. Now, in many feature stores, that might be Spark or it might be SQL to run on some data warehouse. And it was often done with big data in mind. So we've heard this morning, handling terabytes of data, doing complicated point-in-time joins with massive amounts of data, putting handrails on data scientists to make sure that they don't shoot themselves in the feet. There's obviously a huge need for ensuring that features are correct, and DSLs can obviously contribute to that. But we've also seen with the likes of Hopsworks and Feather and other feature stores, more general purpose programming approaches. So using Spark and Python in particular, and data frame based APIs, we can call them. So imperative APIs, where a feature store stores data frames, you write data frames, you read data frames. But then the third aspect are the non-functional aspect of your APIs. So if you've a feature store that has an operational aspect, so it has to return features within a certain latency, and it has to create training data within a reasonable amount of time, They also play into the role of the feature store. So I'm going to start, and I'll ask a question in general for everyone. What is the role of domain-specific APIs? Is that the future of feature stores? Is it the past? What's your opinion on domain-specific languages for defining features for feature stores? And we can take Amit. I'll go around in order, but we'll try and keep it brief. We have a few questions to go through. Amit, what's your take?
Yeah. So I think you brought up Michelangelo and DSL, so I can kind of speak for that. But I mean, I just wanted to clarify a little bit here, is that the way we think of feature engineering is like broken up into two parts, like the part that is done before data is ingested into the feature store, which is closer to data engineering, right? And that's the area where you can probably use anything, right? Like big data, SQL, we use SQL a lot before ingesting into the feature store. But the Michelangelo sort of system applies DSL post feature store retrieval. And the reason I think DSL plays a role there, and maybe Spark or any other technology, it's challenging to do so, is because our common deployment scenario is offline training, offline evaluation, real-time serving, right? So now imagine if you had used a Spark API and you use some sort of reduce operation, something crazy. Translating that to an online serving construct is extremely hard. And to do so in low latency, right? And so that is the reason we really implemented DSL to sort of contain the kind of transformations you can use, and it can be executed symmetrically online and offline, and keep the computation reasonable in the real-time world, right? So as long as you have any technology that can achieve that, I think it's okay. DSL is one way of doing it. That's my take. Yeah.
All right, cool. So yeah, I mean, I think we agree on the model. You use the term model-specific transformation.
Yeah, like one-hot encoding and stuff.
Yeah,
like that.
So what a data scientist would call transformations, as opposed to what a data engineer would call transformations. I'll just go around in order. So David, do you want to give your take on this?
Sure. So I think this is a very interesting question. I think that I like to think about a Swiss Army knife analogy. I think that we want it to be easy for people to define features that they might be likely to say, pointing at the data assets that the company has. Like if someone wants to define a feature like the number of times a user has visited this part of the site over some range of time, and just to be able to use that as a feature, we want those things to be easy to say. And providing a kind of Swiss Army knife toolkit that makes the kinds of features easy to say that used to be more difficult when people would need to write their own data pipelines to do it is sort of what we want to do. What belongs in the Swiss Army knife? Should there really be a Swiss Army knife, or should it actually just be like a big toolbox that's, like some bigger system like Spark? Like I think that there are like a whole lot of things to say there. I think a lot of the things that Amit mentioned, about the challenge of trying to then do some online execution of code that was actually user wanted to write using a Spark API. You can't really do that kind of stuff. So there's different angles, to kind of go down with that. But what we do with Feather is we try to provide it is a Python API, but it is also kind of like constrained along certain rails to make it so that you can define features that can then be performantly produced. And then there are also, trapdoors to use like UDFs and other kinds of more advanced APIs for the cases where that is hard to do, or where the Swiss Army knife doesn't have exactly what you need. So at LinkedIn, we see some use of those kind of UDF APIs and things like that for advanced cases, but we want to hit it such that the Swiss Army knife covers, 80% of cases and still leave the more advanced stuff possible. There's probably even more I could say about like how these APIs should evolve in the future, but I'll probably pass to the next person.
Yeah, Jae-Young, do you want to add anything on this on Feather?
Sure. I think that so first, this is definitely a good topic, and I want to bring up another perspective, which is from the feature consumer point of view, because for feature store project to be successful, like within Uber, LinkedIn, Microsoft, or in many other customers, the first thing we want to do is that make sure that all the platform can be used easily, right? And then if they say, look, all the capabilities of this feature store is this DSL, and you need to learn the new DSLs to onboard to Feather or other feature store. And while in the meanwhile, the customers or the end users, they have already a bunch of code in Python, Spark, or whatever languages that they already have. It's really hard to migrate them to a feature store solution. And it's even harder to convince the LT because, you know, feature store is more like a productivity tool. And then we are convincing them by saying, look, by using this productivity tool, you have to spend like half a year to onboard to this platform and, you know, restructure all your feature engineering code. I think that's probably impossible to sort of convince the LTs and the management chains. So
I think that's a very important point. Yeah, reuse of your existing feature pipelines. Yeah. Moritz, what's your take?
In general, I agree with what Xiaoyong just said. I also think that in the long run, the general purpose framework will win, because if you start with a DSL, you usually do it by providing a bunch of abstractions which limit, and then as you grow your use cases, you will want to onboard more and more complex aggregations or functionality. And at the end, you will end up with a framework which re-implements what was there, or your DSL gets more complex and more complex over time as you grow the use cases. And then you'll end up where you could have started off from the beginning.
I'll throw in there the example of testing, for example. So, of course, everyone wants to test their feature logic to make sure it's correct. And, you know, how do you do that in a DSL, I guess? Maybe that's not a question for you, Moritz.
No, but then my other point that I wanted to make is basically for streaming pipelines, maybe their DSLs have a chance because the set of aggregations that you have and common operations, it's much more limited than in batch use cases. So that's what I see, that there's many more DSLs coming in stream applications.
Brian, you with Fabricate, you talked a bit about, you know, handrails for data scientists and helping them go off. What's your take on DSLs versus general purpose?
Yeah, so I echo a lot of the same sentiments as Amit, where there's like kind of two phases, the data engineering and the deployment side. And we use like a mixture of both DSLs and kind of general frameworks. And they've both been pretty popular with users, and general frameworks are great, but I think a lot of the success we've found is that general frameworks take a lot of boilerplate to interact with other components. And then so that constant copy pasting setup you need to do to interact or like start a new job kind of becomes tedious. And because you have so much copy pasted code, any kind of migration or API breaking change becomes a monolithic task, right? Where now all of a sudden you're replacing 1,000 references to really make a significant API change, or you're waiting for like a breaking component or a V2 function or something like that. And I think DSLs help you kind of avoid that situation. But I think in general, DSLs will naturally crop up for any general framework, because not every company will have the exact same use case. And I think, just how your data is structured and what you need will change from company to company. So you just end up needing a DSL, in which case anyways.
So I'll ask a open question if anyone wants to take it. I mean, is there anything beyond DSLs and the kind of data frame APIs that we've seen out there? I've seen, for example, in data pipelines, there's, you know, some people looking at functional programming languages like Elixir for some of the benefits of functional programming for data pipelines. Are there any other approaches people can think about that maybe are interesting to look into?
Yeah, I mean, if you look at deep learning people, they are just using, there's no DSLs. They just retrieve features from the feature store in our case, and they just do the transformations inline in PyTorch or Keras. And so the whole feature engineering is now just part of the model ecosystem. So, which is what the Scikit people did anyways in the beginning. So it's kind of come back. I mean, so that's what we at least see. So there, so that's one form where, there's no DSLs. You just write code and PyTorch, and will restrict the amount of Python you can do anyways. Like I don't believe you can do like open-ended Python, but I think the key still remains you need to restrict the type of computations you can perform, so you can have some reasonable guarantees around at serving time, especially, right?
So I mean, there's a good point in there, which is related to. Sorry, Julian, you want to say something?
No, like a restricted data frame or something. Yeah. A
restricted data frame, like a snow park data frame.
Go ahead, Jim.
No. There's an interesting point there, which is related to deep learning. So feature stores are often associated with tabular data. Enterprise data is often tabular data. And when we think about the APIs that we provide, they're often to help with the tabular use case. We have data frames to contain our features and so on. If you're using deep learning, you're probably not working with a pandas data frame. You're probably getting TF records or some other file format like that. So how expressive do our feature stores need to be, or do we just work on the enterprise use case for the moment? What are people's takes on this?
I can.
Okay, go ahead. I'll go next.
Yeah, I guess anecdotally to the first part of your question, I saw like a really interesting library today where Databricks just kind of open sourced Delta Lake, and one of the libraries they released is like Delta RS, which is a library to interact with Delta Lake, written completely in Rust, but it cross compiles and has a library that publishes in like 5 or 6 different languages. And to me, I think the most valuable part of any feature store is the ability to interoperate with like 4 or 5 different services. And by necessity of a machine learning platform, most of these services end up being in a different language. Data scientists need Python, real-time needs Java, batch processing Java or like Scala, and then online services need to be in C++ or some low-level language. And I think one of the things we struggle with is having a common contract for how to evaluate a field or a protobuf or anything like that. And then so any kind of library that can abstract all these things away, where instead of writing the same function 5 times in different languages, is kind of where we're going. And like just anecdotally from using like protobuf libraries from Google, this has just really simplified the handshake between everything, and having a single RPC server that manages all the interactions for how we manage and interact with features has really changed the game for us and lets us propagate changes out to the entire system almost instantaneously.
That's a very interesting point you make, Brian. It's when we think of APIs, we often think of them in terms of REST API with a specification in terms of the name of the method, the parameters, and the types. We also have data level APIs, what are often called data contracts. And when you obviously have many different clients written in different languages trying to interact with your feature store, there is obviously you have to translate that. If you're going to have an imperative endpoint, a network endpoint, you have to translate it for all of those different languages. Whereas if you use something like Arrow as a common kind of data format that can be interpreted by all these languages, or protobuf or those, what are people's takes on the need for data contracts, if you will, at feature stores, or is that something that we're not there yet? Open question, anyone take it?
I can take that because I think as Brian just said, like it's probably more related to how you actually define a feature store in some way, because it's like feature store needs to be an open architecture because it needs to be operated with many of the other services. If we sort of fix it in a way that say, hey, everyone needs to use this fixed schema and fix everything, I don't think that will work to onboard feature store into many of the enterprise settings. And from that point of view, I feel that, it should be like either protobuf or some sort of open standard or open schema for data, and then feature store will just adopt that rather than, developing a new thing completely for feature store. That's sort of my high level take.
So feature store is a data platform and should live in the data ecosystem.
Right. That's my feeling.
Cool.
I think that you could also say that feature stores sort of imply their own kind of data contract just by what they need to do, right? What in the previous world before Feather was sort of unwritten contracts between training and offline experimentation systems and then the online systems that would need to run those models. It's kind of formalized with having names of, a feature namespace and feature types, and the ability to then use like a common serialization format or something like Arrow or whatever your system is going to use in order to actually present those features. It first requires having a registry and a namespace and a type system for the features.
All right, I'm gonna move to a little bit. So something that came up in both Amit and Brian's talks were embeddings, and where do they belong into FeatureStore API? So I guess the bigger question is, should embeddings be part of feature stores? Should the feature store manage all data for AI, or should the embeddings live in their vector databases, or what's people's take on that? And maybe I'll put it Amit first.
Yeah. So I'll tell you our experience. I think a lot of embeddings you're seeing being built by the deep learning people. Traditionally, I think embeddings would be your first layers of your neural network, and that's essentially a very complex feature engineering that's going on inside the model. But I think people have been, at least a lot in the recommendation systems we've been working with, they're taking those embeddings and turning them into feature store like artifacts, right? And these are vectors of numbers. And so we are actually actively onboarding them to the feature store. So they're not, so you can sort of represent them and onboard them, not just in the feature store, but in Michelangelo as a whole, make them first-class citizens, right, of the platform. So this is a kind of like a form of transfer learning. You can actually optimize your models by taking your embeddings, persisting them in the feature store. And the feature store is then you just pick it up from the feature store into the downstream models, right? So that's what you're seeing a lot. And that's why we're kind of making embeddings. They're for first-class types, not just first line, but also embeddings need to be managed. Unlike a standard data pipeline, like an embedding is typically now these days generated through another deep learning model, right? So the life cycle of that model needs to be managed, which is slightly different than how you would manage a standard data pipeline, right? So that's how like the feature store design is getting influenced. Yeah.
I would just say +1 to that. It sounds very familiar with regards to how Feather is used within LinkedIn. We have many use cases that in their kind of model architecture, they will break the model, take the first layer that's producing embeddings, they'll run it as one model. The output is a feature that they put into the feature store to be able to use at serving time with a bunch of other models. Like this is it's a pattern that we see for sure. So that's like why we had to add tensor-based feature types and things like that in Feather. Yeah, +1.
Anyone else? Say anything on embeddings, Brian, Moritz?
I have just to answer your question, Jim. I think the conclusion there seems that, which I also agree, is that like everything, like feature store should support embeddings, but sounds like the embeddings should be stored in like a embedding specific system, let's say Milvus or those kind of embedding stores, while feature store should have more like the interface for that, like the embedding type support or vector type support, and then sort of make it first-class citizen, as Amit just said. I think that's also what Feather is doing, and that's also what Uber is doing.
Yeah, I mean, so there's two parts to it, I think, which are interesting. One is that where should be the single source of truth for embeddings, because we do have vector databases, right? So feature stores do not provide similarity search, which is what embeddings are. One of the use cases for embeddings, that you have an embedding and you say, give me the 200 closest embeddings to this in this high dimensional space, and that's similarity search. And of course, you have specialized stores for that. But often those storage engines, they're more modern, more recent, and if we have, for example, OpenSearch in Hopsworks, and we can do embedding search or vector similarity search in that, and there's an API for it. But OpenSearch is not considered a single source of truth, right? You would store in one platform and then replicate to it. So I'm just curious as to, like, from a data scientist perspective, should we be providing a unified data for AI API to them to allow them to do all of these things, to do, you know, similarity search through our feature store APIs, or should we just have those as separate systems with separate concerns and just accept that, hey, you know, data is becoming more and more specialized, so let each specialized system handle its own data. That's one of my takes on it. Any comments on that? Or
I mean, we try to make the feature store at least the source of truth as far as the definitions of embeddings are concerned. But we also integrate with our Uber's own search engine, which implements an ANN. So, you know, they're available for, you know, similarity search and other mechanisms.
So they're available
the
by
source of truth still remains valid.
Yeah, I would think about this like supporting different kinds of deployment targets. The feature store system should be able to, you know, write to Redis for certain kinds of use cases, and then to be able to write into other kinds of retrieval engines. And where you're still the invariants are, you're still dealing with actually like the same feature, whether it is being served out through one kind of serving layer or if it's being served out through.
So maybe like we have offline, online, and potentially vector databases and another target.
Yes.
I have a question, because you brought this up, David, about you know, embeddings being a feature type. So that's something I've spent a little bit of time thinking about. And you know, in databases we have data types. So you know, and we talked a bit about schema and unifying schema between online, offline, consumption, production, and some of the challenges of data flowing through systems and ensuring schema is consistent also across programming languages. So it's quite a complex topic. But in machine learning, we also have feature types. You know, it's a categorical feature, it's a numerical feature, it's an embedding, it's a list. And they confer different capabilities. So, you know, if it's a numerical feature, I might like to perform a form of what we call transformation. So maybe we're going to do a log transformation or normalize. And if it's a categorical feature, I might encode it into a numerical representation. Feature stores currently, as they are, don't really capture, I don't see any APIs that capture those feature types and, you know, enable to lift the level of abstraction of feature stores to make it easier to do that. Is there anyone who thinks about how we can help make it easier for data scientists to, or how we can extend our APIs to encapsulate some of those concepts that we talk about, but we don't tend to provide tooling for yet?
So we do provide something like this in Feather. There are kind of two notions of type, right? Like you, I think, mentioned. One is around kind of a semantic type of a data point that may matter to a data scientist, and another is more like what is going to be shape of this tensor when it is then, you know, inserted into a TensorFlow model or something like that. And Feather does support defining features as categoricals. There are a few other supported types like that too. Then the output type that is passed out into the like the training or inference context is then, it doesn't reflect like categorical. It would just,
yeah, sure, it's
at the lower level type to the, you know, to the machine learning platform construct. So we have this sort of high level and low level type paradigm within Feather, which I think is my preferred way to do it. I think that like it's useful to be able to talk at one level, right, about like what type of tensor is this thing, and then to have in the Swiss Army knife and in the definition APIs, the ability to have, you know, more convenient and semantic concepts to help people define their features that they want to define.
Anyone else want to comment on feature types? And
yeah, I just wanted to add that it also opens up like help we can do or pain points we can take away from the data scientist. And because if you see that you have a categorical feature, there's usually a bunch of steps involved that you don't get around when using a categorical feature. So either you have to one-hot encode it or use some kind of label encoder. And maybe that's the next set of tooling that we can provide to propose those or automate those transformation functions essentially that are coming after the feature store.
The model-specific transformations.
Yeah, exactly. So, yeah, maybe it can help in like selecting the categories which should be kept as features for my one-hot encoding, or yeah, some type of binning or those things.
Yeah.
Yeah.
Because
And,
we do see that a lot. Sorry.
So
Oh, yeah.
we're running out of time. So we've talked a bit about APIs, and you know, I think we haven't had too many disagreements. Where Feature Store is going from here? You got like going to be a quick answer. I'm sorry, it's going to be like 30 seconds. So this is open. You don't have to answer it, but please go in turn. Where do we go with Feature Stores from here?
My favorite is metadata. Connecting the downstream and the upstream through a common metadata, I think, is where we're going.
I think
yeah.
we're going to be moving towards features being generated in real time, and that's how you collect it, where you just either reprocess your entire, I guess, Kafka stream and then generate a feature based on kind of like Flink SQL on demand and reprocess everything. And that's how everything gets created versus the traditional old SQL way of aggregating things in the background, trying to replicate what happens in real time.
So the what we call the flywheel, where the data flows in and around and back in.
Mm-hmm.
Yeah, that's definitely a big thing. Making more of the Swiss Army knife tools work well in the real-time streaming setting. To rely too much on that analogy of a Swiss Army knife is a thing that I think about a lot for Feather. For like the long-term future, like what will we be talking about feature stores in 5 years, or how will these systems evolve, and like how do they relate to other parts in the ML stack? It's like or what's, I don't know, what does the future hold? It's I don't know if that's exactly what you meant with the question, but there's like, you know,
that's good enough. Thanks. Xiaoyong.
Yeah, I feel my biggest sort of vision there is at least to get Feature Store as a concept more as a proven success to all the users, because we do have a nice group here, but it's still a small group compared with, let's say, data engineering, Spark, and all those kind of huge folks and the huge community there. So I think Feature Store as a new concept still have a long way to go, and getting more adopted and get the value proved to the folks outside of this community. That's probably the highest priority for me.
Moritz.
Yeah, I think we're moving more towards, or like we'll be getting closer with the serving side of things. So if we think of deriving features at real time, we need to be tightly integrated with the serving infrastructure. So where does the data come from with the request? Where does it go for feature engineering, and how does it get passed to the model ultimately, right? So the closer the two are together, the easier it will be to get to this future where all the features are computed on the fly, basically. And then also getting back the prediction and writing it back into the feature store, or into some kind of other prediction store to be able to later on monitor the model and also the features.
Okay, thanks everyone. There were a few questions on Zoom, and they'll go out over the Slack. So please jump over to Slack and see if you can answer them. We're now and I'd like to thank everyone again, and thanks both for your talks. So thanks Amit, thanks David and Xiaoyong for your talk. Thanks Brian, and thanks Moritz for your talks. All been fascinating and really gave us a great insight to where we are in feature stores today, and some of the challenges that you've all been solving. And thanks for being here on the panel. We're now going to take a very short break, just a couple of minutes. Not much breaks today, not much for me. But jump over to Slack. There'll be some more questions over there. And we're going to come back with Disney in a couple of minutes. That gives me time to take a couple of minute break. Right, and we're back. That was a crazy short break. Dustin, are you here?
Yes, Jim. Hey, can you hear me?
I can hear you. I can't see you, but I can see you. Looking very good there. I love your T-shirt. It matches. This is the branded Feature Store Summit merch that our speakers have. So Disney, really exciting to hear from you. So Dustin Hammerla, and I'll give you a quick intro, Dustin. Dustin works obviously at Disney Streaming, and he's a manager of the machine learning engineering group there. And he leads the development of a general purpose feature store for machine learning. And before building machine learning infrastructure, he spent several years developing and deploying ML models for different use cases. And I think this has been a very good year for Disney. I think my kids are on to me to get Disney streaming instead of Netflix. So it'll be interesting to see how you're using feature stores to power your streaming platform. Dustin, over to you. You can try and share your screen, and then we'll see if that works okay.
Thank you, Jim. Can you
Brilliant.
see my screen?
Everything, yeah.
Perfect. Right on the first try. Yes. Good morning, good evening, wherever you are as part of this wonderful global community. Really good talks so far. Yeah, my name is Dustin Hammerla. I'm a manager of ML engineering here at Disney Streaming, and we are building, or my team is building, our internal feature store that is powering various ML use cases across all of the Disney streaming apps. And for those that don't know, that's not just Disney Plus, but also Hulu, Star Plus, and ESPN Plus. The agenda for my talk is pretty straightforward. I want to kind of start off with an overview and the motivation to what led us building our own feature store, and then talk more about its capabilities and what problems we're solving with our feature store, and then kind of pull back the curtain on implementation and architecture. So yeah, taking a quick step back, I know this is obviously Feature Store Summit, but our feature store is part of a larger ML platform that we call Nexus. Nexus obviously aims to democratize and accelerate ML development across all of Disney streaming. And there's 4 other main components as part of this ML platform. So we have the model engineering system that consists of our real-time inference infrastructure. So data scientists, machine learning engineers interact with this component to kind of develop and deploy their models. And we have a workflow management system, which is kind of an Airflow on steroids, where practitioners can schedule and execute various workflows, so batch training and batch inference, for example. And then we have a context and event processor. Since we are general purpose, there's a lot of config files and context going on across different use cases. So we want to provide the ability to define this context and these configurations in a central system and not kind of buried inside ML code. And then when we were talking about nearline inference, we give our practitioners the ability to kind of specify what types of events the pipeline has to listen to that would then trigger inference. And then lastly, we have an online metrics component that allows us to track performance of our models in real time. So, with this in mind, obviously, compatibility and being able to, customize the APIs so that our feature store would interact nicely with the other components was definitely a driving factor for when we decided on architecture and build versus buy. But again, why did we start on this journey? And probably some repetition here. but we needed a way to improve how features are created and how they are consumed, because what we saw in our legacy pipelines were kind of these bespoke pipelines where data scientists would kind of define and run their feature transformation code alongside model training and inference. And so you would not only repeat the development work there, but also kind of repeat the compute. And so with the feature store kind of in the middle, we are decoupling these two steps and have different computing environments ingesting features. So this can be batch processing or stream processing, and then different computing environments reading features back, be it in batch for training or inference, or using our real-time inference infrastructure to fetch features in a low latency fashion. And so unifying all of these ways how features can be generated and how they can be consumed, it's I think one of our main value adds, or one of our key factors that I also want to talk about more on the upcoming slides. And then, of course, if you register features in the feature store, then they become discoverable and shareable, and we really reduce the time to the next model. And so again, one could say I've seen this before. This was kind of the general motivation when we started to look into the concept of feature stores. We looked into the market, and then we realized, okay, seems like we have some additional requirements. And at the time, which again is over a year ago, we saw that existing products weren't really meeting some of these. And most of it had to do with our global scale batch training and scoring. So Busy Plus is obviously available around the world, and we train regionally specific models that then need to be fed regionally specific data. And then if you add experimentation to this, where we potentially feed different slices of the training or inference data based on user segmentation, and we're running a A/B test, for example, that kind of data distribution, we wanted that to be kind of native to the feature store. And then another thing that we saw in kind of the third-party offerings was the concept of one training data set, which, at least for part of our use cases, wasn't really the case. We needed to, surely we had one training or inference data set, but we would additionally have to be able to manage other data sets as well. So potentially some contextual data sets. Think of pairs of recommendations that you don't want to necessarily appear together, especially kind of in a family-friendly environment like Disney Plus. So being able to kind of specify multiple data sets, doing this natively through the feature store was another requirement. And then, the way we were running our data prep jobs is in Spark, but our training and scoring runs in kind of a Dockerized single node environment on AWS Batch, where we have multiple instances of a model, but we don't have Spark to distribute that data to these specific single nodes. And here we kind of had to get creative. I'm going to talk more about this one, where we kind of build our own distribution engine to bridge this gap. And then I've spoken about the compatibility with the larger platform. That was a driving factor. And kind of organizationally, we had legacy infrastructure and teams in place that were ready and eager to kind of get going with the kind of next evolution of our ML infrastructure and building out Feature Store. Yeah, so that's kind of how we started on our own journey to building our internal Feature Store. Okay, yeah, what pain points do we solve with Nexus, and what are the Feature Store capabilities? And looking at some of the other talks, it's never a single sentence of what the value add is of a Feature Store and what problems it solves. It's at least always a paragraph or more. And so when I explain to someone what do we solve with Feature Store, we kind of use this framework of a capability map, where we define or distinguish between auxiliary capabilities. So here we have a Feature Store UI where engineers can go and kind of discover new feature data sets and features. We have statistics and validations that can run once data arrives at the Feature Store to kind of provide intelligence and data quality assurance. We have SDKs in Python and Scala. We have feature transformations. So for us, at least at this point, it is more of an auxiliary capability. I know some other teams have focused more on the transform part, but yeah, for us, it's a shared library. It's kind of a CI/CD tool stack to be able to deploy feature transformations really easily. Point-in-time joins, a sandbox environment that allows practitioners to kind of iterate and experiment with new feature data sets outside of the production environment. Yeah, but these are kind of on top of what we call our core capabilities, which is really around data transportation in a way. So these, we kind of see data transport is kind of at the center of, how do you compute and write features and how do you read them? And because there's so many options available for different use cases, and I'm kind of gonna walk through these different modes. So when you're writing your feature transformations in batch and you're reading in batch and you're doing this in Spark, there's no big magic here. We're using Spark data frames. But then I've alluded at this before, but if you then want to consume this large data and potentially a subset, maybe a subpartition for a regional data set, or you're specifying some memory constraint where you only want to read a subsample of the data set based on like a max memory requirement, then you really can't use Spark to kind of identify your files. And so here we built a service endpoint where a one-node consumer can query our API and kind of get file pointers back, so it can then read that subset of the data into its one-node environment. And then moving over, if we want to read features in real time, we then have another Feature Store mechanism where we sync the data. So we process it and generate it in batch, but then we sync it to our online key value store. And then moving down to another kind of mode of computation, which is stream processing. Here we offer the ability to generate the features in stream and then ingest them into the offline store, as well as ingest them directly to the online store. And then a third category that we see is kind of real-time compute, where we can say feature transformations with the Feature Store, kind of model-specific feature transformations. And you can apply those UDFs on the batch data, as well as compute in real time for example, an inference context. And then lastly, another mechanism is the feature logging. So no matter how you decide to generate your features, at inference, we can save the entire feature vector, the final feature vector, into our offline store to make it available for batch reads. Yeah, and so we use this kind of framework to organize our own work and roadmap, and it's been definitely really helpful. And then also when we have to support so many different use cases, and any particular use case can kind of pick and choose their mechanisms and kind of their pathway to their data. Yeah, let me take a little bit of time. Okay, so looking a little bit closer at implementation architecture. So essentially our feature store consists of 4 main components. We use Delta Lake on S3 for our offline store. We have a feature registry, or the brain of the whole system, which is a service on top of a Postgres DB to store all metadata related to features. And then we have a separate low latency online feature service on top of Redis cluster Elastic Cache to serve all of the low latency, high throughput reads and writes. And then we have client SDKs in Scala and Python. And to, I mentioned there's many different options how data can flow through this system for different use cases, but kind of picking one of them and showing some kind of pseudo code to make things more tangible. Let's look at how our system operates when we're writing data in Spark and we're reading it in kind of a non-Spark environment. So we distinguish between 2 different classes. So we have feature groups that are kind of potentially model agnostic, general data sets across models that data engineers prepare. And then we have a feature service object that a data scientist or machine learning engineer would prepare for a specific model. So there we can say there's a one-to-one relationship between a feature service and a specific model, where we can then tie together different feature groups, for example, for one specific model, specifying joins and things like that. And so, when we're running this pipeline, we would, the Spark job, for example, would use the SDK to pull its metadata, connect to the feature store, get a feature store object, get one or many feature groups. So in this example, we already assume that the feature groups have already been populated by a previous step. We then create a feature service and then ingest that kind of training data to the feature service and register it with our distribution engine. And then at read time, model wakes up, again, uses SDK to get its feature service, and then it could use the feature service to query a subsample of the data. So we're running, multiple instances of a regional model. We would query just that regional specific data and kind of distribute it using natively our feature store. Okay, yeah, and then moving over to kind of the stream write, real-time read scenario. The streaming job would again get metadata from the registry, and also here we use the same concept of feature groups to organize the online data as well. So we serialize the protobuf and kind of build key building logic to kind of build the hash keys and write this data to the online feature service. And then for reading features back for real-time inference, we provide a join API that gives us a query plan that kind of specifies which feature groups have to be fetched, and kind of also we can translate this query plan from a kind of generic representation to kind of a Redis type query read plan. So we would save the query plan with the feature service, and then when the model is deployed into the real-time inference infrastructure, it would wake up, again, load its feature service, and then could run this kind of get feature vector method to retrieve a feature vector in milliseconds by passing primary keys from a real-time request. And I think I'm good on time. That's it. Thanks for your attention, but also thank you to the Feature Store and data engineering community, especially the open source projects like Feast and Hopsworks that were definitely a great inspiration for some of the things that we had to solve as well. So thanks for having me. And we are also hiring. If you are wanting to join us on this journey, please reach out.
You're of course allowed to do that. Spend your time to tell people that. We have a bunch of questions. We have some time for questions. So Sai Girish, who's been very active, thanks Sai for asking all the questions, is asked the first question: is it possible to read features by applying filters on the features rather than the ID?
Yeah, that's a good question. So I am assuming this would be for the offline read, the batch read.
I mean, I think like I can tell you about how we do filters in Hopsworks, for example. You, if your data is stored in Parquet files, you can have a filter, a push down filter, which prevents you from reading up all of the data from feature group that you need to read. Maybe you're going to filter based on time or a value of a feature or a range. And then if it's going to be Spark that's going to do it, it'll push down that filter to the Parquet files, which means you won't have to read up as much data, and it should make it more efficient query. Is there any thought? What's your thoughts on that? Or?
Yeah. So we're doing something similar, but without the need for Spark, right? This is kind of what I described as our distribution engine. So we save a representation of the entire tree, so to say, in our registry as well, and we are able to filter and kind of retrieve the relevant files that belong to a filter query without needing to do the push down predicates again. For that, we would need Spark, but we kind of really just leverage the metadata entry, which also runs much faster, and kind of are able to really isolate the relevant files for any filter.
Okay. We have a few more anonymous attendees asking questions. We have, by the way, we have listeners both on Zoom who give named questions, and then we have people on YouTube. So we're coming through different channels. The first one is, what kind of latency request constraints do you have? Do you have any? I guess you have very low latency requests constraints, low latency request constraints because you're using Redis. But can you give any details on that or through use cases?
Yeah, so yeah, definitely sub 100 milliseconds, and we are able to run read queries against our low latency infrastructure in a few milliseconds as well.
There's a little controversial question. You don't have to answer it. You've been through the build versus buy, and you decided to build. Any regrets, or what would you build again if you're given the choice? Advice for others? I guess given your scale, maybe you have some comment on that.
I think again, I think in our case we had definitely some specifics that were specific requirements that were specific to our business, and I think it was in the end a good decision to go with build. But it wasn't definitely without its struggle, and you do need a larger team. There's so many components that you need to build. So there's definitely a big consideration on if you can make this happen with your internal resources.
Yeah, I think that's why we get paid to build stuff. And it's the fun part, of course, as well. There are more questions, Dustin. And so if you could jump over to Slack, you can answer more of them. I think someone's asking in the chat as well. So please ask questions in Q&A, and if you put them in the Q&A button at the bottom rather than the chat field, you can also ask questions on Slack, and our speakers will try their best to answer on Slack. So that's Disney, and we're going to move over to Nikhil Sima. And Nikhil has been around for a while, and Zipline has been around for a while. I think you were number 2 as the feature stores. I think I remember there was a talk in maybe 2018, early at a Spark Summit, about the feature store at Airbnb. It's now called Big Head Zipline. I think Zipline's your feature store, but Nika will tell us a bit more. He's a staff software engineer on the ML infrastructure team at Airbnb, and he's working on Big Head. That's their end-to-end machine learning platform. And prior to Airbnb, he built a scheduler and stream processing framework at Facebook. Nikhil, have you've made it through the Zoom kind of challenges of getting yourself online here?
Yeah, sorry about that. Thanks for the wait.
We're great. We can hear you fine. Yeah, you can try and share your screen just to make sure that we can get this party started.
All right. Do you guys see Chrome?
Yeah, I can see it. Perfect. So go for a slideshow, and we're there. It's over to you. The floor is yours.
Awesome. Hello, everyone. I'm Nikhil. I think the intros have been great. No need to reiterate. So we're talking about Chronon, Airbnb's feature engineering framework. So there are 2 terms in the industry, a feature store and a feature engineering framework, and probably also go into why there is a difference and what are the main differences. So some announcements. So this used to be called Zipline. If you saw, the title used to be Zipline, and now it's changed to Chronon. Do not worry, you're in the right place. Right, and currently we are doing a private beta. So we have been working with a few companies to install, set up Chronon and get some feedback and finalize on the API, more or less. Right, so if you're interested, drop a mail to either me or my manager, Jack. Cool. With that, let's get started. So this is the team behind Chronon. So it's not just my work. I want to thank all of these folks, wonderful folks that have worked with me in the last few years to bring this to light. So the agenda is really simple. So what's a feature platform and how do you use one? All right. So to understand a feature platform, we need to take a step back and see what are the big pieces in the ML workflow. So the simplistic view is that there is some training data. You generate a model based on the training data through model training, and then you use it for inference, so either online or offline. Right. So I call this the Kaggle view. There's a lot that happens behind the scenes to get this view to keep churning. So you need some features offline and labels offline, and you join them to generate training data. And for online inference, you need features to be served online, right? So all of that comes from raw data that already exists in your company or data that you have access to. So the job of the feature platform is to drive all the red arrows. I don't know if you can see clearly, but there is these red arrows, and then there's black arrows that are not bordered. And the job of the feature platform is to take raw data, generate features and labels for training data, and also serve them online for inference. So it's a lot of compute heavy work, essentially. Right, so just walking through these arrows. So there is feature backfill. So you look at raw data and backfill features. So if you have a feature idea, let's say you want to use user clicks in the last 5 minutes on a category of items, if you're serving an e-commerce site like Amazon. right? So you'd want to backfill that feature to generate training data, right? And then you extract labels. Like let's say you're serving a recommendation model, the label would be click. So did the user click or purchase? Right? And then you put those two things together and generate training data, right? That's a label join. And once you are okay with the trained model, you want to serve features. So you want to refresh features online, either through real-time pipelines or in a batch fashion, and then you serve them for inference. Right. So this is roughly what I'm talking about when I say feature platform. And last but not the least, we also want to log all the features that are being served for two purposes. So if a feature is already online and if you log it for enough time, there is no need to recompute and re-backfill it. So feature logging is a dual of like feature backfill. So you can either backfill from raw data or like use the logged feature data. And once a feature is fairly stable, there is like no need to backfill it. You can just like derive it from logs. Right. So the goals of feature platform, the first one is management. So what I mean by that is there is one unified API to drive all the red arrows that I was talking about. Right. And that also to manage feature lifecycle. So how do you author and how do you release? How do you change a feature? How do you add a feature to your feature set? All of that like goes into authoring and release. And the last but not the least thing is feature observability. So in the previous diagram, I didn't like show any box or an arrow related to any feature observability because it is cross-cutting. So at every transformation step, we need to understand what's the input data like, what's the output data like, and we need to use that to guide us in like what features to choose or if the input data is good enough or not. So there is roughly 3 pillars of feature observability. First one is training data quality. So you do the feature backfill or get it from logs, get some labels and join them and create a training set. You want to know if this data has coverage, if the distributions look good, or if there is correlation between any two things so that you can reduce the size of your feature set. So all of that comes under training data quality. This all happens before you even serve an inference request. And the next thing is feature drift. So once you begin serving inference requests, what happens over time is the data changes or there is issues upstream from the data sources that feed data into features. And as that those pipelines keep changing and as the real world data distribution keeps changing, you want to make sure that your model understands the new data. If it doesn't, you want to know upfront that there is drift in features. Right. And the last thing is online offline consistency. So before I explain what that is, I would just want to say that it's one of the biggest reasons why machine learning projects fail, which is that you train a model, it performs wonderfully offline, right? And once you begin serving it online and observing performance, it doesn't match up, and that kills a lot of machine learning projects. It's like you spend a ton of effort into doing a lot of work offline, and when you like try to use it online, it just does not materialize. So what causes that problem is that the data that you have trained with offline and the data that you're using online are different. So one thing that we want to guarantee here is that the data that is offline and online are both consistent. They're coming from the same distributions, using the same computational logic in both places. Right. So let's talk about the API. Right. There is a lot of moving parts in that flywheel, and we want to simplify all of this for the user essentially. And one way to do that is to provide a powerful API that is simple to use and familiar, right? So one principle behind Zipline API, I'm going to show you like what the API actually looks like. But the guiding principle is that we want to build these Lego blocks, give you the Lego blocks so that you can assemble your feature pipelines however you want to very easily. All right. So by power, I mean a few things. So there is no real understanding of the source type. We'll see what kind of sources exist, but you might be familiar with the star schemas, fact tables or dim tables, or like event data or like database snapshots. There is various kinds of data sources. There is change data too. All right. Those are not very explicitly modeled in relational algebra or like in SQL. So what we want to do is add those concepts as first-class citizens. So you can just say, okay, this is a database snapshot, or this are change data, or this is just events, right? And we can use that to derive features for you, right? We have different types. I'll like show you examples later on. And the next building block is group by. So this is the thing that actually does the computation. It takes your raw data, understands the source type, you can express filtering and transformation here, and specify aggregation, right? So the aggregation inside group by is a bit more powerful than what SQL supports. We support time windowing. And the big reason here is that time is not a first-class citizen in SQL. If there are two relations, and if you are trying to say that this relation and that relation have a single timeline, right? You can order the events based on that timeline. That is really not a concept that SQL understands. Right? So that's why we have to extend it to make it powerful enough for feature engineering. Right? And the last one is join. So because we know that different relations can have the same timeline, we can do a temporal join or a point in time join. So you can get feature values at various historical points in time. And then there is the last concept is like staging query. So we are going to go into a bit more detail on like one of the more complex concepts. But the last one is staging query. You can put arbitrary ETL queries into this concept, into this API, and it will execute that for you. One downside is that this will not be real time. This will not be point in time correct when you try to batch. This will only be batch correct. Right. So you only use this when the complexity of what you want to express is beyond what group by or join can handle. Right. So the final goal is computation. We want to support two models, log and weight versus backfill. Log and weight is like when you first begin a dummy inference of sorts. So you don't use the feature, but you're serving it online and logging it. And you wait for enough data to work in it. So if your business is seasonal, you cannot really afford to do this. You'll have to like wait for a year to accumulate enough data to train a good model that handles seasonality. The other one is backfill. So given that you have all the raw data already, like if you have all the raw data in your warehouse already, you can derive all the features in history without having to wait. Right. And the next goal is real-time features. So real-time features are extremely powerful in different areas like customer support, search recommendations, fraud detection. They're just like have been super useful and super important for a lot of modeling use cases. And it's one of the core goals of Chronon to support this as a first-class system. Right. It's also one of the hardest system problems in ML. Like we're asking data scientists to write stream processing systems, work with storage engines, which is definitely not the right fit. We want to abstract that away from data scientists and like help them focus just on the modeling part and feature engineering. Right. So this is hard because what I said earlier, you need to figure out stream processing, scale batch processing, work with storage and latency optimization. All of this is a burden that we want to like incorporate into the feature engineering platform and like abstract away from data scientists. Right. So non-goals of feature platform. So feature platform doesn't do model training or inference. That's a model management platform. Something like MLflow is a good example. And this system, although it has been used for generating business reports and like all other non-ML style use cases, but it's not really suitable for interactive report generation kind of use case or business intelligence kind of use cases. So what I'm talking about is that there is a divide in processing engines, right? If you might have heard of Spark and ClickHouse or Druid or like all this other stuff. So Spark is really for scaling over a large amount of data. And ClickHouse is like you take a small amount of data, but you try to get the results very quickly. Spark is slower, but much more scalable. ClickHouse is a lot faster, but not as scalable. Right. So we are more in the Spark camp. You know what features you want to compute, you just express them, and you're okay with waiting for hours for those features to be backfilled. Right. Now, that's what I mean by static usage. It's that you can like write and wait for a while instead of like trying to use it interactively. So those are the two like big non-goals of Chronon. Right. So requirements. So we have basically 5 systems here that we build Chronon on top of. First one is Kafka, condense all your events, and Hive or any other batch catalog. And then you have Spark, which can run the computation. So Zipline expresses all the algorithms that it uses to compute features as Spark topology, as Spark jobs. So you need a Spark cluster essentially that can talk to Hive or Kafka. Right. And the last 2 things are like, first thing is like key value store. To serve online inferences, you need to get your own key value store. It can be anything like Cassandra, HBase, Redis, it's just an API from Chronon point of view. As long as you implement the get, put, bulk put API, you can use any key value store. Right. And the last thing is Airflow or any scheduler that can schedule pipelines automatically. So we have an implementation that works with this particular setup. So now going a bit deeper into the problem statement. So let's say you're trying to recommend items on something like Amazon, right? And you have certain users, and at certain timestamps, we are like looking for features for these users. Right. And one of the features, let's say, is view count of a user in the last 5 hours, so whether this user has been active or not. Right. So there is a view stream data. It comes in as events through Kafka, lands in Hive somewhere. Right. And the next feature is average rating of an item in the last 90 days. So the previous feature was about the user. This feature is about the item. Right, we want to know what is the most recent or like recentish rating of an item, because we don't care like what is the rating a couple of years ago. Right, and just for the sake of this argument, assume that ratings is a database table, so that people come in, write their ratings, give a number rating also, and that can change over time. People can come and update that rating. So as those updates happen, we still want to like maintain this view of average rating in the last 90 days. So what Zipline needs to do offline is look at that source data and enrich the input, enrich your list of like user ID and timestamps with all the features, right? And online, it's the same thing. We need to produce the same values. So if you were to ask for Alice's features at this point in time, you need to respond with the results. So that is essentially the simplified problem statement. Right now, just to visualize what's happening with the source data, right? There is a timeline, and you want to like make a prediction at a point in time. So going back, this is the timeline, right? This timeline is represented as this timestamp column. Right. Now we have a label at a later point in time, which tells us if Alice made a purchase or not. Right. And then there is 2 data sources. There is a view source, and then there is a rating source. And we want to compute the windowed aggregation of either the view or the rating. Right. And at another point in time, we want to like make sure we are refreshing the features and creating newer or fresher features to power the recommendations. Right. And what needs to happen is that we need to backfill first. We need to create this training data first before we can do any of these other things, right? Either we log these and wait, or we backfill these things. So that's where like backfill becomes really crucial. We need to generate this view before we actually begin serving. But serving is useful to like show you how to think about the problem. All right. So yeah, the example is an e-commerce platform. And just to expand the example a little bit, we are counting item use of a user in the last 5 hours. So this is coming from item use stream. So the underlying things are basically parameters, right? Similarly, average rating of an item in the last 90 days from ratings table. So here count or average are aggregation operations. The inputs are item use or ratings, right? And the key is either user or item. And aggregation window is like how many days or how many hours in the past you want to gather the data from. Right. So these are essentially the parameters for group by. We talked about the group by concept, right? So we can give these as the inputs to the group by, and we'll figure out how to generate the stream processing jobs, how to generate the backfill jobs, how to serve these features in low latency. Right? All of that is powered by this configuration essentially. Right? And you can also toggle accuracy. So you can choose to enable real-time accuracy, power it through event streams like Kafka. Or if you don't have the Kafka stream and if you just have high tables, you can use daily accuracy. Right. So going a bit deeper into data sources, I'm just going to lay out a typical setup of where data comes from, how it like flows through various systems in the company. So you have a service fleet that serves application traffic. So you go to Amazon.com, some services serving like your requests. Right. And there is a production database, so which powers those requests. So Amazon is pulling data for items about you and surfacing it through the browser. Right. That's coming from the production database. Now, this data goes into an event stream from the service. So your clicks, your views, everything like goes into event stream and even gets accumulated in the offline data store like Hive. Right. And similarly, the production database gets its changes streamed through the event stream and it gets captured offline. And additionally, like most companies have this snapshotting mechanism where like at the end of the day, every day you take a snapshot of the database table, right? And then there is other kinds of data, which is derived data. They don't have any real-time or like Kafka component. They're just data Hive tables that get materialized every day through other processes. Then there is media. Media is things like images or audio or video. Right. So there is essentially groups of sources which contain the same data. The event stream and event log obviously contain the same data. And the change stream and the database snapshot and the change log, they also all contain equivalent data. So that makes a source. A source in Cronon is not just a single box here. It is a group of these data elements that represent the same data artifact. Right. And lastly, we have derived data. So this could be your like fact tables or dim tables that are computed by other teams. Right. And then there is media. So media is audio, video kind of stuff. It doesn't need explicit support from Cronon. Right. You probably want to generate embeddings off of this media data, and you can use Cronon to manage the embeddings. But we explicitly like don't operate on media data. Right. So there is, so if you remember, there is two or three kinds of data sources essentially. The first one is events. So it's clicks, views, etc., or like bank transactions, things like that. And the way to determine if your data source is event or not is that if the partition in Hive contains only the events that happen that day. So each partition only contains events happening during that day. All right. So fact sources are basically event sources too. So facts also are model data, but dim sources are not events. All right. So we can get point in time correctness just with this Hive data. So you can say any feature based on this data at any point in time is computable just using this. Right. And if you want to serve online, you also need a Kafka topic, basically. Here is a simple example. I won't spend too much time on this, but we are basically, it follows that scheme I was mentioning. So 920 has only 920's data, and they all have a notion of a timestamp. This is pretty important. So this is what we use to roll back features to different points in time. Right. And similarly, the other thing is entities. So this essentially is DB snapshot or DIM tables. You can use tools like Scoop to populate DB snapshots, or you can use. What is special about this is that we can also support change data capture. So if you are capturing change data through bin logs, you can use Chronon to roll back your database table to a specific point in time and derive features on top. Right? You can use things like Debezium, which runs on top of Kafka to do this. Right. So we get point in time accuracy for this data by using the snapshots and the mutations. Right. And we also generate those real-time refreshed views using the snapshot table and mutation table. But the key thing is that, you know, if you have CDC, you get point in time correctness. If you don't have CDC, it's going to be daily correct. Right. So here is an example. So we have a snapshot of data, basically of reviews, at a particular date, and at the next date we have like another snapshot, and basically there are some mutations to this table so that it became this table. So these are the mutations. So it says this is the old version and this is a new version. So
Nikhil, we're kind of run out of time, so can you run through? It's okay, just kind of run through the rest.
Yeah, so I think those are the important
points. Maybe skip the code examples, unless you want to go through those briefly.
Yeah, I'll just maybe show the code examples and then stop. Right. So here is what a group by definition.
You can press slideshow actually, just to make it big. So yeah.
You can express your filtering and transformation logic as Spark SQL statements. We think Spark SQL is like extremely powerful, so there's no need to reinvent the wheel here. And we capture those different elements in a single event source. And you can specify keys and windows and aggregations. So this is like how you declaratively specify. And this generates three things: the backfills. So backfill is like training data for offline training, and online serving features. So it will expose an endpoint where you can fetch these things in real time. And lastly, the data quality metrics for the features that are being pulled from Google. Right. So going down to the architecture, right? So here is what it roughly looks like. You write your Python code as like a config and use this compile.py to generate a compiled version of this thing that the data pipelines can use to generate all the downstream jobs. Right. So there are like 4 kinds of jobs essentially. There is backfill, quality, batch refresh, and streaming refresh. Right. And the client basically is consuming from key value store. And one of the big goals here is to reduce the latency to be sub 10 milliseconds for each of the inference requests. So all of this is on Spark and Airflow. This is the rough architecture of Chrono. I'm going to stop here and maybe take questions if you have any.
Well, I think we're out of time for questions, Nikhil. But but questions can continue on Slack, and there's questions there. Everything will be shared afterwards, folks. So we'll get the slides as well out there. Thanks a million, Nikhil, and you'll be back for the panel as well later, so we can continue some of this discussion on the panel. Okay, so next speaker is Sinan Ozdemir, and Sinan is a manning author on feature engineering, and he's going to talk today about fighting against marketplace scams using community-driven AI. Sinan is also the founder and CTO of Shiba, who are creating a next-generation community marketplace for physical and digital goods, and he's a former lecturer in data science at Johns Hopkins University, as well as author of books. Sinan, are you here? Can you hear me? Can we hear you?
I'm here.
Brilliant. Brilliant. We can try and share your screen, see if that works well.
Yeah, absolutely.
Looks
How does that look?
We're good. We're good. So the floor is yours. Go ahead.
Excellent. Thanks so much. Go ahead and start my stopwatch. All right. Welcome. Good morning, good afternoon, good evening, wherever you might be. Thanks for tuning in. Jim, I do have the one minor correction for you. It is the Johns Hopkins University, and unfortunately, they beat that into your head so much. I have to correct everybody who does it. But you know,
I actually said that wrong my whole life.
No, it's just a little tease. I get it all the time. So Today, as Jim mentioned, I would like to talk to you about fighting marketplace scams using community-driven AI. And kind of the story under the story I would like to tell you all today is how people, individuals, entrepreneurs, in my case, think about problems they see in the world in terms of data, and then convert those problems into usable data, into usable pipelines, into potential solutions to those problems. So you can think of this entire talk as one big case study in how feature engineering and feature stores are used to solve problems that people see out in the world. So let me first introduce myself. My name is Sinan Ozdemer. I am many things. I am an author. I am a founder, a former theoretical mathematician, current machine learning engineer, but I'm also a teacher and an art collector and an art lover. So among these things, what is most relevant today is I started a company back in 2014, went through YC, an AI company, conversational AI, fun stuff, my field, we exited. And during COVID, my co-founder and I got into collecting art and also in particular, NFTs during the big boom. So I also wanted to talk about how that pairs with my love of feature engineering. As you can see here, my cat Euclid is posing next to the batch of my most recent Manning book that Jim referenced, the Feature Engineering Book Camp. So to back up a little briefly, we all think this is probably pretty familiar to most people. The modern ML engineering tends to follow this kind of flow where we acquire data, we do labeling and feature engineering, experimentation, model training, deployment. There's some form of steady state. And then during that steady state, we're monitoring for drift detection, and then all of that loops on itself. I'm sure we'll see this graph or flow in some form many times today. But I would like to zoom in a little bit on the feature engineering aspect of it. Now, to be lazy and borrow from my own book, I like to break down feature engineering into four smaller umbrella terms, where feature understanding, structuring, optimization, and evaluation, which all flow into how do you collect data from disparate data sources or potentially disparate data sources and understand them, structure them, optimize them, and evaluate them, all for the, in most cases, purpose for optimizing some machine learning pipeline. Now, again, we can talk about how all of this will work in production, in experimentation phase and training phase, but most people tend to think about feature engineering as something that just, quote, has to be done, or just, well, it's whatever makes the models happy and not error out. But when I think about feature engineering and the fact that I've written 2 books on it because I love it so much, I think about a few things. A majority of data scientists' time is spent working on the actual data itself rather than the models. Now, this is not really news to most people who work in the field. There's the running joke that 80% of time is spent cleaning data rather than building your models. And that's true for a reason and to an extent. But it's one of the reasons we should be working on data as much as, if not more than working on models, is most boosts in machine learning performance are often attributed to feature engineering over model tuning. And I think, and again, anyone who's ever worked in the field would very likely agree with that statement, that your biggest boosts in your gains, in your performance, are mostly attributed to what you did to your data, whether it's getting data from a cleaner source, optimizing it yourself, a new text vectorization algorithm that you've discovered, whatever it might be for your particular field. Those often lead to the best boosts in model performance rather than hitting your head against the wall doing model tuning. Another reason is that bias in machine learning pipelines, which is something I lecture on quite often, is often best mitigated at the data phase, in the pre-processing phase of model training. And more so than not in the last 5 years, or last decade, I would say, more and more people are paying attention to bias and fairness in machine learning pipelines, as they should. And part of my thinking on feature engineering is it is the perfect time to recognize and mitigate such biases, which, again, so much so it's an entire chapter in my new book. Now, at the end of the day, feature engineering is often how we turn unusable data into useful and explainable data. Now, let's tie this back all into the topic of today is we are no strangers to fraud as a species and a society, right? You know, we all have a story of either ourselves or someone you know who has been tricked or duped or bamboozled in some physical or perhaps even a digital marketplace acquiring digital assets. Now, all these marketplaces are fraught with fraud. There are plenty of news articles where you can bring up people who are talking about massive scams in physical marketplaces. Facebook marketplaces now being one of the biggest marketplaces out there in the globe, and how scammers are using that to target people everywhere, not just in the US or in the UK or wherever the marketplace is settled. Now, even more so, in digital marketplaces, and when I say that, I mean mostly in the sale and resale of digital assets, in most cases NFTs, they are especially full of fraud. Most bad articles you see about NFT marketplaces and scams talk about how it's just so many. So much so that in the biggest marketplace for NFTs, OpenSea, they admit that 80% of the NFTs on their platform are spam or scam or fraud. So as someone who frankly loves the space of collectibles, both physical and digital, you can see at my walls, I have everything ranging from the centuries-old oil paintings to a KAWS figurine, contemporary, to a modern sculpture right up just off screen. This is and I can show you my wallet if you're so interested, but this is a field that I really care about. And so it's a field that I want to understand. So this is the feature understand what makes a scam or a spam happen in such a marketplace or in such communities, which we'll talk about how we're going to get most of our features, not necessarily from a marketplace, but from communities of people who also care about this, and then use that data to feed back into it. So let's see that. So before we do that, just to kind of zoom in on why I will be talking about more digital than physical. Physical marketplace scams is kind of what most people think about. It's mostly secondary market where people are reselling goods to each other, and they range from mislabeling items like this is an iPhone 14 when they actually give you an iPhone 10, all the way to being robbed at gunpoint. So there's a large spectrum of the kinds of scams and fraud that can happen on physical marketplaces for physical goods. Digital goods, they're often less physically threatening to yourself, to your body, but they're easier to conduct at scale, which is why marketplaces like OpenSea see 80% of their assets being spam, whereas it's not even near that for physical marketplaces, but that's the trade-off, volume versus the severity of the actual fraud. Now, if you're not familiar with NFTs, and in particular NFT communities, they tend to thrive on a platform called Discord, which is like Slack, but originally was for video gamers to chat and talk to each other, but was kind of adopted by the NFT community. And this is how most NFT communities, frankly, all major NFT communities build their base on Discord or something homegrown themselves. And Discord, most often, are public and open for anyone to join. So this is kind of where our data story begins, because to build a community-driven AI, you have to go to the source of your data, the community. So here I'm just showing two Discord communities for two pretty big projects that I collect, World of Women and VFriends. So in each of these Discords, they have some form of a way to let the community tell them about potential scams. Usually that comes in some channel about reporting scams or scam alert or what have you. But it's so ubiquitous that any NFT community you join will often have, of the three main channels they have, some general chat for people, some announcements to tell the community about updates. And right there next to both of those very important things are scam alerts, because they know this happens all of the time. So there's community-driven vigilance, and that vigilance is going to help us transform it into machine learning pipelines. These Discord communities are very proactive to alert their fellow NFT lovers about these potential scams. which is good for us because that means data is constantly flowing in the form of free text, which, for NLP experts, that's obviously what we want. These free texts are flowing freely in these Discord communities, just waiting to be ingested. They will also negatively react to posts that they think are scams. So in Discord, you're allowed to react to any message, just like in Slack with emojis, and most people will put siren emojis or thumbs down emojis when they discover some kind of a scam or feel like someone is being spammy in their behavior. The point is, communities act as their own sheriff and therefore can provide the data to fight these scams at scale. This is useful for us who are building a community-driven marketplace to understand how Discord communities think and act on scams to help us understand how we can automate it. Quick differentiation between spam and scam. Scams are intentionally fraudulent messages who are generally designed to steal your money or assets. Spam are just messages designed to get your attention. They can be scam, but spam messages could also just be someone really excited about their own project and just telling the world about it in an albeit annoying way, but technically not fraudulent way. We'll be focusing more on scams just because they are more dangerous, obviously, but we'll see how they're in a way linked. Because the first case study is my own Twitter. So as of today, this was a few days ago, I get targeted with scams at least once a week. And they tend to, recently at least, look like this. And I'll talk about why I said recently in a moment. They'll look something like this, where some Twitter user will tweet something about a whitelist, which is what WL means, and then they'll mention like a dozen people and with a link to what seems like a legitimate website for some NFT project. And in this case, another popular project I'm involved with, Alien Friends. Now, because I am a part of a community in Discord for Alien Friends, as soon as I saw this, I, to be frank, knew it was a scam, but I always like to check my sources. So the first thing I did was go to Discord and check if this was already reported, and it was. So this exact scam was already reported by someone in the report scams channel telling us about the scam. So it kind of confirms the suspicion that when scams happen, it is often important to check the community to see if it's already been reported. Now, me, the data scientist, takes it one step lower and says, well, how would I know without actually checking the scams site or the scams channel? Well, in this case, there were a few dead giveaways, and not to put this bot user on blast, but this person is clearly fake. They have 0 following, 0 followers, and they joined Twitter in October, which is this month. So their account at the time of me getting the tweet was at most 8 days old. So young account, no following, no followers. This is clearly a fake account. And also, to go even one step further, the website and the Twitter handle they referenced was not an associated website with the project. So in that case, for a human at least, it was extremely easy to detect that this was a scam, or at least a very, very likely scam message. Now, breaking this down into features and what will eventually become in our be stored in our feature store, we're really talking about two entities: messages and actors. You have scam messages who are written by bad actors, and each of these are going to have a different set of features to maintain. Now, in these kinds of problems, it's easy to kind of catch yourself in a bit of a catch-22, where you could say, well, you're only a bad actor because you're sending scam messages. And this is a scam message because it was being sent by a bad actor. In my last case, I noted that the user was fake, and that was one of my primary reasons for thinking the message itself was scam. And you can kind of get yourself caught in this loop, and in a different way, you can design the problem in many ways. So when you're designing the problem to be machine usable, you have to define features that are generally independent of one another, but at least related on the entity level. So as an example here, if I'm trying to decide if someone is a bad actor, I could use features like the number of likely scam messages that they've sent, or the number total messages that they've sent, and use presumably a ratio between those two to understand whether or not the person themselves are just more likely to be a scam artist in general. I could also use more simple features like the account age or the number of followers, the number of friends, depending on where we're looking, but on Twitter, that would be the number of following, et cetera, et cetera. Now, the first feature, the number of likely scam messages, obviously refers to the other entity messages. So to understand whether or not a message is scam, I could use independent features of actor so as to avoid that loop from actor to messages, kind of confusing the problem even further. So for scam messages, it comes down to a data scientist, for the most part, to think about what kinds of features are going to be useful. And this is for thinking back to the feature engineering, we have understanding, optimization, structuring, and evaluation. Now we are discovering features, we are structuring them, we are optimizing them. We can think about the number of people who are mentioned in a tweet. In my case, there were at least a dozen people mentioned, not just me. Uses of common scam phrases. Now, this is a domain-specific problem for the most part. And for example, the WL I mentioned, or you've been whitelisted, is a very common phrase in NFT communities, telling someone that they are eligible to receive an NFT, and which gets people excited because they get their NFT. Counts of negative reactions in public spaces. This is an easy way to help us also label messages ourselves from the community. Or the person who's claiming to be the admin of a project very often, or one of those successful types of scams are people who are claiming to be the creator of the NFT project, because most, if not all of this is occurring online. Most people don't know what the creators of NFT projects look like. It's hard to Google them. They have some profile picture that is not actually their own face. So it's relatively easy to claim to be the admin of an NFT project and not actually be one. And that can happen privately in your direct messages. So to me, this comes down to having multiple feature drivers, meaning the number of times someone is mentioned in a tweet or uses of common scam phrases like you've been whitelisted tend to be more bag of words style features, right? The count of mentions or counts of these known phrases. These are simple bag of words features for those in the NLP field. We can go one step further and talk about negative reactions in a public space. Now, easily, this could be done, although tediously, this does exist as packages. You can get a dictionary of negative emojis. And one step deeper, to understand if someone is claiming to be the admin of a project, that's more of a semantic field that we would have for a raw text. This could be accomplished using some transformer-based model like BERT or GPT. We can use these large pre-trained language models, which is something I tend to specialize in, and understanding these semantically derived features, like, is this person pretending to be the admin of a project, yes or no? And these large semantic models can help us understand those at scale. So how do feature stores fit into all this? Well, feature stores are how we can create, define, and iterate on these features, because the goal is to discover the strongest possible community-driven features to build an AI that can detect these scams in real time. Centralized feature locations to make experimentations reporting easier, and things we'll likely hear a lot today, sharing features across our organization and monitoring these features over time to detect drift and skew. Speaking of skew, hindsight tends to be 20/20. Historical users and message data have already been reacted and reported, but that's not true for a message that was sent 2 minutes ago versus 2 years ago. So we can't necessarily rely on these time-reliant features like the number of reactions, the number of retweets, but we have to be more reliant on time-agnostic account age or message content. Now, age might sound like it is not time-agnostic, but the account age tends to scale linearly with time units, if you can believe it. So for that reason, I tend not to think of it as necessarily time-reliant because it's a simple linear scaling. Now, scams do drift, but they often tend to drift in more of a step function. Scammers will find a method that works and then stick to it. This was just literally yesterday. Someone tried a very similar scam with me for a fake Nickelodeon NFT that they thought I would like because I am a millennial in my 30s and I loved Hey Arnold as a kid. So I'm a good target, but clearly this person is also fake. So these things are continuously happening. These scams are constantly happening. So at Shiba, as we're building a community-driven marketplace for fine art collectibles, both physical and digital, it is imperative that we use this data to build this community-driven AI that can loop back on itself to drive out scammers and spammy behavior. This behavior is not just for detecting bad actors, but it's also for something a little bit more high level. So we get the speed and performance of a feature store and pre-trained language models, but we also get to use the opportunity to educate people on what constitutes a scam or spam and help them as they're writing a message to someone and tell them, hey, what you're writing looks like scam. And if you keep writing messages that look like scam, you are likely to get reported by either us or someone else. And if someone is genuinely not trying to sound like a scam, but for some reason are writing in that manner, it is a chance to educate people on how to message better in these kinds of marketplaces. Because at the end of the day, we deserve to shop in peace. And with use of feature engineering, feature stores, and community-driven AIs, we can at least strive for a world where no one gets to be scammed. And in the meantime, everyone should be vigilant. They should know what to look for, specifically in the domain that they are. If you're into NFTs, hopefully this was a little bit helpful in that regard. And if you see something, say something. Report these bad actors, because that is the data that will be used for AI companies like ours, in a way, to build these community-driven AIs to help drive out these scammers. So that's it. Thank you so much. My name was Sanan. And again, if you want to, please don't spam me. But this is my Twitter and my LinkedIn, and I'll be happy to take any questions now. And of course, I'll be on Slack afterwards.
Brilliant. Thanks a million, Sinan. That was a very fascinating talk. Sounds like there's a kind of a need for a public market space for features out there, not just for scamming, but in general. I think that. Yeah,
and I think the biggest, the hard thing about that is these features tend to change between domains, right? For NFTs, you talk about whitelisting is probably the most common term, but that would never be mentioned on Facebook Marketplace. So when you think about that kind of problem, and I have thought about that kind of problem, domain context becomes more imperative than most problems.
Brilliant. So we'll see. I think we're back for the panel, or maybe, I'm not sure if you're on the panel, but
I am.
Okay, brilliant. Thanks a million. And jump over Slack, see if there's more questions there. Okay, we're going to move on. So the next talk is by Aman Khan, and Aman is Group Product Manager at Arize AI, where he works on machine learning observability solutions. And prior to Arize, he worked at Spotify on their Jukebox feature store and the ML evaluation frameworks like Cruise prior to that. Aman, can you hear me?
I can hear you fine. Good to see you again, Jim.
Let me turn on my microphone so I can speak. So just try and share your screen and make sure that everything's working okay. And we are live, of course, folks. So it looks good. And then slideshow, and we're done. Everyone's using slides, Google Slides. Very interesting. Off you go.
Yeah. All right. Great to see all of you folks here. Very nice to be back with, of course, Featurestore.org and Hopsworks. So just a quick introduction, as Jim mentioned. My name's Aman. I'm a product manager at Arize. We're an ML observability platform. We'll talk a little bit about what that means. And a bit before that, I was actually at Spotify working on the Feature Store infrastructure and Feature Store API. So pretty familiar with the Feature Store space and challenges around, defining the difference between the data of the feature and versioning the transformations on that feature, the offline, online challenges, point in time joins and backfill. And what we're going to be talking about is actually once, you feel like you have the feature ready to go, once it's ready for production, what happens next? What happens when that feature is actually integrated into a model? And what are some of the downstream challenges that potentially your customers or yourself, if you're the producer of these features, might be facing that can actually undermine the value of that feature at the end of the day when it comes time for that feature to actually start being used, to start making inferences at scale? And that's really the core kind of challenge that we're focused on at Arize. And we'll start with actually kind of a high level. What are some of the problems with production ML? And just so we're all on the same page. And then from there, we'll start talking about this category around feature store monitoring and feature store observability And the ways that we actually assess and evaluate features to actually, surface up the insights of what are the problems that might be going on underneath the hood with either your model or the features and the data themselves. So kind of just talking about a high level, there are many steps that either your customers or if you're a model builder, you'd have to go through to actually get your model into production. There might be actually significant changes in how the feature is defined, be it you might have to rewrite potentially the logic of the feature to actually make it production ready for AtScale. The sad truth is that even after all of these steps, once your feature actually starts getting into the model that's in production, there could actually be some downstream challenges that due to the underlying nature of the world that the feature is operating in, that the world the model is operating in, that could be due to human behavior, things like sentiment changing. COVID is another big reason, of course, as well, that a lot of models were basically producing outputs and inferences that just weren't representative of the real world. And a lot of those issues actually fail silently. And that means that, business KPIs can be impacted. And then by the time that an issue actually shows up in the form of feature drift or performance drift, by then it's very quite difficult to actually troubleshoot and triage what the root cause of that failure was. And so really there are multiple steps here that kind of go into, actually correlating that business metric and the sort of business impact of a model, going back to the individual model performance, and then actually identifying the sort of root cause or slice that could be impacting that model performance the most. So not only are there a ton of challenges to get the feature and model into production, but the path after that is equally, if not more difficult as well. And so just to start with a little bit around the definition of what we're talking about with observability, we're not talking strictly about monitoring, but actually the underlying sort of understanding of how to fix your features and your model when things break. So, monitoring could be as simple as telling you, hey, there's an issue with this feature, but to actually go deeper and assess and evaluate, be it structured or unstructured data like embeddings, what the root cause of that issue is really what we kind of qualify as observability. And that's really what we're going to be talking about. So just to kind of summarize that back up, observability is just, the monitoring is sort of the tip of the iceberg, and observability is what gets you to that root cause. And for the most part, what I'm going to be talking about is going to be relatively at that sort of higher level of just concepts and themes. But to go any deeper on any of these subjects, I'll actually be dropping a link towards the end of the talk for you to actually sign up for Arize and sort of see, if this platform kind of meets your needs. And then we have a ton of documentation as well that can kind of go deeper on any of these subjects. So where does the feature store kind of fit into this whole thing, right? So, I mean, this is a feature store conference. We view feature stores in sort of the same level of importance as, say, your model store, as well as the inference store that we're kind of talking about, which is really once the feature is created, once you have that offline and online definition, you then kind of pass that on to the model for either for training or when it comes time for serving. So you have that notion of that feature, the definition of that feature, kind of passed along with the model, sort of underlying metadata of the model as well. So that could be what type the model is, what the sort of the architecture of that model is. And then when it comes time to serve those inferences online or in batch, that's where the inference store really starts to become valuable, because at that point, we then log the actuals associated with what happened in the real world and correlate and sort of actually join those along with the inferences that the model made and all of that underlying feature metadata and feature data itself as well, not just the metadata. And from there, that's when we really start getting to the value of observability and actually sort of slicing and dicing even further to show you value. So why does all of this matter? Well, at the end of the day, what we realized is that we actually went out and surveyed around, roughly about 1,000 companies or so and got data and found that when issues do occur, it takes roughly about a week for engineers that own those models to actually detect and fix the issue. And so to go deeper, roughly about 50% of engineers we spoke to said that they actually lack the tools to do this root cause analysis. And on top of that, the sort of end impact here is that businesses don't have visibility into their return on investment in machine learning, as well as when issues occur, how to kind of correlate that back to models. So that sort of stitches all of this together. At the end of the day, it impacts your business, it impacts your users. And so understanding what's going on underneath the hood is kind of critical to the feature store being successful in a production environment. So with that, let's jump into what I'm talking about when it comes to feature store monitoring. And there's really kind of three concepts I want to talk about, which are data quality, drift, and performance. And we'll kind of break down each of those as we go. So data quality, what do I mean by that? So data quality is really what you can imagine as sort of at the sort of highest level, at the top level. It's really the sort of pipeline issues that you might expect from the data itself. So when you set up a data pipeline, there are many things that could go wrong. And a couple of the common issues that we see right off the bat are missing data. So, let's say you have a model with 300 features. One of those features was the app open or not, hypothetically, in some sort of, batch serving model of, should we serve an ad or not? And in that case, because of connectivity issues, because of pipeline issues, because of database issues, you may not actually even realize that you're missing data. And in that sort of way, that's like the highest level problem, but there's many types of problems in that domain, from things like out of range violations. We might be getting data that's just not within the bounds that we expected it to even like type mismatches. All of these really get caught under this umbrella of data quality checks in production. And so the way that we kind of approach these issues is we really ingest at least at Arize, and when it comes to observability, the goal is to really kind of take all that data and profile it and look at what are the sort of common values that we would expect. What is the expected based on a good period of time for this data to look like? And from there, you actually set up monitors against all of those threshold values. So we actually have models underneath the hood producing these thresholds. And from there, you actually get kind of notified or pinged either through Slack or PagerDuty when any of these issues occur above the threshold. Let's say we're seeing more missing data than we expected it to, 1% of knowledge as opposed to 0.1%. That would then page you and alert you to go and check on the data quality of an underlying feature. So that's really, we kind of view this as, the sort of maintaining that contract between you as the model owner or the feature producer with your upstream data quality teams, where they're kind of responsible more for the logging pipelines and maintaining the quality and integrity of the data pipelines themselves. But that's just really kind of the start. That is sort of just at the highest level, is the data even good going into the model? One layer deeper than that is when we start getting into what we call drift, which is looking at the underlying distribution of that data and profiling that distribution of the data and seeing if that data or that distribution is changing over time. So let's say I have a reference distribution. In this case, it might be by production model for the last week. Really, it would be important to be notified if that reference distribution is significantly different from the baseline. Let's say that's either my training data set or it's my production data set from a week, maybe a month ago. If all of a sudden the environment that my model is operating in is markedly different, that's something I'd want to be notified of. So in this case, we kind of view data drift as one level deeper than the data quality of the pipelines themselves, and more along lines of a potential proxy metric for highlighting, perhaps a number of data quality issues that might be still underneath the hood, might be underneath the thresholds, but are causing this sort of change in distribution. Or it can also be a signifier or some sort of alerting to users that that your model might need to be retrained, that the environment that your model is operating in is now different than when your model was trained, or in production data, perhaps sentiment has changed. So drift is really kind of a bridge in a way of almost a proxy metric of, is this model operating in the same world than that we expect it to based on our offline or online understanding. So it's very common. We catch drift issues quite significantly, even at sort of what you'd expect to be top tier ML companies. And part of the reason for that is because understanding how to quantify drift is actually a pretty difficult statistics problem. And so there's a number of ways, we've surveyed and spoken to a number of teams. We have a number of customers that, look at, all of them have different kind of methods for evaluating drift. And really there for certain features, for certain metrics, there are certain approaches to evaluating drift that might be stronger than others. We found that generally PSI, which is Population Stability Index, is a pretty kind of good general approach to measuring and quantifying drift. However, there's a number of other approaches you can take. And really the trick here is to understand, based on the distribution and feature that you care about, what does drift mean in that case? And that's kind of hard to do just in the, sort of the highest level, like is this feature drifting or not, is a question we get a lot, even when we're evaluating models. And the answer to that is it really depends. It depends on the case. It depends on the performance of that model. And so that way we actually look at sort of this funnel of drift and data quality kind of leading ultimately to performance. And that's really what, at the end of the day, what matters. It's the performance of the model, the accuracy, precision, how you define if that model is performing correctly in sort of this environment, and then kind of working backwards to see, is drift a potential problem here, or is data quality an issue? And from there, you can start drawing correlations between those metrics and start understanding, what does drift mean in your model's case. Of course, even within our platform, we do, again, offer sort of those automatic thresholds for drift to get you started when you just get your features ingested around, just monitoring features. Let's say if I don't even, let's say in this case, if you're just responsible for the feature store, you don't have that access to the downstream performance data. That's still something that you could be alerted on, that the underlying distribution of your feature has changed. And that's something that you may want to notify your downstream, let's say 10, 20 data scientists, that they may want to look more closely at the performance of their model and see if there are any changes. And that may also be, a good proxy if you don't get actuals back in some cases, or the actuals take a very long time to return. Drift can sort of preempt some of the downstream performance issues that you might see. So we generally kind of view this as correlated. And I did notice a question come in, and I'll save a little bit of time at the end for questions in the next few minutes. And so really, that's really kind of the last sort of what we call pillar here is understanding explainability, fairness, and kind of tying that all together. And so when we kind of look at and view as explainability as, when it comes down to the feature and underlying feature slices themselves, how much are those features contributing to the model's overall performance? And kind of going one layer deeper than that, what is the relative sort of importance of these features to each other? And so really what these histograms are meant to kind of demonstrate on the right-hand side is, based on the volume of an underlying feature slice, which we define could be either a range, or if it's a categorical feature, it could be, in this case, different types of animals, something like this. Then you can actually see based on the impact of that feature based on the volume and contribution to the prediction. So that's really kind of how we view this explainability, and kind of going even one layer deeper than that. We've kind of identified that there's actually a way to sort of stack rank these slices based on that sort of overall impact on model performance. And that's usually a pretty good way to start burning down what are the feature slices, even if the overall feature looks good, that might be impacting the model performance the most, to go and kind of understand, am I missing data? Is this data different than what I trained the model on? And so that's really kind of the in a way kind of getting to the root cause of how much a feature slice is impacting a model's performance. And so just to kind of summarize that up, what we recommend when it comes to performance tracing is actually compare to something that compare to a reference distribution, so that you can monitor effectively. And then you can actually from there compare and break down the features by slice. So that can usually be a great way to troubleshoot and root cause. And from there, actually being able to look at points in time and compare these values. That's really the steps that we recommend following when it comes to identifying and kind of going deeper down the ML performance tracing workflow. And all of that has generally been around structured data. I'm going to briefly touch on unstructured data, or embeddings. And so, in the case of a feature store, many of these cases may also, many of these feature stores may also be housing unstructured data in the form of vectors, nearest neighbors vectors, or user vectors. And so what we recommend is, you do kind of take a similar approach where you want to monitor every embedding the same way you do with your features. You look at patterns of change. And then from there, what we actually enable is exporting out that the problem segments or problem cases here, where drift may be correlated back to a part of your unstructured data looking markedly different. And so we actually take the same approach, but what's maybe and sort of just kind of double clicking and sort of like what are embeddings. They're effectively just this mathematical representation of data from some vector space, and they could be either high dimensional or low dimensional vectors as well. And so in this case, if we take like a word embedding, like man is to woman, what king is to queen, from there you can actually visualize that vector space and actually be able to cluster around segments that might look markedly different than the training and production sort of distribution of this high or low dimensional vector space. And so in this case, what we're kind of showing is different colors correlating to different data sets, and then actually looking at outliers here for something like a text vector that represents sentiment of reviews. You'll see that actually a number might be clustered around great or didn't like it, but there might be a training in part of the training set that might look different, or even production data set in this case that might look different than the training data set, which is a different language than what we expected to sort of train the review model on. And so to actually visualize unstructured data is a whole nother challenge. It's actually one that we do enable in the product as well. We use a sort of a technique called UMAP, which actually takes these sort of vectors and actually compresses them down to a lower dimensional sort of visualization space. And so you can actually kind of view this in 3D and actually cluster different sort of data points within this unstructured data set, and then go and export those for your labeling. So we basically fundamentally we do take the same approach in our sort of structured data as we do in unstructured. It's just that the tools that you might utilize can look a little bit different. So kind of tying it all together, we touched a little bit on what is observability, how does the feature store fit into this sort of storyline, and then what are the different approaches that you might take to monitor features. And in summary, really what we're kind of getting at is just to stay focused on your customers and data science use cases. At the end of the day, the adoption of your feature store means that you want to make sure that the quality of the features that you're providing to downstream customers, or the quality of the features that you are in charge of managing, are as high quality as possible. And so it's imperative to actually monitor those features using ML observability as close as you can to the business case. And then that really helps you kind of hold your upstream teams accountable as well when there are issues that occur when it comes to third-party vendors or your upstream data pipelines, when that could be an issue with the feature, but it's actually root cause to a data quality issue, or just requires a model to be retrained. And then that really what we kind of sort of recommend is looking across data quality, drift, and performance metrics to perform that root cause analysis when issues do occur, because what we've seen is it's really just a matter of time, and having the right tools ready is what will make your feature store be prepared when it's ready, when it comes time to actually ship the feature in production. So that's a bit of a high level on what ML observability is and applying that towards the feature store. Welcome to sign up for a free version of Arize. You can sign up for a free account, start ingesting your features or ingesting your feature store as well and playing around. Feel free to give us feedback in our community Slack as well. But thank you so much for your time, and I'll be sticking around for any questions as well as the next panel.
Thank you a million, Aman. I think we have like maybe 1 minute. There's a question here. You can grab that one on Slack. I'm going to ask you a beginner's question because I'm a professor and I read up a bit. And in the literature, I read about statistical shifts, but I haven't read so much about drift. But our community seems to have adopted the term drift. Do you differentiate between drift and shift, or is there any difference between them?
Yeah, and that's sort of, I think, Jim, if I understand correctly, that kind of comes back to like some of the metrics that we were looking at of, PSI versus KL divergence. And I mean, at the end, at the sort of the highest level, it's what we're trying to represent is this distribution of data looks different than that distribution of data. And drift is sort of what we've kind of, I guess the community has sort of kind of coalesced around because of perhaps the selection of metrics used to evaluate that change in underlying distribution. And I think that it actually, and to maybe just go one layer deeper here and sort of, and I'll just show that list of metrics again. Some of those metrics are more useful than others depending on the distribution and on the feature itself. And so I think that in academia, there can be, you might be looking at populations differently, you might be looking at data sets differently. And that's why we have that checkbox around PSI. We found that generally, like the most general case for financial applications, for recommendation engines, for things of that nature, that generally ML, like production ML is used for, that's where that metric is most useful because of the nature of its similarities to KL and the sort of symmetric nature. And sort of like just kind of talking about that at a high level, it's the most general metric you could apply, but there might be more specific metrics depending on your distribution, either for shift or drift.
I kind of had this intuitive understanding that shift is, of course, like a one-time comparison of a source and a destination distribution, whereas drift is maybe a set of time windows over time where you're comparing its evolution. But maybe we need some new papers in the space to kind of clarify the terms a bit better. Okay, with that, I think we're going to move over to the panel. Thanks very much, Amma. There's a question. You can grab that question on Slack.
Okay.
And we're going to move on to the panel at this point. So I think if we can share, if Marianne can share the panel. So we have Patrick Liu-Tran, who's the CEO of Validio and co-founder of Validio. They're a data quality monitoring company. And they work with data quality, primarily with the modern data stack. So the Feature Store is, I would say, a more recent platform, of course, than the modern data stack. So it's possible, and maybe, Aman, you can correct me on this, whether the metrics stores and the data quality work that's being done on the data warehousing side is slightly ahead of where we are on the feature side. But anyway, it'll be interesting to hear the different perspectives on this. And we also have joining us Rekha Bachwani. And Rekha Bachwani is from Disney Streaming. And she is the director of machine learning engineering at Disney Streaming. And she drives the strategy for machine learning infrastructure and applications and engineering use cases. And I'm sure Disney have a ton of use cases there. She also has a PhD in computer science from Rutgers University. So for the panel, we have Patrick, who's the moderator, Rekha Bachwani from Disney. We have Nikhil from Airbnb from earlier. We have Sinan from Shiba and Aman from Arize. Welcome, Patrick. Are you there?
Thank you so much. Yes, I'm here. Really happy to be here.
Right.
Really exciting topic. And yes, so this session, we will focus on discussing data quality and feature stores. And as Jim explained, data quality is something that is close to heart, given what I do on a day-to-day basis at Validio. We build an end-to-end data quality platform with a modern data stack in mind. And I'm the CEO and one of the co-founders there. And this is a very interesting kind of, I've listened in a bit, and there will be a bit of repetition, but I assume that some people have not listened to all of the great talks before. So I'm gonna go back and ask some basics so everyone gets up to speed, and then we delve a bit deeper. But so I think the first thing that we need to define a bit is kind of what is data quality in a feature store context, because like outside the feature store context, we have the terminologies of data observability, data quality, and we have metadata checks, we have data lineage, we have checks on actual data on a data point and data set level. There's a lot of variation in terminologies, right? It is almost like AI, roughly 5-10 years ago in terms of diffusion of and confusion about the terminology. But Sinan, could you start by sharing kind of your definition of data quality in a feature store context? And I've taken a brief look at your book. It's really good, by the way.
Thank you. Oh, I appreciate that. I always appreciate that. Yeah, but you're right, because data quality, and I would even argue still today, AI can still have just a little bit of subjectivity and creative differences, to put it mildly. I guess when I think about data quality, thinking about both labels and features, I'll focus on features. I feel like for me, the biggest definition that kind of trounces everything else is quality of data should should map to a equitable and reasonable representation of some population. So if quality is high, that should also mean that you are accurately and equitably representing some population well. Because at the end of the day, when we're building these AI models, we are trying to work within some population. And if we're not representing the population well, our quality is likely poor in our data. For me, that is not the only definition I have. I could come up with imputation of missing values, blah, blah, blah. But for me, if quality is high, then I am accurately representing some population well. That, for me, that's the biggest definition.
Cool. And so then we focus a lot on the kind of data drift or shift concept, right? That Jim and you, Aman, discussed a bit right before this panel. And when you look at the kind of data quality and data observability more generally, you see these things such as schema changes, data freshness, data completeness, which many times comes down to like, when was the place you store your data most recently updated, how many rows were ingested, these type of things. And then you also have kind of, misformatted data points on a data point level. You have a zip code that is misformatted. You might have dates that are in the future or too much back in time. So Rekha, would you agree with Sinan's definition of focusing quite a lot on the data drift and shift in a feature store context, or would you expand it more broadly?
So I would add on to what Sinan said, right? Quality, to me, data quality is a necessary condition. If you don't have high quality data, the chances of you getting useful insights are pretty low, or even if you get them, there is going to be low confidence in them. Drift and shift to me are more specific phenomenon. They may emanate from data quality issues, but that might not necessarily be the case. You could have a very high quality data, but your user behavior or the trends are shifting over a period of time. And in that sense, you may continuously have high quality data. You just need to adapt to the ever evolving change in the world itself, or the reality that is being represented by the data. So yeah, that's how I would categorize them. And to answer, or maybe like to me, the difference between shift and drift is more gradual, and it could be ever so changes in the shape of the data, not the fundamental assumptions or the trends that are being represented. Versus when I say here shift, to me there is a shift in the trend, and it could be more like a step function or a little more drastic than what would be represented by drift.
Cool. And we can go back to the drift and shift discussion in a bit. It's very, very interesting because and the underlying potential root causes for a drift and a shift. Because sometimes we say that kind of if the data describes a population well, but sometimes, as we saw in many cases during COVID, the behavior of the population changed, right? And it might be more towards a shift with your definition, Rekha, compared to a drift. It's representing the underlying population very well, but the history is not then in that case, right? But let's get back to that in a bit, because I'm sure we can stick around and discuss those terminologies forever. But Nikhil, I'm quite interested in kind of your experience at Airbnb and kind of how you have solved for data quality in the feature store. If you could elaborate a bit on that.
Yeah, so we see three big areas when it comes to data quality, especially for features. The first one is training data quality. So I have produced some training data from offline warehouse through some high tables, and I'm trying to understand the training data set. Right. So the point of this exercise is to see if the data has enough coverage. What kind of normalization should we do? What's the distribution of categorical versus numerical features within the data? What are the correlations? That kind of stuff. a good starting point for like looking at the details is this paper from Amazon called Differential Data Validation. We kind of like are very inspired by that to summarize tables. Essentially, it's not very specific to features. It's a bit more general, but it has a lot more depth into like what kind of metrics we should consider for it. So that is one area. The second one is serving data quality. So the main thing here is that I want my prediction distribution to be very stable, right? When it's suddenly changing, that means that something is wrong with the features, right? That's the only input, like features produces prediction. So the point of this is that, let's say I notice a change in prediction distribution. And by that, I mean, if predictions are numerical, for example, right? So you can measure what's called a KS distance or Kolmogorov-Smirnov distance to tell if the distributions are like far apart or not, right? And then based on that, we can like trigger an alert. And after an alert goes to like a user or a model owner, they'll probably look into which features are changing that have caused this thing, right? So that is the rough workflow, but the purpose of this is that this needs to trigger alerts in real time. So we have streaming pipelines that like consume data and compute these distributions, compute the distances, and push it out somewhere so that the alerting system can consume. Right. And the last thing is online-offline consistency. So one interesting thing I have heard in this context is that both online and offline computation can be wrong, but if they're equally wrong, the model will still compensate for the wrongness. Like let's say you hard-coded some dollar to pound conversion as like 2 instead of 1 or something, right? So the model doesn't care that you have used the wrong multiplier, like online and offline, as long as it is same. It will do the normalization. Right? So that is the real difference. So if we are guaranteeing that the logic and the data that is being produced for training and serving is same, then we can assume that the performance will translate. So if you see some performance of the model offline, and then if you try to put it online, if you have this guarantee from the base feature store or feature platform, you can very confidently turn on the flags, begin serving these models. So that is also similar to what I talked about before, that KS distance and whatnot. But the difference is that we are like doing first a side-by-side comparison of logged and backfill data and computing that distance. But in the older drift case, we are computing distance between distributions already. So there are no distributions here. We are like looking at individual points and summarizing it. Yeah. That is roughly the 3 areas: training data quality, online serving data quality, and online-offline consistency. Right? Online serving data quality is like where the drift comes into play.
Cool, very cool. So when it comes to like these different parts, I mean, would it be possible to mention a bit when you look at the training data quality in the first step, you referenced a paper about so would it be fair to say that it is a set of kind of checks that you do on that training data? Could you mention a few of those metrics that you look at?
Yeah, so it starts from simple metrics like what's the coverage? Coverage is like how much of this is null, how much of this is not. Then the next thing is detecting if some feature is numerical or categorical. Right, so you do that using approx unique count basically, and see if there is very high cardinality, and if it is a number, you say this is numerical. If it's low cardinality and if it's a number, it's categorical. If it is a string, with very low cardinality, it is categorical. Now, once you identify that something is numerical or categorical, you can specialize like additional metrics. So for numerical stuff, you compute distributions using approx percentiles, or like there is this sketching algorithm called KLL sketch. You can use that to summarize a distribution very efficiently. And for categorical stuff, you probably can just collect map count or histogram if the cardinality is very low. And if you want to identify skew, right, in string but not categorical features or like continuous stuff. You can use heavy hitter detection. So there is like various algorithms that you can employ to understand the problem. So roughly there is like coverage, skewness, there is distributions, histograms. That is column level statistics, right? Then there is cross column statistics. So what is the correlation between different columns? What is the entropy gain between different columns? Right. So these are all like laid out in the paper actually. So I think like if someone wants to like look into the, I'll like link that in the Slack chat also. But there's also a library like AWS folks release this library called DQ, DEEQU, that contains like most of these things that I talked about.
Very cool. And I mean, when I hear these things, it sounds like very similar to outside of feature store context, right? These are very similar to the things you would look at in general. Yeah.
So I think the cross-column stuff like correlation and entropy gain is kind of what specializes it to features. But the big difference is the context in which you apply. Like most of the existing open source work is very focused on offline data sets. There's a Hive table, summarize it for me, right? And it doesn't really translate to the streaming context. Like you need to identify drift in streaming and online-offline consistency, where you're comparing two data sets, not just a single data set summary, but you have two data sets that are supposed to be same. So you're trying to understand what's the difference between those techniques. So yeah, there is like some work that needs to be like made public domain, I think. But it's based on very established ideas of comparing distributions and computing distributions.
Yeah, thank you so much for that. And Aman, now I know you just talked about it, but still, I think there are a few people who just tuned in. So at Arize, you're kind of building this machine learning observability platform. So could you just give us the kind of explanation of how you help your customers solve for data quality in a feature store context?
Totally. And yeah, I was, as Nikhil was talking, I was like holding myself back. I'm like, yes, I completely agree. And also there's a layer deeper here. I think that Arize is kind of working to solve. So just kind of backing up a bit as well, like what matters at the end of the day, it's that your model or that your downstream models, if you're the feature store owner, is producing inferences in a way that is overall kind of good. I mean, just frankly good, right? Like if the inferences are bad based on either a reference data set or your actuals of what actually happened in reality, or your overall business metrics, you want to be alerted based on that. And so we kind of view data quality as part of this journey or this funnel of actually catching model related issues, model issues, performance issues downstream. And my background was in engineering. I started as catching actually perception computer vision engineers for a software and car company. And from there, we actually had to look at individual cases of where either data quality was bad or the prediction was incorrect. But at the end of the day, what we cared about was that metric of, are we making the right inferences? Are we making the right predictions with these models? And so my sort of take here is like, where does Arize fit into feature store monitoring? Is generally observability is as close as you can get to that business value and that model performance. That's how you tie back to the value of your feature, as well as does the data quality or the underlying drift of the feature really matter, right? And so in a way, we as Nikhil was kind of saying, this third pillar here of like, if your reference distribution and your production data set, the feature is incorrect or drifting in some direction where the model is still, like the inferences still compensate, then in a way you're actually pointing to, well, this feature may not actually have huge impact, or the drift of the feature doesn't have huge impact on the ultimate performance. And so correlating that is really it's a tough problem. It would either require you to write a lot of pretty expensive queries in your offline and online stores and join them with your predictions and actuals if you have them. And so we've thought, why not package that into a solution? And so that's really what we do, is monitoring and observability that sits on top of your feature store and can either look at just if you already have that context somewhere else in in a Tableau dashboard or another dashboard, you could pull that out. Or if it's, if you have the inferences and actuals, you can actually join them back into our platform and perform that either performance metric level analysis, drift analysis on the feature, and then the underlying data quality and hold those, those pipelines accountable as well.
Very clear. Thank you so much. And like when I hear about these things, I mean, coming from the more kind of general data quality space, when you look at, it could be streams, it could be, object stores, buckets with data, it could be warehouses. Rekha, based on your experience, kind of how would you say that data quality in a feature store context differs from kind of data quality outside the feature store context? We heard a bit regarding the kind of more multivariate thing and so on, but there's also a lot of these things, kind of distributions, shifts and drifts also matters regardless of feature store context or not, right? So in your daily work, how do you see the difference, if there is any?
So I would say in some situations, there isn't much of a difference. The data quality provided by the downstream, like base data warehouse, might suffice. But for certain features or certain elements, essentially, you probably want additional data quality checks, right? So one would be around the distribution or the cardinality. So if you have a categorical feature or something, you want to understand, like, okay, usually have 5 categories. For whatever reason, today I'm only seeing 3 categories. It might be okay, but you probably want some additional checks to ensure like those kind of value added or very context driven quality checks. The other would be between, like, especially in our case where we have offline and online feature store, different features are landing at different cadences. So you probably want to have some alerts or some checks around making sure that the cadence is not too off for any of the features, because there is downstream dependencies that would get affected, even if the values are accurate. But if they're late arriving or if the cadence has been affected, you probably want to know. So those would be some more like very specific to the context sort of a thing. Also for streaming features, it's at a single profile level. So sort of distribution may or may not matter. You may need like something very point in time, very specific checks, if any, depending on the features you have.
Cool. Thank you so much for that. And Sinan, based on now you're one of those people who I would consider as visionary in the space and who kind of sees things a bit farther than others when it comes to data quality in this kind of context. What do you think the future holds for data quality in feature stores? Do you think what we're doing nowadays is kind of hitting it, or do you think we're missing something that will become important the coming few years?
Yeah, first off, wow, thank you. Appreciate it. Don't know if I accept it, but I appreciate it. I think we're on the right track. I think if I'm plotting right track on data quality over time, I think it's at least quadratic. We're getting there faster. I think, like kind of as I hinted at earlier, in the last decade, there's more talking, there's more conversation about quality. And I think from the definitions we're hearing today, quality as it refers to representation, as it refers to drift and or shift, not to open that can of worms again, and just thinking about what mathematical languages we have that can translate our perception of quality to a machine's perception of quality, I think is converging. It feels like it's converging. Our ability to be able to, as Aman was actually talking about, just knowing and having a collective knowledge about which kinds of tests are best for some kinds of domains, that alone as a collective data science knowledge is so crucial because that's shareable. And when that kind of knowledge is shareable, for anyone with a Stats 101 background, that knowledge becomes ingrained in the next generation of data scientists and machine learning engineers. So as long as we're talking like this in an open setting about what is best and for what kind of purpose, whether it's financial fraud or bias in criminal justice data or arrest data or anything in between or outside of those bounds, I think that kind of transparency will be noticed and I think will be replicated by people under us, looking to us as role models, as how should we be thinking about data? Should I just fit this to any quality data? The answer is no. Again, based on our definitions, we have to first make sure the data is at a top tier quality before we can even move on. As Reka mentioned, that is number one. We'll not move forward if it does not meet our quality standards. And if we have a rigorous standard, that means we are on the right track. So long story short, I think we're on the right track. As long as we keep talking about it, keep converging, keep writing papers, as Jim mentioned, I think we're on the right track.
Cool. I think that I really much share that view on a data quality in a more general setting. When it comes to kind of one of the things outside the features store domain that is very unusual is when we talk about data quality for unstructured data, because outside the features store domain, everything is focused on the structured data, right? For various reasons. And Aman, you alluded a bit towards the kind of when you get to unstructured, you start to look at the embeddings and so on. I want to follow up on that with you, Nikhil. Do you have any kind of do you have a take on how you work differently between the structured and more unstructured data when it comes to data quality?
Yeah, I mean, the answer is going to be a bit strange. So in most cases, the model consumes the unstructured data by converting it into semi-structured data like embeddings. So we map this unstructured data, audio, video, images into an embedding space. So it forms some kind of a spatial distribution, right? And when you have distributions, it's very natural to like map them into 2D planes using algorithms like UMAP or find anomalies or find clusters, right? All of those things apply to unstructured data, but the prerequisite is that you map it into a semi-structured space or into an embedding space, right? Once you have the embeddings, then it's fair game to apply n number of methods to summarize and identify quality issues.
Yeah, and when we get into these kind of embeddings, or like, I mean, when we go from unstructured to semi-structured, I mean, the interpretability of these features aren't that high, right? So when it comes to data quality, sometimes you have these rule-based things, as Reka, you mentioned, sometimes you have 5 in cardinality and it goes down to 3. It's a very easy thing for you to understand as a human. But in other situations, you have these kind of, what is it even that you're looking at kind of thing? And you can calculate on these things, but to rule-based rules on that becomes trickier, right? So it could be to you, Aman or Reka, but how do you think about the difference between kind of having more anomaly detection type of monitoring versus rule-based?
So my approach would be, right, there are things that are simpler with rules, and if the patterns are as simple that can be represented by rules, probably that is the easiest way to go. But for other things, right, like distribution, so that if we can build simple statistics, as Senan or Nikhil mentioned, if you understand your data, then you can sort of capture that as anomaly detection. So for instance, the feature store that Dustin described earlier, as the data lands, we do have null counts, and based on like certain, if the delta is over a certain statistical percentage or a sigma, we do alert and those kind of things. So depending on the shape of the data, if it's a stable shape, then you can use statistical models. Otherwise, you may have to come up with a little more sophisticated anomaly detection models to sort of deal with the data. For instance, for some of our CDN data, we actually have an ML model in place. That's not from the feature store perspective, but in general, we had to do at a data warehouse level sort of a thing. So the shape, the cardinality, and the distribution of the data kind of dictates what kind of approach would make sense. But I'll yield to Han to add more color to it.
Yeah, I actually agree with Rick at like that sort of highest level where there's statistical approaches that can tell you, hey, something might be wrong, you might want to go deeper. But that human level understanding of the data is really where we're focused on as a platform, which is, okay, you just got pinged, but like, how do you go figure out what's wrong, right? And that's where kind of what Nikhil was talking about in terms of either dimensionality reduction techniques or mapping, higher dimensional vectors to lower dimensional sort of visualization spaces like UMAP. But at the end of the day, you as a human have to go click on points and figure out, is this correct or not, right? And so what we're offering as a product is clustering, which can help make that a little bit easier, make that a bit of more of a funnel. And so we'll cluster based on these sort of techniques that will actually find similarities between points. And in this space where points can be very far apart, we'll surface up visually, in actuality, these points might be very far apart, but that like in this space, they're sort of closer together. And so, you can actually kind of get an entire bird's eye view is what we're trying to show you, where you can go from the highest level down to individual points to go and export or label and refine your data set. And at the end of the day, like when it comes to understanding embeddings, I think where the space is generally like a bit forward looking here, and maybe Sinan, I'm curious if your take here is like, effectively, you'll need embeddings to understand embeddings, right? Because to some degree, these are models. If you're a model as a human that is deciding what's good and what's not, then in some ways you can train models to also kind of perform those sort of similar actions. And so embeddings being used to visualize and even get a deeper sense of the embeddings that you're trying to determine individual points for is a direction that we think things are headed. And that's really what we're sort of building tools to enable, is that sort of clustering and just starting at the highest level, clustering and then refining and getting into individual data points that you might need to export as part of your flow.
Yeah, I couldn't agree more. Sorry, go ahead.
No, yeah, I've actually, as someone who's actually built on similar drift techniques using clustering, mostly coming from the customer support space, which is where I spent most of my entrepreneurial time, is using that kind of shift or drift under rather terminology to say, hey, this cluster of people talking about their passwords appears to be moving, and you can define moving in some Euclidean sense or some non-Euclidean sense depending on your level of topology. But if you can show someone, hey, this cluster of people who are semantically talking about the same thing is somehow moving slightly, perhaps there's a new issue to be logged in that space. Or to put it in the more shift direction, to take us back a couple of years ago, if in the early March of 2020, people are asking about obtaining a refund because the global pandemic has shut everything down, fast forward 2 weeks where people are still talking about refunds, but not asking for one, asking about the status of their refund. So you have people talking about arguably the same thing semantically, but it's a bit subjective. So the ability to show that in a visual form of that kind of semantic movement across the graphs, or especially if you can quantify and automate it, that's the next step. But for now, you're right, it's kind of on humans to see that drift visually. But I think it's going to be a really big game changer in the next couple of years if we can converge that automatic visual detection of that higher clustered shape.
I fully agree. And having spent my prior time on cybersecurity, I can vouch for like having better visualization tools. Like even if you had most of the models or the statistics in place, having a good visualization reduce the time to identifying the true root cause, or separated, like give human experts the task that they are best at while abstracting out the other dimensions and stuff.
Very cool. Thank you so much, everyone. We are actually over time. I'm sure there's so much more to discuss. This is ending up with kind of mentioning the kind of Andrew Ng and his data-centric AI movement. I think it's time. It's very timely. It came a year ago. I think it should have come many years ago, but it's good that we start to care about data quality in every context right now. And yes, super exciting to see where what companies do in this area, as well as tools and platforms to help humans understand data and data quality in different contexts. Thank you so much for joining this panel, and thank you so much for inviting us.
Thank you.
Thanks, Patrick. Thanks, Rekha, and Sinan and Nikhil. We just ate into our break. That means no break. So we're gonna jump on to the next talk. And thanks for that panel. Very interesting. Data quality. Who doesn't care about data quality? Of course, it's an incredibly important issue for enterprises. So we're going to move into a new session now, and we're going to kick it off with Stefan Kravchik. And Stefan helped develop Hamilton, that he's going to talk about while at Stitch Fix. And Hamilton is an open source platform for feature engineering. So for how do you build features in a kind of a structured way that you can have a team work on them in parallel and still have a working code base. And I find it's a very interesting platform, and it'll be great to hear from Stefan about some of the work there. So Stefan, he loves the stimulus of working at the intersection of engineering and data. And he grew up in New Zealand. He speaks Polish very impressively, and spent his formative years at Stanford, LinkedIn, Nextdoor, Ibidon, and Stitch Fix. And Stefan, I just saw an interesting chart actually that of people of the countries where people live abroad, number one in the world is Ireland, where I'm from originally, and number two is New Zealand. And they're both islands at the end of the world, effectively smallish populations, and both quite good at rugby. So yeah,
true.
Yeah.
Yep. Cool. Yeah. Thanks, Jim. I guess I'm just gonna start sharing my screen here, and then get started. So yeah, thanks for the intro, Jim, again. So yeah, talking about Hamilton, an open source declarative micro framework. So it's not a fully fledged framework, it's a micro one that will help you write clean and robust transform code in Python. So essentially, as kind of Jim alluded to, essentially I'm going to be talking about how to write better code that will help you and your teams help yourselves. So this is a short talk. Hamilton is open source. It is easy to get started. If you miss something, there should be documentation that will cover what's in this talk. So start off, for those who don't know, I'm going to introduce what is Hamilton. In one sentence, I describe it as a declarative data flow paradigm. So it's a paradigm in that it's a shift in a way of thinking. So you kind of have to buy into the way of Hamilton prescribes. It's a data flow paradigm. So through it, you're going to be describing how data and compute movement kind of flows. And then it's declarative. So you're going to part of the premise of Hamilton is that you declare outputs as well as inputs very explicitly. And I'll show you that in just a second. So at a high level, if you're going to be using Hamilton, you're going to be writing some code that's going to describe a data flow that then you're going to use to kind of compute and get out some object. So you as a user will write Python code. You will then provide it to Hamilton so that your code will describe a data flow. This data flow Hamilton will turn into a DAG or a directed acyclic graph. And then you as a user will then tell Hamilton to compute something. So this could be pandas data frame, a machine learning model, or any Python object. You can kind of use Hamilton to create it. In terms of the actual code, like the things that you need to write, well, you need at least 2 files. So you're going to write your code and you're going to organize them to Python modules, and then you're going to write some driver code that will take those modules, tell Hamilton to build a DAG from it, and that's where you'll provide the right inputs and then say what should be executed for Hamilton actually to materialize a result for you. So what's this Hamilton paradigm? Well, here I have an example using pandas. So I have 2 lines of pandas code that create 2 columns, C and D. With Hamilton, you don't write kind of code in this style. Instead, you write things as functions. Now, these functions, you don't directly execute. That's why you need some driver code, which I haven't shown here, but I'll show in kind of the next slide. But essentially, the paradigm that you kind of think about is that if there is some output that you want, you essentially have to write a function that has that output variable, or where the function name is kind of the output that you're going to request. And then the function input arguments then declare what are the inputs required to actually compute a result. So to map this first line here, we're going to be writing, if you want to create a column C in pandas, that's the sum of A and B. You're instead in Hamilton going to write a function called C that takes in and declares A and B as input. Then the function body will have the actual computation. And then to create this column D, we then declare a function D, and its only input dependency is C, because that's the only thing that's required for it to be computed. Transform logic goes in the body of the function, and that's roughly how you write a data flow in Hamilton. Now, a full hello world, as I said, you kind of need this driver code. Looks something like the following. So again, you write your functions and curate them to Python modules, and then you got to write some code to kind of stitch things together. So I call this kind of driver code, since it's kind of analogous to a Spark driver, for instance, since it helps drive kind of execution. You're going to be importing some modules from Hamilton. You're going to be importing your feature logic here. You're going to be instantiating what's called a driver object, which may or may not take in some configuration or initial data. You also then pass in the modules. From there, Hamilton will kind of scrape the modules, build a DAG, and then you're going to simply say, tell Hamilton to execute something, and Hamilton will walk the DAG and only execute what's required to materialize the result that you want. So you might be thinking, okay, cool, that's a nice little paradigm, but why was it created? So let's kind of back up a little. So at Stitch Fix, there was a time series forecasting team called the Fed, and essentially their workflow looks something like the following. They got business actuals, created a featureized data frame, fed a bunch of models, which predicted the future, then they gave the business forecast. The biggest problem in their workflow in terms of delivering results was actually managing this kind of the code and kind of getting a featureized data frame, which is what Hamilton was designed to solve. Why was this an issue for them? So in time series forecasting, you run into this more sooner than other kind of modeling disciplines, but it's really easy to write a lot of features because features or columns, if you're thinking in a tabular sense, are just functions of other columns. So if you want to create more features, they're just derivatives of other features. So to create a holiday kind of feature, maybe you're just taking in year and week. I don't know, if you want to, create a new feature, maybe you're deriving something else. And so you can then come up with this kind of chain of dependencies of creating various features. And this is what was causing a bunch of issues for the team. So just to ground what I said in terms of some code, here is the characterization of the code they were kind of writing. So you have the Panda script. At the top of it somewhere, you load some actuals, say spend and signups. You then, start your featureization process. You start appending columns. Maybe there's some configuration where, depending on what's passed in, you will have a different implementation of the feature. Then you'll just maybe you have some one-line incantations of features, or maybe you'll actually, have delegate to functions that will kind of create these features for you. And then at the end of it, you're going to be, saving this for use for model training somewhere, or even just model training off of this directly. Now, this code looks pretty innocuous, pretty easy to manage. I want to say now, if you scale this code to, thousands of columns, and a growing team over the course of years, the code here and your process isn't going to look anything but clean and robust. Why is that? Well, if you think about unit testing and integration testing, unit testing here is pretty hard or non-existent if you write a lot of things in script form, especially if you do these one-liners. If you want to, do an integration test, or say you add a new feature, you kind of, even though you don't need to compute all the features to test that one thing or that chain of dependencies, you kind of, you are stuck running everything to test one thing. Then there's code readability and documentation. Give this to a new hire, they're kind of gonna scratch their head and have to literally read every single line of code and then try to draw this kind of a mind map of how everything connects, because there isn't really a natural place to put documentation or even kind of segment the code in a nice way if you're unfamiliar with how to do so, right? And then what happens over time is you're going to have updating code, maybe there's some upstream dependencies that change. You then have to kind of know the downstream impacts of in which case if you write code in this kind of manner, tracing lineage is difficult. Like, would you know that if you were to change acquisition costs, that actually this could impact the spend B feature? It's not obvious unless you kind of read and understood the code, right? And then if you can now, you have a growing team, things are happening, how do you actually reuse things? Well, if you write the things in this kind of form, everyone says, oh, I'll refactor later, but that generally never happens. It's always easy just to cut and paste, and then you have duplication everywhere, and then that becomes, adds to your maintenance burden. So that was the kind of the motivating kind of things for building Hamilton. So, so Hamilton at Stitch Fix, well, it's been running for over 2.5 years, probably almost closer to 3 right now. And the Fed team who we designed it for, manages over 4,000 feature transform definitions with it, where all feature definitions are unit testable, documentation friendly, and centrally curated, stored, and versioned in Git. So there's a nice kind of versioning story that they have. Otherwise, the data science teams who use it at Stitch Fix love it, and we've seen the best adoption from active time series forecasting teams because they're the most willing to pay the migration costs. So Hamilton isn't a drop-in replacement. You kind of have to re-engineer or rewrite some code to kind of make use of it. And along the way, we actually found that it's actually by writing Hamilton code, it actually was a productivity improvement for the team, since they used to have the Fed team used to have a monthly feature update and model fitting task that used to take on the order of a day. Now it takes less than 2 hours, so it's 4x faster. And the only change is by using the Hamilton paradigm to write their code, which I think is pretty neat. So okay, so to the theme of this conference, feature engineering. So how do you use Hamilton for feature engineering more concretely? Well, we have this kind of rough schematic here of kind of modeling things. So you have a featureization step where you're loading data, transforming into features, then fitting a model, and then you're using that model in production to predict stuff, and then passing in features there as well. And I want to say with Hamilton, you can actually model your entire machine learning workflow end to end if you wanted to. But just for this talk, I'm going to focus on featureization. I will also kind of focus things on pandas, just because I think that is the most common kind of thing that people know and understand. But Hamilton isn't beholden to pandas. So if you want to do NumPy stuff or your own custom kind of Python objects, Hamilton can support you there. We're just going to, for the rest of this talk, I'm just going to assume you know pandas, and the examples are therefore going to be oriented that way. You can Hamilton is a micro framework. It doesn't replace an orchestration system. So to use it for featureization, you would embed it, say, within Airflow, Metaflow, whatever your orchestration system of choice is. You could run it in a Jupyter notebook. This could be used in front of Feast. So create the features to then push to Feast. And then you can also use Hamilton in an online setting, since it's a very small Python dependency footprint. It can run in an async IO environment, so it's very easy for you to potentially even reuse your feature definitions from batch to an online or streaming settings, as long as everything runs Python. So onto featureization. So if you are going to use Hamilton featureization, you need to write at least 2 files. Say you need to write something that will potentially load data, and have your feature transform code, say features.py, and then you need to write some sort of run.py file or driver file, as I've referred to earlier, that will take these feature definitions, create a DAG from it. And then that's where you kind of specify, what you want computed, where you can, so you can specify the superset of features, and Hamilton will only walk the DAG for the things that you've requested. So in terms of the actual code, so thinking now, so one, you need to write functions to load data. This is where you kind of normalize naming of features or inputs. You need to create a common index to ensure that things join on. Then you're going to be writing kind of your feature functions, and optionally you can model your actual model fitting and prediction stuff if you want to as well. And then you're going to be writing these kind of driver files to kind of actually orchestrate and materialize data. And as I said before, with Hamilton, you can kind of build up this kind of bank of features, which can be the superset of what you need. And in a driver, you only request the things that you want, and Hamilton will only walk the DAG for what's needed. So pictorially, with Hamilton, for every kind of input, you'd be writing some sort of generally some function to load it. Then from those functions, you'll then be kind of writing your actual feature transforms, and then you'll be writing some driver files that will actually specify what you want computed to kind of compute a data frame for model training that you want. In terms of general problems with feature engineering, just to kind of touch on this, that will bring things back to the robust and clean side of this talk. So from the human and team side, as it was with the Fed, kind of the examples, it's really easy to write highly coupled code. that is really, difficult to take out of different contexts and reuse. And so that, adds to your maintenance burden. If you want to reuse and understand other people's work, most people actually rely on materialized data at rest to kind of do that. But with Hamilton, I think, we have a better way with code to potentially do that, since we kind of facilitate and make, the code reuse easier. And then if you do have, things in production, generally, things break, and that it can detract from your time. Hamilton has, a few things there. Otherwise, from the machine front, just to touch on it, if data is too big to fit in memory, you need to figure out how to scale your computation. Similarly, if you want more throughput, you got to figure out how to parallelize it. And so I want to say Hamilton was designed, for the human and team side, but also has a few hooks for scaling things on the data and compute side. But for this talk, I'm just going to focus on kind of the human aspects of things. Okay, and so how does Hamilton actually make feature engineering clean and robust? So as I mentioned, with highly coupled, it's easy to write highly coupled code, especially if you're writing pandas in a kind of script form. But with Hamilton, you're kind of forced to decouple your functions, your transform functions from the context, from the driver of where they're actually used. So it's very hard to actually write coupled code with Hamilton. And then because you're forced to curate your functions into modules, it's much easier to kind of reuse and understand people's work, since you're forced to kind of curate from day one. You're not going to be appending things to a script willy-nilly. You're going to be placing them into a specific module. Every function is unit testable. So if you want a good testing story, it's very easy to be test driven with Hamilton. Documentation is natural, since you can reuse the function doc. And then with Hamilton, just because of the way that things are stitched together, you are forced to align on the naming of them. So there's no foobar variables or things that don't make sense, because you're kind of forced to make sure that people understand and can use the outputs. And so therefore that's also reflected in the functions and the code you write. And then in terms of helping with production issues with Hamilton, the idea is if there's an output, so a particular feature, there's only one place where that code is defined. Then it's very easy to go to the code definition and understand what are its input dependencies. And so then it's very methodical to methodically debug issues. Because you're forced to curate things into a code base, it's very easy also to version features with Git and packaging. So if you need to roll back, there's a very kind of straightforward way to kind of do that. And then Hamilton also has the ability to do some runtime data quality checks without you having to install, something very, heavyweight, such as Great Expectations. So just to give you a bit of a flavor and example of like what a Hamilton function is. So here's a function you likely haven't seen before. I want to say, take a few seconds to try to read it. It should be fairly understandable to you, and that's part of that was part of the design philosophy with Hamilton, since you read code more often than you write it. So how can we make it much easier to hand off code and inherit to people who have no context, right? So specifically, just to hammer home the points here. So with this function, it's very easy to unit test. We haven't leaked how to get data in, so it's very easy then to come up with a unit test that injects the data that you want to test the logic. Documentation is pretty easy and natural, since as you might have guessed, there's this at tag annotation, so you can add in different metadata if you wanted to help understand who owns things or impacts. We can actually visualize things, since we by definition have a data flow that we can then we actually Hamilton outputs a graph visualization for you pretty easily, and then you have the function doc string, as well as the names of the function and input, so that make documentation very natural with Hamilton. Again, modularity and reuse, you're forced to curate these functions into modules, which are decoupled from drivers. So you can have a lot of different contexts that reuse the same modules. And so your maintenance story is much easier there, since you only have to, if logic changes, you only have to change it in one place. And then what happened at Stitch Fix was the team actually built up a central feature definition store. So basically they built up a little code base where they aligned on naming, curated things into modules, and by using Git had a very nice versioning and lightweight story of just of how to maintain features and go back in time and understand why things changed. And then probably didn't, you might have guessed and I didn't tell you, but this @check output annotation is just a lightweight runtime data quality check that it was specifying that, hey, the expectation of this output is a float, and it should be between the ranges of -5 and 5, and there shouldn't be any NaND values. And so that's kind of a rough sketch of the Hamilton functions and why I think they help you write clean and robust feature engineering code. In terms of code-based implications, like I think we generally forget about this as we're writing code, how we actually structure our code base. Well, with Hamilton, just to hammer home these points again, it's like functions are always in modules, and then you write JavaScripts, that actually contain context for how things are executed. They're very decoupled from those functions, so you end up curating modules and then creating very separate JavaScripts that. So you get code reuse from day one, so you can have a single kind of definition and then different contexts that can reuse it. And then generally from a maintenance perspective, if things change or inputs change, you only have to change this one JavaScript. You don't have to change all your feature logic, and so maintenance and updates are easier there. And then your code base ends up being pretty well structured. So you can give Hamilton to a junior data scientist, and they will write maintainable code. So to kind of summarize this talk, so Hamilton is a declarative paradigm that essentially helps you to describe your feature transforms and is embeddable anywhere that Python runs. It grew out of a need to tame feature code base at Stitch Fix, and go ahead and try it. I'm sure it'll make yours better too. In short, Hamilton essentially allows you to write clean and robust feature transforms by essentially getting you to write to practice software engineering best practices without you having to know it. And essentially, it's my goal, and I think a firm belief that anyone who's doing feature engineering in Python should know about Hamilton, because I think it's a useful tool to have in your back pocket if you're going to be writing code that you want to live for a while. So again, Hamilton's open source. Do go ahead and try it. Star us on GitHub. We are trying to curate roadmaps. So if you find issues or want features, you do create issues on GitHub. We also have curating a Slack channel. So if you want to come or if you have ideas and need help, do join us. Otherwise, that's the end of my talk. Thank you, and happy to take questions.
Thanks, Stefan, very much. It's very fascinating work that you're doing at the moment on Hamilton. And I think it complements many of the feature engineering tools that we use, like Pandas, very well. And we have one question that I think we have time to take. It's about, if you click on the Q&A, you'll see it in more detail. It's quite a long one. Is there anything that prevents the developer from forgetting about existing columns, of which there are many, and recomputing a column that is used as an intermediate for the desired feature? For example, an enforced single computations for a feature function. Maybe this issue ends up being picked up in post-monitoring.
So if you define the same function with the same function and the same module, like Hamilton won't be able to pick that up. But if you define them in different modules and try to construct a DAG with them, Hamilton will tell you, hey, look, you got two definitions, something's broken, and it won't allow you to kind of proceed. So we've tried to ensure that we have, some static analysis checks when you build the DAG to kind of help with some of those issues. But yeah, the only one we can't catch due to Python actual limitations is if you define the same function twice in the same module. But generally, that's your IDE can generally tell you that, and so hopefully that's caught that way. Otherwise, yeah, I think to Jim's point, like Hamilton kind of complements a lot of the tools here. Yeah, you can run it in front of things if you wanted to, hook it into data quality on the output of things. It's kind of, Hamilton gives you a lot of flexibility there to do so as well.
Yeah, and I like the way it enforces what I might consider best practice, which is to put feature logic in functions in Python. It's just good practice.
Yep.
Cool. So that's I muted myself. So we're going to move on. This next talk is Richard Woolston, who's a data science manager at American First Credit Union. Now, unfortunately, Richard can't make it, but we pre-recorded the talk. So, in general, we've had live talks you've seen this evening. This one will be pre-recorded, but hopefully it'll be very much of interest to many of you in the buy versus build debate. And Richard, when he first joined AFCU, he was working to productionize their first machine learning model to predict member churn. So they're a credit union in the States. And after 1 year, AFCU's models in almost every major aspect of the financial life cycle. So without further ado, we'll jump into Richard's talk. So I'll mute myself.
Hi, everybody. My name's Richard Woolston. I'm the data science manager at America First Federal Credit Union. We're a larger credit union that's based out of Ogden, Utah. We are I like to say we're in all of the states west of the Mississippi, except for the states that touch the Mississippi here in the US. We're about 7 17 billion in assets, and we have over 1 million members. As far as details about the data science team, I run a team of 5 right now, and it comprises of machine learning engineers and data scientists. So what I would like to talk today is about our feature store journey and where we started to how we got onto Hopsworks, and then where we're going now that we have Hopsworks. So the way that I like to start that journey is always talking about what I call prehistory. And a good way to set that up is kind of how the data science team is set up at America First. We operate much like a hub and spoke at America First, meaning my data developers are core competency shops. We maintain tools and practices and support a lot of embed analysts that are kind of out with the various products and things like that. We also act like internal consultants. And what that allows us to do is we don't own anything, but we kind of help when we have this large enterprise scope. So along that path, what we've had to do is we've had to develop several products, being kind of a core competency, and we've had to deploy lots and lots of data objects. So when we first started doing this, this was about 8 years ago. A data developer would sit down, they develop some sort of code, right? Let's just say this is membership attributes. Once they got to membership attributes being in a good place, they would then email the DBA with the code. The DBA would say, hey, let's go ahead and get together in a conference room. Because at this point in time, the DBAs were the only ones allowed to make changes on the centralized enterprise RDBMS. And often it would take some time to coordinate this. And as we would do these deployments in the conference room, there would be a lot of issues with these deployments. And environments were not always in sync. So there was kind of a lot of live troubleshooting. So what this led to is often we would have to take several months to make deployments, to tune those deployments, because you never do the deployment or the product requirements right the first time. So we'd have to do several iterations of these. So it was fairly slow. Some of the other issues that we had on this was, SQL itself is a great language. What it really lacks is, I would say, ubiquitous or mature testing tools such as PyTest or unit test in Python. Java has similar frameworks, and I believe there are also unit testing styles in R. And because we were so focused on these low-level issues, we weren't focused on the more strategic level issues that we should have been focused on, such as the data model. So that was one of the downsides, was we would often end up with features that were calculated in multiple places, such as length of membership, balance, and those types of things. Just because we were so focused on the lower level drudgery, there wasn't time to how do we strategically hold all these things together. So we did this for a couple years, and then we asked ourselves, there has to be a better way. And one of the ways that we first started to iterate on this was Python. So we moved into a CI/CD architecture. We onboarded the Atlassian SDLC stack, and we were really good at deploying Python code several times a day and getting it out with low change failure rates. Now, what this really put a friction point on was our database layer. Our database layer, we still had to get with the DBAs. We had to have them push through changes and kind of all this clunky stuff that we were talking about kind of in the prehistory where we were. So we ended up looking around and saying there has to be a better way to deploy SQL code, and especially now that we have all these pipelines. So one of the tools that we found was Redgate. And Redgate is an excellent tool for migration code and other SQL needs and things like that. So we were able to plug this into the pipeline, and now developers were able to make changes, push that into the migration, and push that all the way out into production without needing the DBAs along, right? So this really helped shift a lot of this development cycle to the left. Another one of the core issues that we had to flush out along this journey was the fact that and especially educate the organization on, was the software development lifecycle is similar, but also uniquely different from the analytic development lifecycle. Early on in this journey, we were always told, like, hey, you need to build your data products in test. But the problem with test is test had loads of testing with tester sim records, which are never great for building data products, because as you build the data product, it's kind of a discovery, iterate, discovery, iterate, discovery, iterate. As the data tells the story, you build the product, which then dictates how you deploy it. So as we matured this process more and more, that was another one of the big things, was now we created a low latency production environment. So we went in probably the span of 2 or 3 years, We went from emailing the code to deploying that way to not really having a good development environment to now we have a low latency production environment. We're using Redgate to go ahead and manage those deployments, get them in pipelines, get them out to the database, and shifting as much left as possible. At the same time, we added other tools such as Great Expectations into the environment, so that way we could test the data as it flowed through the system. Now the one thing we did was we removed a lot of the developer friction, which really brought to light a lot of the runtime issues we were having. So the enterprise RDBMS being a centralized managed area was not a great place for us to need to backfill or run things quickly, just because it's really a tragedy of the commons type situation and unknown query support. So when we'd have to backfill, we'd have to time these things for the weekend, so that way we wouldn't bring down the data warehouse for other people that were using it, other OLTP or OLAP systems. So this led us to say, well, now that we've iterated from here, there has to be yet another step that's an even better way, which led us to the feature store journey. And so we started our feature store journey probably around the same time that feature store started to become in vogue, which was really convenient for us. So probably about a little over 2 years ago. And at that time, when we were looking at feature stores, there were really three contenders. There was Hopsworks, Tecton, and Feast. So as we looked at the three products, we said, well, we really want to find a partner to work with. We are open to onboarding open source projects like Feast, but this is really not a product that we want to do that right now. We have a lot of other tools, Airflow, Great Expectations, and all these things that we're maintaining ourselves. This is probably not the build it yourself essentially approach, which is Feast. And then as we look at Tecton and Hopsworks, one of the other things, being a financial organization, we're a little behind on the cloud transition. So we needed to find a partner and a tool that allowed us to first deploy on-prem and then convert it to the cloud. And Hopsworks is an excellent tool for that. So that was one of the deciding factors for us choosing Hopsworks among a couple of others. So that eliminated Tecton. So we went ahead and we deployed Hopsworks. And the ROI was pretty quick. So our core focus when we deployed Hopsworks into our ecosystem was to get all of our training sets. So we had lots of effectively dimensions and facts that we had collapsed and why to get those on the Hopsworks. So underneath the hood, Hopsworks uses Spark to go ahead and execute its transformations and its movement across the data layer. So once we started implementing and learning Spark, the nice thing was we now had native test infrastructure within it. So we were able to use PyTest and unit test, and our change failure rate was way down, which meant we deployed faster, we deployed quicker. So it took us about 3 or 4 months to get a lot of our core, what we call feature groups and Hopsworks up and running and getting the data scientists onboarded. Now, as we found as we deployed into this newer architecture and moved away from SQL, not only was our code quality higher and really measurable, honestly. I think it's hard to measure the code quality of SQL, but our runtimes were faster. So as we ran jobs in Airflow that then kicked off jobs in Hopsworks, we were seeing jobs complete in 15% and even 33% of the time that they would on within the RDBMS system. So what that allowed us to do is when we looked at backfill scenarios anymore, we weren't looking at taking weeks or several days to go ahead and backfill stuff. If we had to make a change to the data, we could really backfill our entire ecosystem on some of our larger data sets in maybe a day plus, not much more than that, which is a huge game changer for the things that we need to do. And especially for keeping nice, clean, good data. And what that also allowed us to do is there were a lot of features and calculations that previously we just were not going to take on because the RDBMS system just couldn't keep up. It couldn't compute it fast enough, which is really bad when your tool is effectively dictating strategy. Now, we no longer have to do that. It's no longer a can we, it's, well, let's do it. Let's get it into the backlog. Let's get that feature in and let's get it running. So what we found too is that as we've onboarded additional data developers into this, it's much faster, right? Because now we have a testing framework. And so as they make changes, we can make much bigger changes quicker because we have all those testing frameworks that come around. PySpark, such as PyTest and unit tests. Now, that's the left-hand side of the equation. And now on the right-hand side of the equation, we have the data scientists. So the data scientists are also able to onboard much faster and really effectively run their jobs much faster, because Hopsworks is really focused on, a shopping cart. I shouldn't say really focused, but one of the main attributes of them is they basically have a shopping cart-like experience for their features. So it's easy for data discovery. It's easy to bring things together. And once you bring things together, it's easy to export again in your Jupyter notebook and go ahead and run the models you need and then move those models on. So this also brings into one of the highlights of one of the other massive benefits of Hopsworks is Hootie underneath. So beforehand in the RDBMS, we had to create those change data capture tables. And so a lot of our source systems were type 1. They didn't have that change data capture. So as we created these legacy data structures type 7, so that we could capture things, we had to write that structure in. Now, when we connect to these source systems, we no longer have to worry about writing that stuff, because underneath the hood, Hopsworks already does it. It's a flip of the switch. So we have those source ones. The data engineers are pushing it in. Now, kind of bringing that full circle back to our data scientists, is our data scientists develop models. Hopsworks underneath the hood has both that data control and that version control. So from a compliance standpoint, as we're training different models, as we're upgrading, it's always easy for us to reconstruct, hey, you built this model. Where'd you get this data? How is it calculated? And then all the way back, which is really, really nice. On top of, like I say, the shopping cart, it's enabled our data scientists to onboard much quicker. To be honest, we're probably looking at a 3 to 4 times increase in onboarding speed, which is just amazing from a productivity standpoint. So that's kind of where we are. Hopsworks has really enabled us to, I would say, get out of the drudgery of that lower level, really start to innovate on how we want to implement things and increase efficiency, so that we're just not performing redundant tasks that should really be built in at this point into data pipelines. So this kind of brings me into where we're going, which is nice, because now we can really focus on these next level architectures. So as I said, when we onboarded onto Hopsworks, one of the core things that we were focused on was our batch systems. So now we're working on converting our online serving, which is pretty straightforward, especially in Hopsworks, and it's very quick. So a lot of our APIs right now are reading off of the RDBMS, and as we're running tests to convert them to this online serving, we're already seeing a 3 to 4 times increase in getting the data out as far as I/O goes and to the models, which is amazing, especially when you think of large data applications, how hungry a lot of these models become. The less time you can spend on I/O and the more throughput you can get, the better. So we're working on the online serving. We're hoping to implement that here in the next couple months in all of our stuff and complete what we're calling phase 2 of our migration off of the RDBMS, which we're really excited about. The next piece, which compliance, probably not a lot of people get excited about, but anytime I can find a tool that can really automate and help with the compliance aspect is amazing. So as I talked before, as the data scientists on my team train models, so they're in Jupyter Hub, they're connected to MLflow, they're experimenting. And as they're checking in models, we're connecting that to Hopsworks training sets, which are versioned. And so the nice thing is when the data scientist says, hey, I iterated a bunch, I'm ready with the model, let's go ahead and deploy it. And we do the model review. When they go and they push it into the registry to then be deployed, our systems go ahead and say, great, we've got to send this out for validation. One of the joys of being in a financial driven organization, we have to have a second and third line go ahead and validate those things. So, but because we have Hopsworks and we have all these pieces interlinked, as our CI/CD goes out, it goes, hey, this model version blah was trained. Oh, you were trained off of this Hopsworks version, Hopsworks dataset. You can go out to Hopsworks, land the data. Once again, really helping with the reproducibility of things, which is nice. It took us a little bit to get there, but it's really nice, because one of the things you don't want to be in a validation is, hey, are you sure this is the right data set? How did you do this? And all those things. So it's really helped us start to fine tune that, which has been amazing. One of the next things we're really focusing on, once again, because we're out of the drudgery of these lower level tasks, is lineage. Really cleaning up the lineage, which Hopsworks out of the box has really good, lineage, and now we're connecting that to the enterprise data catalog, and so that way we can get our power business users and product owners in there, really creating rich documentation and engaging in the platform, so that moving forward, it just creates a nicer, well-documented system, and not really the self-documenting dream that people are always chasing, but let's take care of this lower level stuff so that people can get in and really focus on that really nice documentation rather than connecting things. Finally, the last piece that we're really focusing on with Hopsworks is, for a while, we've been using the open source version of Label Studio, and as we test and deploy models, we commonly have our product owners and our business owners go back through, say, hey, do you like this prediction? Do you not like this prediction? Yes, no. And so right now we're going to work on connecting those two things, so that way we can say, all right, data set comes out, the subject matter expert goes ahead and does what we need. How do we then get back there to Hopsworks and basically create this really nice, rich life cycle, so that way we can get as much information back into the system to then have a positive feedback loop in the future, so we're not losing information as we go along. So that's been our journey, and it's been quite the ride. And so that kind of wraps up where we're going. There's probably a lot of things that we're going to have on the roadmap into the future, but to be honest, this conversion from really this prehistory all the way to Hopsworks feels like an amazing transformation that's really enabled us to be innovative to a point that previously we wouldn't have had to have had. And there's just so much richness baked in the tool that it's allowed us to focus on these things moving forward. So that's been our journey on the Hopsworks. It's been an amazing success for us, and we look forward to working with the team into the future. Thanks everyone for taking the time to listen. If you have any questions, please reach out to the folks at Hopsworks. I'm sure that they would love to discuss in a lot more detail than we can kind of go into this presentation. But once again, thanks everyone for your time.
Thanks to Richard, who unfortunately couldn't be here, but it was a very interesting presentation. There's one question from an anonymous attendee. I'll answer it briefly. Can you explain more about how Hopsworks implements change data capture for a database that doesn't have native CDC functionality? So Hopsworks supports both external tables on Snowflake or S3, Parquet files, or any JDBC compliant database, but it also supports feature groups stored in the platform in Hopsworks. And in that case, those tables are stored in Hoodie tables. So Hoodie tables are Parquet data. Hoodie gives you extra ACID properties to those Hoodie tables when you write to them, but it also gives you commits. So every time you write to a table, you get a commit. So then you can actually do CDC and say, hey, what were the commits or the updates to that table over this period of time, or since the last 5 commits? So Hoodie as a framework, a data file format and a framework supports a CDC API. Okay. So we're going to move on. The next speaker is Ashint Thomas, and Dr. Ashint Thomas is a data architect at Scribble Data. Scribble Data have been around a while, so they've built a feature store, I think one of the first ones out there, and they're venture-backed enterprise with an MLOps platform, but the feature store as well, of course. And Ashint has 12 years of experience working on data science and engineering. Welcome, Ashint. Can you hear me?
Yes, I can.
Great.
Hope you can hear me and see my screen.
Yeah, we're good to go. Off you go.
All right. Great. Thanks, Jim. Thank you so much. So hi, folks. My name is Ashint Thomas. I'm from Scribble Data. I'm a data architect there. Today, I'm going to be giving you a lightning talk, a quick talk on sub-ML use case development. So don't scratch your head. I'm going to talk about what sub-ML is all about, and talking about how feature stores and what we call feature app stores are instrumental in development of these sub-ML use cases. So a little bit about Scribble Data. We are a feature store company. We have a feature store that does what a bunch of feature stores do, but then we focus on what we call the sub-ML use case domain. We are based out of Bangalore in India and Toronto in Canada. So we have heard a little bit about this today from a lot of the folks who spoke earlier. that there are a lot of different dimensions to data-driven problems, to machine learning problems, and we are seeing this as well. So you have your machine learning problems, and I'm going to put data-driven problems into the bigger bucket. You can look at it from the dimension of complexity, low problems that are low complexity to solve, all the way to high complexity. Low complexity, you can think of things like statistical averages, simple aggregates, simple models, all the way to high complexity, where you have real-time deep learning features on time series, or things like that. You have models that need to be built, data-driven solutions that need to be built for different classes of users, right? So internal users in your organization versus external users. There are a bunch of organizations out there that build solutions, for users and consumers within the organization itself, and you can imagine that the constraints, the requirements for that class of users is going to be different from external users. And the other thing that we're seeing a lot more today is the consumption of the prepared data that come out of these data-driven solutions, right? For the most part, typically, the data has been destined for machine consumption. So data that would probably sit in a database, or go sit in cloud storage somewhere and be accessed using APIs, be accessed programmatically. But there's more and more today the data that needs to be accessed for human consumption. And you can think of, for instance, decision-making applications, for powering decisions that humans need to make, where this would fall under. So if we keep that in mind, we can see that the assumptions that we have made about what the data needs to look like for these ML solutions, and what these ML solutions themselves look like, these assumptions start to change, because typically you'd have you deal with large data volumes, you deal with high performance real-time requirements, you deal with requiring high skilled talent. You need data engineers, you need data scientists in order to build these systems out, build these solutions out. And even the nature of the data itself, you'd look at probabilistically accurate data, right? I mean, you don't care if it's off by in the third decimal place. You just want it to be probabilistically correct. But then there are a lot of problems today. There are a lot of use cases that are coming about where these assumptions start to break down. And I'm going to talk about where these use cases lie. So in the past, what we have seen is that data preparation and data-driven solutions have typically fallen into two large buckets. One is on the low complexity end for business intelligence, so where you'd have data prepared and then used by a BI system for visualizations and data consumption. And then you have machine learning on the other end, where it's purely programmatically used. But there's this in-between space where there's a growing number of use cases that we call the sub-ML space. And we are seeing a lot of companies and organizations requiring data applications to be built here. So they need data, they need all of the guarantees around data correctness, all of the trust around the ways that this data is generated and delivered, but without having to build complex machine learning models. For instance, simple models, rule-based systems, those are enough. So you can I've given a bunch of examples here. Let's take, for instance, fraud detection, right? So think of an organization that does not have even their first data scientist, or they don't have data engineers, but they would have analysts, they would have humans who are making decisions on fraud that's happening in their world. So a fintech, a new fintech company, for instance, you'd have humans actually doing the detection of fraud. And if you can automate that, make that much faster for them to be able to reduce the time that they spend doing this work, that's a huge improvement of the performance that they have. So the sub-ML problem space is characterized, differently from what traditional ML looks at. So where, traditional big ML, we look at a few problems where there's high clarity on what needs to be done and where performance is important. Sub-ML, you talk about, a large number of problems, this huge space and a long tail of problems with changing requirements. The delivery, which means, the data needs to be delivered somewhere and then the data needs to be consumed. That is full stack, which means that you need to have applications that these folks can use beyond just the data being available somewhere to consume. Timelines, right? You're looking at a large number of applications, so you want to be able to develop these applications very quickly. And I also spoke about data accuracy, where you want very high accuracy in the data itself, because you're looking at things like, powering dashboards. You're looking at things like being able to, detect whether someone is fraudulent or not. So the paradigm that Scribble has, the system that we have is something that we call a feature app store, where you tack on an app store to your feature store. So your feature store takes care of generating the features, all of your feature engineering, and you have an app store which exposes very simple applications that consume these apps for things like planning, forecasting, for pricing, for fraud detection, for scenario planning, for anomaly detection, for metrics. And you need to be able to give folks who don't have organizations that don't have time to run month-long projects, the ability to compose these apps together, to put together pieces and components that they can build out the solutions quickly. So what we have seen, deploying our feature app store across a bunch of organizations, across close to 100 odd use cases now, use cases that take a couple of weeks to develop as opposed to the typical months. Having a feature app store basically helps you to streamline this use case development, because you have a common design language that everyone in the organization talks. You have less coordination, because you have one developer who can build both the feature engineering as well as the apps that consume all of the data from the engineered features. And obviously, because of that, reduced costs, right? All of the pieces that you need for your feature engineering comes as part of the platform. So when we're thinking about building out feature app stores, these are some of the things that need to be taken into consideration. And we see this as the future, not so much in the fact that sub-ML is going to replace ML. There's always going to be a place for both, but in the sense that sub-ML, it's almost like a gateway drug. The smaller organizations that don't have the talent required in-house, that don't have the resources to start investing in ML right away, but they have the data, right? So they can start building out data-driven solutions. What can they use in order to build their data pipelines in a trustable manner and use that data, be able to consume that data? And we see, there's a long tail of these applications. By some estimates, there are 70 to 80% of the data-driven problems in an org fall under the sub-ML category. And the fact that there's such low cost and low risk to experimentation would have organizations experiment with more and more sub-ML use cases. That's what I had in this lightning talk, and happy to take questions on Slack.
Great. So we'll take the questions on Slack. So we have to move on. Thanks, Ashint, very much, and we'll see you later at the panel in a few minutes. So the next talk is Simba Kader, and he is the CEO and co-founder or founder of Featureform, who build a feature store. So they're vendor feature stores, and he's going to talk about feature store usage patterns from single data science to an enterprise. Simba is, apart from being a very nice person, he's also building a virtual feature store, and he worked previously at Google, and he had a company called Triton ML, where his team built an ML infrastructure that handled over 100 million monthly active users. Simba, go ahead. Over to you.
Awesome. Thanks for the intro, Jim. I will the whole.
Try and share your screen, and we'll just make sure we're good to go.
Got it. I think I'm sharing.
It's a big green button at the bottom.
Got it.
See if we.
All right.
Yeah, you're good to go. Yeah.
Go. Thank you. Like Jim said, I'm going to be speaking about feature store usage patterns. We've seen a lot of users, from single data scientists using us to large enterprises using us. And I realized that a lot of the things I've learned are not kind of common knowledge, and I hope to fix that today. Who am I? Like I said, like Jim said, I'm co-founder, CEO of a company called Featureform. In a prior life, I was at Google. Left Google, started my first company where I handled over 100 million MAU, did recommender systems, fraud detection, churn prediction, subscription prediction, everything. Here's my LinkedIn. Featureform is open source. You can check out the repo.
Simba, you might want to just minimize the there's the zoom the top right hand corner.
Can you see that?
You just press the minimize button on that window. Good, we're good to go. Thanks.
No worries. So in MLOps, there are two problems to be solved. There's the processing problem and the organizational problem. And we like to make a separation between what we call ML platform and MLOps. ML platform is about scaling compute. What that means is I'm a data scientist. I have a model has to run across 100 terabytes of data, whatever, and it needs to have this latency. That's an ML platform problem. It's usually pretty binary. You either can handle your scale or you can't. MLOps is about scaling people, which is organization, versioning, sharing, everything that comes with working with people. So in feature stores in particular, processing problem is you need 10 millisecond latency, 100 terabytes of data, streaming data, etc. Organizational problems are who owns this feature? What happens if whoever leaves the company, or is the feature being used? Am I allowed to use this feature with PII? What features is our ad serving model using? And how is this feature defined? Like, what's the lineage here? If you scale up without MLOps, you end up with something like this. I'm sure a lot of you have this right now at work. And so the goal of MLOps is to make this not happen. So I'll give a really quick brief on a virtual feature store. A feature store enables data scientists to define, manage, and serve their model's features. A virtual feature store aims to sit on top of existing infrastructure and solve the majority of the organizational issues without really focusing as much on the processing issues. We let other vendors handle that, like Redis, whoever. So we provide the application layer of a feature store. We kind of solve the feature store lifecycle or feature lifecycle problem on top of your existing infrastructure. So let's talk about how it really looks. So we have single data scientists using us. We actually have a local mode in Featureform, which is unique to us. In local mode, your compute is your laptop and your storage is your file system. The feature store in this case is all about being a repository of definitions. It's Git, but it's Git that is feature lifecycle aware. It understands what a feature is. It understands what a training set is. It understands what a transformation is. So you can store all these things in this purpose-built repository. You kind of get that Git-like history of changes, and you're able to progress. If you are a single data scientist in a larger team, that's often how we get into companies. As more people from your team start to use it, it scales up very cleanly. If you're in production, now you have to have features that are deployed. You have features that you're working with experimentally. Again, the life cycle of a feature is not just in deployment, and it's not just in your notebook when you're experimenting. It's both, and we think about both. So we make it very easy to be able to, we've seen that it's very easy when you're using a virtual feature store to simplify feature deployment, to monitor production features, and to unify that experimental and production feature with that unified definition language. When you get to a team, this is the thing everyone talks about with feature stores. Enhanced communication, you have a standardized definition language, you can discover and understand each other's work, you get lineage, you get search and discovery, you get the UI or whatever, and you can reuse things. In our world, our definitions are immutable, so you don't have to worry about breaking downstreams, and you don't have to worry about your upstream breaking. So most people, when they talk about feature stores and the value props, they're talking about just for a team. But I think it's way more fascinating at the enterprise. At the enterprise, the feature lifecycle becomes much more complicated. It goes from being about, like, hey, we're just sharing things, to, hey, we have global features that everyone in the company can use, maybe like a user embedding. We have team-wide features. We have individual features. In some companies we go to, a feature can't be used in production until it's checked off by legal. All this is part of the feature lifecycle. And we believe the feature store, and we designed the virtual feature store concept around the idea of adding that feature lifecycle on top of existing infrastructure. We separate out the concerns. There's a concern, like I said, of the processing problem and the concerns of the feature lifecycle problem. And we focus on the organizational issues, the versioning, the sharing, the reuse, the access control, governance. So at the enterprise scale, the value of feature stores become the hierarchical search and discovery, visibility. It's actually what you can't see, which makes it interesting. Heterogeneous infrastructure. We have a lot of people who they have Spark in one team, they have Snowflake in another team. Some people have Spark, one Spark in one region and another Spark in a different region. They have Cassandra here, Redis there. We don't think that really matters for the feature store problem. The feature store problem is, again, the lifecycle problem. You can sit on top of existing heterogeneous infrastructure and provide a unified interface. Think of like Terraform on top of multi-cloud. Like, it's still the same abstraction. It doesn't really care where the stuff's going. You get governance, access control, audit logs. And like I said, the cross-functional workflow, the ability to define, hey, legal needs to sign off on this, or hey, for this sort of model, can't use these sorts of features. Like our recommendation model for Europe cannot use this feature because of this compliance issue. So that's where we've seen the most interesting things. I think on either end of the spectrum, on the single user case where it acts as a feature-aware version control organizational tool, and on the enterprise use case where you kind of build on top of the core abstractions of a feature to provide a kind of the right solution for your organization. So anyway, thank you. This is a lightning talk. I think we'll be doing questions on Slack. I'll be there. Happy to answer them. I'm on a panel after this, so I probably won't answer them for 30 minutes, but I will after, I promise. And yeah, Featureform repo's there. My LinkedIn's there. Feel free to connect to me and check out Featureform itself. Like I said, you can use it in local mode. You don't have to deploy anything. Thank you.
Thank you, Simba. And I don't know if you mentioned Featureform, it's open source as well, right?
It is open source, yes. So that QR code is to our GitHub repo for the open source Featureform.
Okay, brilliant. And you can stick around. The panel's starting now.
Perfect.
So you're on time. So we're actually on time. I thought we'd be a couple of minutes over. Let's get cracking. Sarah, are you here with us?
I am.
You are brilliant. Let me introduce you before we get started. So Sarah Catanzaro is the moderator of this panel, and she is a general partner at a venture capital company called Amplified Partners, where she focuses on investing in and advising high potential startups in machine intelligence, data management, and distributed systems. And the other participants in the panel will be Stefan Kravchik of Hamilton fame, Fabio Busso from Hopsworks, Ashin Thomas from Scribble Data, and Simber Kadar from Featureform. And I think that for this panel, it's a little bit different. We have actually 3 vendors of feature stores here. Makes a little bit, they maybe have a different view on the role of feature stores in enterprise computing, but I'm sure Sarah will be able to steer the conversation in the way that she sees fit. Okay, over to you, Sarah.
Awesome. Thanks for the introduction. I mean, perhaps just to get started, maybe we can do like very quick intros, kind of 30 seconds or so. I know that Simba and Achint, you just spoke, but for those who are joining, might be helpful. So Achint, why don't we start with you?
All right, sure. So like I said, I'm a data architect at Scribble Data. We are a feature store company. We help companies take data and get decisions out of those, and we do that by building sub-ML apps on our feature store.
Got it. Simba. you want to go?
Yeah, sure. Hey, I'm Simba. Again, hi, co-founder and CEO of Featureform. And yeah, I come from a practitioner background, so I know what it's like and why you would need a feature store.
Awesome. Stefan?
Cool. Yeah. So Stefan Kravchuk. So I've been, I guess, machine learning, data science kind of area for the last decade, and most recently I was at Stitchfix for the last 6 years, leading the model lifecycle team. So I've done a lot of build versus buy. So maybe I'll provide the contrarian view for you, Jim, to keep this panel balanced.
Awesome. And Fabio?
Hi, everybody. I'm Fabio. I work at Hopsworks. I lead the engineering team at Hopsworks, and I've been working with a lot of our user and customers over time. So seeing both sides as a vendor and also as a user, as feature store users.
Cool. Okay, so let's dive in now. It's funny, in preparing for this panel with Jim, I think one of the questions I asked was like, okay, do we need to level set? Like, do we need to talk through like, what is a feature store? And he said like, no, like everybody is going to like know what a feature store is. And to me, honestly, like that is like a big accomplishment with regards to ML ops progress, because I don't think I could say that even, 5 to 6 months ago, like let alone like, a couple of years ago. But still, I think, there are different interpretations of what is a feature store. So I'd love to get started by discussing like, how is a feature store different than a database? And should feature stores integrate with other databases and other data management systems? So Simba, do you want to get us started?
Sure. I'd actually say most people have heard what a feature store is. I bet you if you had everyone here define a feature store, you'd end up with 15 different definitions. And the reason for that is there's a lot of different takes on the problem, because if you look around all the feature stores that exist, you'll find that most of them were built in parallel to solve similar problems, but by different people who actually weren't communicating, because at the time we didn't really have a term. We weren't like, oh, we're all building feature stores together. And so I think to answer the question, like the difference between a feature store and a database, I think there's kind of two problems to be solved. There's like the compute problem, like being able to handle streaming data, low latency serving, all that stuff. And there's kind of the lifecycle problem, the organizational problem. And I think that some companies try to take on both, in which case they kind of look like a database that is aware of the feature lifecycle. In our take, like we just completely push off all the compute work and kind of act as an orchestrator plus metadata. I don't necessarily think that there's a right way to do it. I just think that it is something that you have to think about as you're looking at and deciding how you're going to architect your feature store. If you want to create separation of concerns, or if you feel like they both should be kind of solved in one kind of heavier platform.
Maybe kind of piggybacking off of that, like, what do you think are the advantages and disadvantages of having, such separation of concerns? And others, feel free to chime in with your point of view too.
So I think this is the value of the separation of concerns. I think that the problem to be solved for most companies is not, hey, like Spark sucks. The problem to be solved is, hey, we have 20 data scientists, we have 400 untitled notebooks, each of their laptops. We're copying and pasting stuff on Slack. We have a Google Doc of useful SQL snippets. We keep track of things in a spreadsheet of what's in production. Like that's the problem that I'm kind of seeing and that I'm really kind of sensitive to and trying to solve. And you can solve that without having to replace the databases underneath it. You can kind of just act as an application layer to the infrastructure layer. So I think that's kind of the pitch, the value of creating the separation of concerns.
I think I agree on that. Like I think there is we often get like as a vendor like that kind of questions, especially at the beginning of like, how are you guys different from like a data warehouse, for instance, and stuff like that, right? So from our perspective, right, the data warehouse can be one component of the feature store. There are many more, and a lot of the feature lifecycle management is a key part of the feature store. And be able to kind of augment the data that is in the data warehouse, to be able to, from our perspective, enable like online use cases and like real-time low latency use cases that traditional data warehouse don't support. To be able to kind of deliver those use cases as well in a single platform, then becomes a big win for data scientists and so on.
Yeah, I was going to say like for me, from first principles perspective, a feature store is kind of a superset of a database, right? Kind of alluding to what Simba kind of said. You have to store data somewhere, so in that sense, you can use a database for that, right? But then you have all this other metadata, lifecycle management, and processes. In which case, then it really kind of depends on your how high level of a definition or kind of concentric circles of scope you want to kind of define as a feature store, and so then that relates to how it integrates with our data management systems, so lineage, data quality, etc. Right. So
I'd like to give an orthogonal view here, right? So a lot of our customers are they don't have even one data scientist, right? So they probably have someone who's looking at some data engineering, but they don't talk about features, they don't talk about models, right? But they still have a lot of data that they want to use, that they want to leverage. So think about fintech folks, who are probably 5-6 years old. So they have a lot of data, right? They do a lot of money transactions, but they haven't started building their models yet. They haven't started doing all of this data pipelining work, and they have a lot of so the kinds of problems that they want to solve are humans making decisions on the data that they have, right? And which means that this data needs to be processed, managed, transformed in the same ways that you would do when you're building your ML models, when you're building your ML systems, which means that you need to have lineage, you need to have guarantees on, okay, this data set is updated every hour, and you can trust that it's transformed the right way. So when you talk about feature stores for them, right, they may just want their data delivered into a SQL database that they have, or they may want it dumped into an S3 store. But when they think about a feature store, they are more concerned on the feature than the store, right? So there are these two aspects. There's the feature management, and then there's the store, right? So they're like, okay, we don't want to kind of integrate with anything else. Give us something that would kind of talk to our stores and help us manage this life cycle of features, but not from an ML point of view. I hope that's coming across. Yeah.
Yeah. So I mean, it seems like what people are suggesting is that like a feature store may be a database, but that is kind of not enough. There are these additional capabilities that you would want on top of a database, whether it is some of the kind of like workflow oriented features, or kind of additional like performance related capabilities. So I think like perhaps we can agree though that like a feature store ought to be integrated into the rest of your data infrastructure, and that like presumably like a feature store is not going to be like the only database that a company ever uses. One thing that I think we see more and more right now is that like there are these two data stacks that are emerging. One that often like kind of hinges upon like the cloud data warehouse, and that like frequently powers analytics, BI reporting, et cetera. Another that might really hinge upon the feature store, and that supports the development of models and ultimately ML-driven applications. Do you think there are ways for feature stores to kind of better unify these stacks? Since it seems like if they continue to grow independently, it'll just breed more complexity. Fabio, do you want to get us started?
Yeah. That's actually, I think that's actually a very interesting point, right? See, feature stores don't exist in isolation, right? They obviously need the source of data coming, from data warehouse is one. You also have streams, you also have data lakes and system of records and so on and so forth. Our approach as a platform, as Hopsworks, is to be able to kind of integrate both worlds, right? You try to bridge the Python ecosystem, and whether it's like, all the model building frameworks like TensorFlow, PyTorch, and so on and so forth with the underlying data. And the way we approach this problem is by exposing a Python API to the users, so allowing user to kind of, allowing data scientists to be able to write their Python code like they were, dealing with like a small set of data. But under the hood, we just take that like computation, we transpile it to a SQL, and we run it on the different data sources, whether it's a data warehouse like Snowflake or BigQuery or anything like this, or whether it's something stored on S3, and then we take that, we unify everything, and give it back as a pandas data frame. So from our perspective, coming back, I think there's definitely like this divergence going on. I think the feature store is a good place for bridging the gap between what's the like data science world and what is like the data analytics world. And you, as a feature store, at least from our perspective, it's allowing you to kind of enhance what's the data warehouse. Like, so oftentimes like our customers come in and say, okay, well, I have all my data there, but then, when I'm building a model, I want to see all the history, right? So I don't necessarily want to keep the history, the entire historical data on data warehouse, because it becomes too expensive. So I want to dump in something a little bit cheaper, like an S3 bucket or something like this. But I want to be able to manage in a single way. So from that perspective, you need to be able to be flexible and be able to accommodate all these kind of use cases and so on.
I wouldn't say that like a feature store is a superset of a database. Like in our case, we don't even store data. Like we store metadata. So I think that like the analogy I like to think of is like, you wouldn't call like Terraform as like a whole new player in the cloud space. It's like a whole different problem, which is the kind of maintaining, iterating on your infrastructure, kind of infrastructure as code. So it's lifecycle problem. So I guess I have a different take here in that I just think they're just completely tangential. I mean, like as an example, we charge per seat, which if you go to any like compute or database, they don't charge per seat. So when I look at kind of what's happening in the data space and other databases and other kind of people in the ecosystem, I just see it as a tangential issue, which is people trying to solve a whole different problem, whether that be making it easy to handle tons of data, making it easy to handle streaming data, et cetera. But it's not a feature lifecycle problem that they're trying to solve.
Maybe kind of like clarifying the distinction, though. I think there are times at which we've talked about feature stores. There are times where we've talked about kind of like feature management systems more broadly. Like, do you believe, therefore, that kind of the feature store and the set of capabilities that you just outlined ought to like integrate with other databases, like, or are feature stores kind of totally separate?
I think they should integrate. And that's like the whole virtual feature store concept we came up with, is kind of trying to give a name to that idea of they're just two parallel problems, two different axes you want to solve.
I do have a comment on the virtual feature store, to be honest, a little bit. From my perspective, like, again, that's something, I mean, we obviously, every customer is different, every use case is different. Like, the tendency is to, like, especially if you start building large, like, a lot of people start with, okay, I'm gonna build all my features as a table in data warehouse, right? I don't even care about like feature store. I don't even care about like my data management. Just gonna dump everything there, right? Then those tables start to grow, and then you start having to backfill data, and then you have to start to add additional features and start like you start basically managing that table as it was kind of a feature store. And so on and so forth, and then that's where they look at like how to augment that like table on data warehouse with additional capabilities, allow the track like history and changes, and allow to backfill data and so on and so forth. And one big component from at least our users is the bill in the data warehouse at the end of the day grows quite a lot if you keep a lot of history. If you start like querying back and doing like point in time join, start joining tons of tables, looking back a lot in the history and stuff like that. So all these things then becomes like a point of concern. where it makes sense to, offload some of the data outside the data warehouse, use the data warehouse as a source of truth, and then, augment this, transform the features, and store them somewhere else. But again, that's two different approaches. I can see a simple point. Just want to make a different argument there.
I mean, I guess to Sarah's original question on like the SQL centric versus Python, I think, to that point, the only way that you can make the two worlds coexist is by sharing data. And so in which case that data needs to live somewhere, right? And so in which case you do need to store it. Otherwise, if I'm pretty sure you can describe everything in Python that you can do in SQL. So my hope is that everyone just moves to Python, and so then SQL goes away. But otherwise, I think, features are a superset of anything that you do with metrics. So it is true, at least it was the case in statistics, that metrics can be features, but not all features are used as metrics. In which case, it potentially could be a one-way relationship where you are just kind of, to your point, Fabio, is that rather than things in the data warehouse being the source, you then push them into the feature store for people to use in features, and then people can then model and things live on that way.
Yeah. I think it's interesting also to perhaps like ask the question that like in the situation that you described, Fabio, where kind of you outgrow the data warehouse as a backend for your feature store, it is kind of the right solution to build a database or adopt a database that is kind of like purpose built and tightly coupled to your additional feature store capabilities, some of the workflow things that Simba discussed, or is the real answer just like not the cloud data warehouse, but perhaps some other database? Put differently, like, do you believe that you need a database that is purpose built to be, the backend for your feature store, to be the store for features?
But at this episode, we don't have like a general like a purpose built, right? Like from our perspective, it's basically Apache UDFIs on S3 bucket. That's the at least for the offline, what we call offline feature store. So for mostly batch use cases and so on. There's one additional point that's not kind of part of this conversation, right? What do we do with the online data, right? How do we handle data that needs to be fetched, like with millisecond latency, but also how do we handle data that needs to be refreshed with that level of latency, right? So if you have data on traditional data warehouse and stuff like this, that kind of database doesn't really support these use cases. So you need to at least move it out of the data warehouse, make it available somewhere else where for that to be queryable by models and to be able actually like usable by models. So the online part is also like a critical component, I think, of like how you think about feature store, how you think about patterns and building models and delivering those models.
I think one reason the feature lifecycle is hard is because, like Fabio was saying, data like kind of is scattered. Like a feature doesn't exist in one place. The feature exists in S3, exists in Snowflake, it exists across a ton of queries that are maybe orchestrated by Airflow, exists in Redis for online serving. And it's your job as a data scientist to kind of make all those things work together and keep them in sync. So I think that is correct, but you can't just use a data warehouse for everything. And so you do need it in a lot of different places. I think then the question becomes, do you want to build a better purpose-built Redis, or do you want to just use Redis, or a purpose-built Snowflake, or just use Snowflake, or whatever? So I think we're saying the same thing. I think one difference is we decided not to build anything to build a better Snowflake, build a better Redis. We decided to just use what's out there and let those vendors solve their problems. And we'll just kind of piggyback on that.
I think one thing that has arisen in this discussion now is kind of the differences in the requirements for feature management when you're building online versus offline ML systems. I'm curious to kind of get the panelists' take on these. How do you kind of see the difference in both architecture and technical requirements for these? And then relatedly, should we be implementing features at least twice or only once? Stefan, do you want to kick that off?
Yeah. I mean, good question. I think, part of it, I mean, in terms of the use cases, right? So with offline, Versus online, you kind of have different use cases. So with offline, not only we doing offline prediction, but you're also trying to surface and facilitate offline development. So that is, adding features, so backfilling things, and, training models, you're tweaking feature sets and things as you're developing, then potentially predicting with them. And then on the online case, it's the view of features that you need is pretty much only the latest features. Whereas in the offline case, you need kind of all points in time, because that's, you're going to create your training data from that. So I think, with those two kind of main use cases in mind, like for me, the main requirements differences is one, with online, you're only really managing the latest features, so that can actually be simpler than on the offline side. You're potentially also managing different SLAs. So then there's kind of, some people view the online store as the cache of kind of the latest view of the offline store is kind of one way to think about it. And so then they use a different technology to store it. So they're not going to S3, for instance, which the offline store does, but maybe, it goes to Redis, as kind of simple saying. And then to your latter, I guess, point was on kind of definitions. So invariably then through the SLAs, and when you get updates, like then there's the whole management and the process management of like, well, how do you update features? How do you add them? Ideally in a golden world, you can write a feature once and it runs everywhere. So, something like, Apache Beam from Google is kind of meant to kind of help with this, right? Where you write a transform once and it can run in batch and streaming. You don't have to manage it. But I think, in most realities, people end up at least implementing things twice. So one in Spark and then one in Flink. And so those are at least the three main points for me. Otherwise, versioning and lineage and data quality, I think, are all the same. But otherwise, yeah, it's just mainly driven by the different use cases as to like how the different management kind of needs differ.
There's a related question from the audience, which is, if you rely on existing data infrastructure, how do you think about the need for two different pipelines, one to support batch backfill and one to support online streaming computation? So certainly related to your response, but
not an easy question to answer. I think, like if you've been around and you've been doing machine learning for a while, you invariably have like calcified kind of infrastructure. The only way is to push things into a pipe into Kafka and then, push things other way. If you don't have CDC on a database, like, you have to do a bunch of, Lambda architecture to kind of join things up at the end. So I think, yeah, happy for the other panelists to jump in to see what they've seen, but yeah, like it's not, there's no simple answer there. Invariably, you probably end up building two things.
Yeah,
I mean,
sorry, go ahead. Okay. Yeah, I agree in that, yeah, I mean, so online and real time kind of are their own beasts, right? You need to have a lot of pieces in place to make sure that you can trust the data that you have online with what you're building offline. So, even if we don't look at something like, even if we don't look at ML, right? If we don't look at features that you need for doing inference on your model, let's say you have some data that that's powering a dashboard, right? You can build offline snapshots of everything up till, let's say, the past hour, and then if you want your dashboard to reflect what's correct point in time as of now, you need to have something that kind of updates the delta from the past hour, right? So I mean that it's painful, and you need to have then two sets of processes that are doing that aggregation over the past window up to the last hour, and then something for the hour, right? And these are definitely different code bases, and sometimes different logic, sometimes different conditions in filtering and joining all of this together. So it's painful. I don't know what the easy solution is.
I think I'm pretty sure Hopsworks does this. I know we do it, but kind of having a single feature definition for both streaming and kind of handling backfill, all that stuff, I think is kind of one of the promises of a feature store, like having one unified definition. I think the problem with a lot of this is that there's a different problem, which is kind of unifying streaming and batch, which gets associated with feature stores a lot because the place where you tend to do that quite a bit is in machine learning. So it gets associated with feature stores. But it's kind of a different problem to be solved. And I think one way to do it is to solve it with the feature store, we've like managed to solve it. Probably not as good as could be done if we owned everything, but we're kind of hoping for the vendors. I feel like if you look at what Databricks, Snowflake, and some startups like Decodable are doing, they're kind of trying to bridge that gap for us. So we're kind of waiting on them to solve this streaming versus batch problem once and for all.
Yeah, from my perspective, right? I think Stefan was mentioning it earlier at the beginning. I think the way we see it is that the online problem is actually two different problems from our perspective. One is like retrieving the data, right? And then, the retrieving data as a given set of SLA, and you need to respect that. Then the question is like, how do you actually update that data, right? And depending on whether you have some daily batches that need to be updated, so you might pre-compute everything once a day and then upload it, then that makes it more easy to kind of keep the same feature definition across batch and online, right? On the other hand, if you have a streaming situation that you need to update the data in a streaming fashion on the feature store, then you need to have some Lambda architecture in place that allows you to basically take the stream and also every now and then dump it on the offline feature store. That's the way kind of we see having the same feature definition. And the reason I think the single feature definition is quite critical is that if you start having multiple feature definition, if you start having multiple features, then it becomes really challenging to keep in sync what's your model you've trained on and what's the inference that you're doing on, right? Then it becomes really challenging. And then at that point, you're basically back at the same state you were at the beginning, where you have a bunch of data in data warehouse, you have a bunch of data on online feature store, whether it's Redis, RunDB, or any other Cassandra or anything like that, and you have to make sure that they are in sync essentially.
So there was a follow-up question, like, should we be pushing for solutions that require us to only write features once? I think like implicitly, many of you suggested that, yes, we should. I think some of these kind of like design decisions, though, probably hinge upon like for whom you are trying to build a feature store and what their goals are. So I'm certainly curious to kind of hear the panelists' take on this, both more globally, like, are we building for model developers, ML practitioners, those that are building models and ML-driven applications, or are we building for like data platform engineers? And then, even perhaps using that example, like why do these things matter? And do the interests of those stakeholders diverge in a way that forces you to make careful design decisions?
Yeah. Yeah. Go ahead, Shiba. Yeah.
What I've seen is it's really interesting you mentioned this, because I noticed this a lot, where data scientists kind of hate lots of MLOps tools, and then platform engineers kind of shove them down their throat anyway. And so I think it's really important for us, especially vendors, to really be sensitive to like what data scientists actually want to be doing, what they want to use, and focusing on their problems too. Very different problems to be solved based on what you're talking about. A VP is thinking about different things from a platform person, from a data scientist. And it is kind of our job to make sure that everyone's happy as much as possible. So I do think that we think of building for the data scientist, and but the person who picks us and the person who ends up buying us and people who pay for Featureform is almost always on the platform team.
Yeah, I think I agree with Simba here. Every successful implementation we've done of Hopsworks is because data scientists are happy with using Hopsworks. If you don't get data scientists happy, someone might be willing to pay, but then ultimately nobody's gonna just build on. They will try to find some of the solutions and so on, right? So it's really important from a feature set perspective that you serve your data scientists to be able to be productive and to be happy essentially. That's the ultimate goal.
I have a orthogonal view here then. So the folks who buy Scribble's enriched platform the most are basically business analysts, business stakeholders, product users, managers, right? Because their use cases, their questions are always, how do I make use of this data? It's not how do I build a model. It's not how do I build my features better. No, I have this decision to make every day when I wake up in the morning. How do I do that with my data, right? So that's the question that they're asking. So yeah, that's different from what both Simba and Fabio mentioned.
Coming from Stitch Fix, our ethos was, we're trying to build for, tools for data science to be self-service. It's great to hear that the self-service thinking, I think, is, extending beyond that. In terms of, I guess, the ultimate goal for us was to try to design a single API, but that wasn't always the case because, I mean, if you have systems like, say, Spark and Flink, they don't speak the same SQL dialect, so someone needs to invariably manage things. Maybe they do overlap. Now there are systems and teams who are trying to make that, but then SQL doesn't do everything, so then you bring in Python, so then invariably you are kind of, I guess, to the original question, should you be pushing for one or two? I think ideally you shoot for one, but it really depends on your kind of SLA and use case, since I do think in some instances you can get by with one definition if you do it for and you're writing SQL, which is very, I think we can largely all agree that's mostly accessible to data scientists. I think I would pose more of the question is actually, is SQL or Python going to win out as the ultimate kind of API for people to write features? That's kind of that's the thing that's on my mind when I'm kind of actually thinking of who we're designing things for.
So we're going to have to wrap in just 1 second, but I think that is a great question to end the panel. This is obviously like a very contentious question. Certainly, I feel like every couple of months on Twitter, at conferences, et cetera, you hear like this heated battle between like SQL enthusiasts and Python enthusiasts. So I'd love to hear any hot takes before we wrap.
I think, go ahead. Sorry, go ahead.
I said, yeah, 1 second. Neither of them are going away, so you just have to play nice with both. Art's gonna still exist too. Like, doesn't matter what we care, what we think. Notebooks too. People are gonna want to try deployment in production. Like, this stuff is gonna continue to happen for many years to come. So you can say whatever you want and be a fundamentalist about something, but it's not going away.
Yeah, so SQL is being used for more and more things that people want to do, but then there's always things that you can't do and that you have to go back and use something. I mean, you have to use a more expressive language, so they're not going away.
Yeah, I mean, I guess my hot take is, I think, ultimately, I think Python, especially there's works on, essentially making it easy enough for people who, I think, SQL people pick up SQL because it's, pretty, readable. But I want to say, if you're coming from a spreadsheet, I want to say Python, if you can simplify it, might be a easier kind of switch rather than writing SQL. But again, to the simplest point, the SQL is very established. It's not going away. I'm likely going to have to, support both ecosystems. But my hope is that as a developer, we can build an experience where people don't have to switch too much if they don't have to, and then it's very segmented by end user and use case.
Yeah, that's also our philosophy, right? Be able to support the people and with the tools they want to use. And if data scientists want to use Python, then we need to provide a way for them to be able to use Python all the way, build features, deploy features, and so on and so forth. So, but again, I as well think that SQL, it's not going to disappear. It's just a matter of I go to Python ecosystem, welcome to be able to access wide array of data and features.
Awesome. Well, I think we are a little bit over time, so I'm going to wrap with that. But thank you so much for the interesting responses. I think this brings it back to what Simba was saying before, which is we have a lot of knowledge gleaned on feature stores, but still lack kind of a common definition, and for good reasons. There's still a lot of heterogeneity in terms of what teams do and how they think.
Thank you very much.
Thanks, Sarah.
Thank you.
To everyone on the panel, thanks, Sarah, for chairing the discussion. And with that, we're going to continue. And the next speaker is Gaurav Rao. And Gaurav Rao is the Executive Vice President and General Manager of Machine Learning and AI at AtScale. And AtScale are the semantic layer company. So they're focused on leveraging a semantic layer to bring applied AI offerings to the market. Prior to AtScale, he was VP of product at a deep learning startup called Neural Magic. And we're going to hear about some of the interactions, or let's say the overlap between the feature store world and then the semantic layer and metric store world and the data warehousing world, I hope. Can you hear me, Gareth?
I can. Thank you, Jim.
Great.
Can you hear me?
Do you want to try and share your screen, and then we'll see if we're good to go? You're very good. Okay, over to you.
Perfect. All right. Let me put it in the slideshow. All right. Provided everyone can see my screen okay.
Yeah, perfect.
Great. Thanks, Jim, for the introduction. And thanks to the summit organizers for having me here today and allowing me to speak. As Jim mentioned, I'm the EVP and GM of AI at AtScale. And today I have the opportunity to talk about how we can power enterprise feature stores with a universal semantic layer. And having the opportunity to listen to the last few minutes of the panel discussion, you know, this choice between Python and SQL, I'm hoping we can actually address some of that in this conversation. And effectively, the TLDR is you shouldn't have to choose, you should be allowed to do both. So with that, why don't we jump right into the conversation? So the first slide I like to use just for market context and awareness, it's probably a slide you've seen in some way, shape, or form. And, you know, it often gets pitched as, you know, competitive advantage, competitive differentiation comes from being up and to the right. And while I completely agree with that, I like to tell a slightly different story using the slide, you know, and that's, I believe, mature technology companies have holistic views of their data, right? Whether it's from reporting to analytics, to advanced analytics, to machine learning and AI, it's all about better decision-making, which means, you know, how do we tie, right, the data across an enterprise to business processes, business workflows, and applications. And the real question and the real opportunity comes to be, how do I leverage this data to address the existing as well as some of the new workloads we're starting to see as a result of all of the technological advancements we've seen in machine learning, AI, infrastructure, right, over the last 5 to 10 years. We've heard it throughout this conference, right? Batch processing, database, you know, EDW, these are known concepts with structured data. We've heard more about online and real time, right? You know, think about recommendation systems and recommenders and sort of the advance we've made, right, in that system of engagement and the types of SLAs that it demands. And with that is coming new data types as well, right? We have the structured, you know, data sets, the tabular data sets that we've known to come and love in machine learning and AI. And now we're starting to see more semi-structured as well as unstructured, you know, text, as well as image and video. And then coming to how we actually run these systems, right? Am I running this on-prem, in a VPC, on bare metal, serverless? Am I running in the cloud, right? Am I running at the edge? Pulling all of this together and then figuring out from an enterprise standpoint, how do I maximize my efficiency within the operating constructs that I have? And those operating constructs are typically time, investment, and skill. And the reason why I start with this is as I go to the next slide and we dive deeper into machine learning and AI, right? We kind of see a tale of two numbers. And the two biggest numbers that I take away are spend is up, right? So regardless of, you know, the pandemic, the economic impact we've seen, spend on machine learning AI has not only decreased, it's increased, right? IDC predicts by 2023, we're going to hit 500 billion in global spend. Yet the more startling number, right, by Gartner in a study they did about a month ago is only 1 out of 2 machine learning models make it into production. And even fewer AI projects realize value and see success, right? So this is a pretty big problem. Right. So in this, you know, advancement of technology, and like when you think about machine learning AI, you know, we think of the advancements in training machine learning models, you know, via AutoML platforms. We see the improvement on deployment and inference and sort of the metadata that we can capture with ML ops. right? And even feature stores. And now the question we have to ask is, how do we ensure success, right? And how do we get impact, right? Where business decisions are happening with the investments we're making across the technology stack. And I feel that there's still two areas that are hindering ROI and scale out. They're still complex, and they, meaning the ML, I'll say, environment and ecosystem, and there's still lack of business adoption. And if we start with the complexity point, this is why I love the summit, and I love what we're actually talking about here around feature stores, because I believe personally, feature stores really help navigate a pain point that every developer is having today, right? How do I build and find and discover and use relevant features, right? As part of my ML pipelines, right? And I think when we think about investment in ROI, where we come back to the second point, right, which is about business adoption, what we need to be thinking about in the complexity point that I just mentioned is, how do we now populate? Let's assume a feature store is in place, the feature store decision has been made. How do I populate that feature store with relevant, right, reusable assets? Those assets can be data sets, they can be features, you name it. But is there a connection point to the business that can actually drive the adoption of a feature store and the reuse of these features? And now on the second point around business adoption and sort of how do we get more of the economic benefit and the realization of the investment, right? Whether it's a feature, whether it's a machine learning model making a prediction based off of features, right? Unless that output of the ML lifecycle, the training, the deployment pipelines, when we go back to that decision maker or the point at which a decision is being made, if that's happening, and most likely is happening outside of an ML tool, then that business user needs three things, right? They need that AI output to be relevant, meaning at that business moment, right? So think of underwriting, application processing, interest rates change overnight. I know it's not the best example, but the point being, if interest rates change overnight, how do I know that the machine learning model the very next day is consistently applying the right features to making the best decisions, right? Maybe I'm biased towards certain age groups, certain populations, right? All of these things need to be accountable. The second part is a business user needs consumable and consumer-friendly AI. So assuming this is happening outside of a ML environment, they need to be able to understand these artifacts in their existing tools, right? So that could be a BI tool, that could be Excel, Tableau, you name it, right? So how do we make this more consumable at that decision point by that decision maker? And then finally, how do we make this AI output more explainable in business terminology, right? So that becomes now the opportunity. And let's see if we can actually handle, right, both the complexity point as well as the business adoption point with a feature store. So that leads me to my next slide, which is let's rethink what a feature is. And I would assume most of the constituents in the summit and on this call understand features from a machine learning standpoint, right? We're all familiar with getting our data sets, building our training data sets, establishing our validation data sets, going through data prep and EDA, going through the feature engineering, feature selection process, right? Tuning, training, retraining, deploy, retrain, right? Depending on your SLAs and so forth. And sort of that life cycle that feature is going to go through. What if we started to think of a feature differently, right? We know that business analysts are often using tools of their choice. What if we started to think of a business metric as the input for a feature, right? Measures, dimensions, hierarchies, things that a business user is using and reporting against, almost every day, every week, right? These can translate to categoricals and numerical features on the data science side, but it's first recognizing that business vetted actual, right? The thing that's already being used in a BI tool can that become consumable for a developer? And a great example of this is, think about the number of data scientists who are building, I'll call it a forecasting model, right? That requires some time relevant measure or time relevant hierarchy, and they need to know fiscal year or calendar year, right? How the business defines a fiscal year and how a data scientist is training their model thinking of what a fiscal year is could be very different. Are they both using ISO? Are they using broadcast? Are they using 445? Are they using a different calendar variation, right? All of that is important because we know that the business users have already defined their calendar structure, right, from the metric store that they've built in their tools of choice. And now the question is, how do we build and share that consistent view with a developer who's in a different ecosystem, different pipelines, right, but wants that consistency? Because if they don't, right, and I've seen this in practice, they go build and train that machine learning model only to find that their time, their time relative measures are off, or their calendar year is off, which skews their predictions, right? So now the question is, if we accept and understand that the business is using various metrics and have these metric hubs, can we build a layer, right, that brings that metrics hub view together with how developers in the machine learning and AI world are commonly building features? Can they intersect, right, knowing that they're in different pipelines, different tools, and different environments? And is there a way to manage this? So if we go to the next slide, this is sort of where this comes together with the concept of a semantic layer. And in case you're not familiar with a semantic layer, the way we've seen it defined in the industry is it's a logical view of your data, right, that sits between your data source. So think your database, your data warehouse, your lakehouse environment, and your consumption tools, right? So most commonly, the consumption tools are, your BI tools. And provided that the semantic layer can understand the dialects, right, which are varied, DAX, MDX, SQL, XML, as well as understand the underlying SQL of that warehouse, right, you can provide this, I would say, system of record, provided you can also add Python, right, as a connector within this consumption tool ecosystem. And what I would say a semantic layer provides are sort of three things. The first is a consistent view of the data, regardless of what's connected to it, right? So if I'm defining business metrics in a metric hub through my BI stack, right, I'm going to have a view, right, of these measures, these dimensions, and these hierarchies. Similarly, if I have a semantic layer and I have a Python connector to that semantic layer, I should be able to define through a feature store and feature views, right, all of the relevant features and simultaneously connect that to the semantic layer. And by doing so, right, I've now built consistency, right, in the definitions. And I'll talk a little bit about how you can extract as well as write back into the semantic layer to maintain that consistency. Now, the second attribute I would say of a semantic layer is, in addition to having consistency amongst the connections, it needs to be controlled, right? We're talking about data access. So it needs to be governed and secure, but it also needs to be discoverable. So if I'm coming in from a BI tool, if I'm coming in from a Python connector through a feature store, an AutoML platform, I need that same level of, authentication, user access, governance, lineage, transformation metadata. I need all of that, right? And I need that to maintain, again, consistency between these two environments. And then finally, a semantic layer should also be performant. All of this goes out the window if my query speeds are slow. So in addition to having consistency and having control, the end-to-end query performance should actually be accelerated with a semantic layer because of how it understands the dialects of both the underlying warehouse SQL as well as the connection dialects between Python, DAX, MDX, XML, you name it. So now let's try to better understand how we can apply a semantic layer concept, right, to a feature store for business impact. So this is a little bit of I'll say a messier slide, but I want to take a step back. If we look at it from left to right, what we're going to show is I have my data warehouse constructs on the left-hand side. It could be a lake house, and I have all of my relevant data, right? So I have my application data. It could be ERP, it could be finance, HR, sales. I may be using second-party partner data. I may be adding third-party data providers to the mix. Now, the next logical step that I want to do is from these data, this data store, I want to semantically build a data model, right? So this is where we build conformed dimensions, conformed hierarchies, and conformed measures, right? This is that logical view that we're building off of the data without having to move it from the data warehouse or the underlying lakehouse environment. Now, one of the byproducts, as we're all familiar with data prep, ETL, feature engineering, one of the byproducts of building this semantic model is I'm going to start to understand what relevant attributes or features the business are using. And if there's a way within my semantic layer to start to manage and organize these features, right, it becomes very powerful to the tools that are now connected. So let's assume I can semantically build a data model. And now I have a rich environment of business vetted metrics and dimensions by which to work from. Now, as we've heard throughout the day, Python and SQL are very important to different developers. So in this case, and in this example, we're showing through a Python connector into the semantic layer, I now have two different ways to consume, discover, publish, and also write back into the semantic layer. So I can start by immediately consuming these business vetted features in a feature store of choice. I can also use them directly in an AutoML tool in conjunction with a feature store. So the primary example I like to give here is, let's say I've defined a set of managed features as a byproduct of my semantic model. I search and I discover them in my feature store of choice through a Python connector. We know that a data scientist that's building and training this machine learning model are not, these features that are coming from a semantic model will not likely be enough. The point here is they're actually starting with something the business is already using, and then they can augment. So through their, parameter tuning, through their feature selection, through their feature engineering, let's say they extract a few features and they also define 4 or 5 new relevant features that they need as part of this machine learning problem that they're going out to solve. They have the ability to now write that back into the semantic layer. Now, doing so, again, immediately, provided you have the performance, right, becomes queryable in any of the connecting tools. It could be a feature store, right? So now I have the updated feature view of the most relevant features. It could be a BI tool, right? So now coming back to the business adoption, I can very quickly surface, right, relevant features that a machine learning engineer or a data scientist are using as part of their training and deployment pipelines that have been written back into a feature store in a semantic layer, and make that consumable, right, in a connected consumption tool of choice that an analyst is using. And then more importantly, in conjunction with a feature store, if a semantic layer is involved, you also get that added security and governance, right, based on anything that's been written or consumed or extracted from the semantic layer. And with that, what I wanted to end with is actually a practical example. So, I wanted to keep this more conceptual on, what's the problem? How can we sort of bridge this gap between how developers are building in their AI pipelines, how business users are consuming in their pipelines, use both the feature store and the semantic layer as a mechanism, right, to build a broader definition of the view of a feature, extract and publish back into a semantic layer as well as a feature store. And now let's think about a very, very common business problem, business forecasting. And what I've done here is we have code snippets. So in the back, I've used AtScale. So AtScale is the company that I work for, and we've built a universal semantic layer. So what I'm showing here is behind the scenes, we've semantically built a model. right? This happens to be for product inventory for a large retailer. And data scientist is coming in and they want to start by quickly understanding what are some of the relevant features that are available that the business is already using. So in a single line of Python, they're quickly consuming and discovering a number of different features. In their tooling of choice, they're adding their time hierarchy, and they're very quickly making this a time series model. And then as they're going through the training pipeline, in this example, it happens to be a scikit-learn. We're just using an open source model, but it could be any AutoML tool. It could be a AI end-to-end AI platform as well. They're going through the process of assessing performance and figuring out what features they want to land on. And I should have mentioned, they could have also started from a feature store here. But in this example, what I'm going through is they've gone and done the hard part of picking out relevant features, going through that training iteration, and now they've determined what features they want to save, and they do so by publishing this back into their feature store, right? So very quickly from a reuse standpoint, the next data science teams can very quickly consume, right, all the relevant features that happen to be used for this forecasting model. But more importantly, the more they're interacting with the feature store, the more they're also interacting with the semantic layer underneath, because that's how we're populating that feature store with business vetted actuals. So hopefully this kind of takes home the point around, we can actually start to bridge, both the metric hub, right, that we've all heard through, headless BI and self-service analytics, with how developers are building and training and deploying machine learning AI, and giving that, connector to write and extract artifacts from that process, and all while doing so, maintaining consistency, performance, and making this more consumable, either for, developers who need to build and train and scale out their next model, or that business developer or business analyst who's making a decision.
So Gaurav, we're over time, so I'm gonna have to thank you there. Thanks very much. Very fascinating talk. We know there's huge convergence going on here, and it'll be fascinating to see how this plays out.
Thanks so much, Jim. Thanks for having me.
And there may be questions on the Slack, so you can pop over. Okay, we're going to move on. So it's Lulu Liu, who's the data science manager at dotData. And he's previous experience as a DataOps engineer at Tamar, holds a PhD in elementary particle physics from University of Michigan. Over to you. Can you hear us, Lulu? Can we hear you? We can see your screen.
Hello, everyone.
Great.
Can you hear me?
Yeah, we can hear you. If you go slideshow, we're good to go.
Sure. Okay. Hello, everyone. So I'm here actually not to tell you about another feature store implementation, or even how we actually use feature store. I'd like to take this opportunity to introduce to you a tool that we're developing at dotData that can be used to kind of automatically generate features, so you can feed your feature store. So I think we have heard people saying, like data is the new oil. If I write along this analogy, I think is to machine learning, development is actually the features that is the fuel here. And in that sense, I think, in my opinion, feature store is like the gas station. You drive up to it, plug in the pump, you get features flowing out of it to power your machine learning development and production. But where does this gas come from, right? I think it's just like, we have the oil industry to drill and extract, the crude oil and then turn them into the gas. We have this feature discovery process. And traditionally, this has been done mostly manually by data scientists. And we actually have a technology that can automatically do that. And I would like to show you that. Let me start with this example data set. So this is from a bank. This is the open data set. You may as well look at it already. With this data set, I'd like to build a machine learning model to predict if the loans are going to default. And I'd like to make this prediction at the time when the loans are applications are made. So of course, I have the loan data, the loan table, which contains this default status, which is the variable that I want to predict. I have the account information, the clients associated with these accounts. and some transactions data here as well. For a human data scientist, the task of preparing this data set to be used for machine learning can be a quite tedious one. You need to join all these tables together. You need to select the columns you want to use, find out, the right aggregate functions and the transformations and all that. With dotData, we can automatically do all that. So what is involved here is, there would be some basic cleansing. For the multi-table transformation, we have the auto joins and aggregations. We explore temporal relationship among the different tables and columns. Of course, the usual, encoding stuff and some more sophisticated neural encoding and wavelet transformation and temporal data set. So in the end, right, starting from these multiple tables as the starting point, you get a flat feature table, and the features are selected solely based on statistical performance. So there is no kind of domain knowledge to actually also bias you here and limit the scope, because usually data scientists, given the input from domain expert, you can define features given what you already know, but there could be also features to be discovered well you don't know yet. Okay, with that, let me actually dive into my example implementation, which we have here on Databricks. We do support other platforms as well. We have this Python interface product. Essentially, it's the package where you can install, which you can install into your existing Python environment. For this example, however, we have the data stored in Delta Lake. We would load them as data frames and pass it to dotData. We would run a Spark job to discover the features, and then we can save those features into the Databricks feature store. Okay, so I would like to show some quick examples of the code snippets. I don't have a lot of time, but for the environment setup, I have this package imported as DDPy. So this is not pip installable yet. We don't have it open source, so you have to contact us if you want to experiment with it. So I'm loading all the tables I showed earlier here, all the 8 of them. With that, I also have a configuration builder object to help me put all this together. So I'm specifying here, the target table. And my target variable would be this default column. More importantly, I'm adding all the tables each as a so-called data slot. So all the features will be explored from these as the source tables. And I also need to specify how they connect to each other. So here my target, the known, are connected on the known ID to the account table on the account ID. So these are all very straightforward. Maybe the only exception here is the connection between a target to the transactions table, because the transactions are temporal, by nature. So apart from matching on this account ID, I'm telling the job to look for entries, information for the past 6 months up to the point the application is made, and this is done by matching the 2 date columns from the 2 tables. So with this configuration, I can run my design features job. So it goes through a series of tasks. It would do the joins, extract the relevant records. Given the join conditions, we would explore the feature hypothesis for you and do the feature selection. So in the end, for this example, you can see that we have about 100,000 different feature hypotheses looked at. And then in the end, we selected 49 of them. And I have the list of feature definitions together with some statistics on the performance. So let me just take a close look at this first example. It reads the count of records that satisfy the balance below 4,192 within the past 6 months after the operation of a remittance to another bank. So this is basically looking at the 2 tables, the target containing the target variable and the transactions table. They are joined on this account ID, and with the date, falling into this past 6 months window. And we're essentially looking at the balance numbers after each occurrence of remittance to another bank, basically sending money to another bank account. And we're counting how many times that have happened that after this remittance to another bank, that the balance has fallen below this threshold. So I think this is kind of quite straightforward. This is found also statistically highly correlated to the target variable. Another one here, looking at the temporal change patterns, of this record account within the same time window. So all of our features are, defined in this manner, where you can, basically read them as plain English and try to find, the meaning of it. Okay, with all these feature definitions, I can then generate the feature values for any new data set. So here I'm loading another 8 tables. I map them, the data frames to the data slots that I have defined earlier. Then I can submit this generate features job to create the feature values for this new set of tables, and you can see the feature values here. So this is returned, as a data frame, so I can save them to my feature store. So here I'm using just the Databricks feature store, pushing this data frame to be saved. Okay, with all these features, feature values saved, then as a machine learning developer, I can then query the features I want from this feature store, and then build a model using my favorite machine learning library. So you can do that quite easily. Okay, so let me.
So do we have time to wrap up, Lou, or can I add a time? Yeah.
Yeah. So let me just wrap this up with this slide. I think this is kind of the paradigm we see with this automated feature discovery component. You feed the data into the feature discovery. After some validation, you can then register the features in the catalogs, materialize them in the feature fit tables, and the features will be ready to be served for your machine learning building and scoring tasks. Okay, so I didn't have time to kind of show you more details, but if you're interested, please feel free to reach out to us. We would love to jump on a call and show you more of our tool. Thank you very much.
Thanks very much, Lulu. And you can ask Lulu questions on Slack. He'll jump over there, I'm sure, after the talk. So the next speaker is Ravi Suaj. Ravi is the founder and principal architect of Open DataOps Foundation. He leads the vision and community efforts to build an open source, self-service, modern data platform. Ravi, are you there?
Yeah. Hey, thank you.
Great. We're running a couple of minutes after, just so everyone knows, but we're good. Go for it.
Okay. Yeah. Thank you, everyone. Thanks for having me here. So today we'll be talking about feature engineering at scale with Dagger. And before we move further, a bit about me. So my name is Ravi Suhag, and I'm basically the founder and principal architect of the Open DataOps Foundation. So let's talk about what is feature engineering, right? And in simple terms, according to me, it's the process of transforming raw data into high quality input signals that you can feed into your machine learning models. And if you look at overall feature engineering in an ML pipeline, so the way it starts is the raw data. You have the first raw data, and then you go through a transformation, and then you put it into feature store. And that is the part I kind of call it as like, I look at it as a feature engineering. And from feature store, you can kind of take it up to model serving and model training, right? So that's like high level overview of where the feature engineering kind of fits into the picture. Now, before we go further, like, let's talk about what is the need of feature engineering, right? So one, I think, is the better feature leads to better flexibility, right? So if you have good data structure for your models, then it makes it easy for you to kind of choose models among themselves. And better feature also kind of then leads to simpler models, right? So because it's easy to pick the right parameters in the right models. And overall, if you look at it, right, if you have a better and composed feature engineering done and you have right features, that basically results to better results of your models. And if you look at some of the feature engineering challenges, right? So one that comes to top in my mind is inconsistency between your training and serving data. So the data that you have during offline training when you're serving your models, and then the data that you end up having during the serving, which is when your models are live. Another one is like managing data pipelines. So you don't want your data scientists to kind of start doing the managing of the data pipelines overall, right? And you have like a large team that kind of taking care of that. Another one is scaling data infrastructure of it, right? So now you have a lot of these feature engineering pipelines going on. How do you go about scaling the infrastructure of it where you have thousands of jobs running? And especially in the distributed organization where there are many teams spread across the organization, it becomes very tricky that how that feature engineering overall is being done by different data scientists, right? Some have certain other tool to kind of to go about the feature engineering. Someone is using Flink, someone is using XYZ tool, right? And then standardizing that pipeline and that infrastructure becomes tricky. And if it is not standardized, then the maintenance of that becomes like more tricky. Last piece is that like real-time features are not just something I think it just comes out of the box, right? You need like skilled data engineers to put those things together. Like you need to have someone knowing how the streaming pipelines work, how the tumble windows and hop windows and those kind of features kind of work, right? And data scientists at times are not aware about some of those things when they are writing or computing their features. And that's where you need kind of the core data engineering or software engineering skills to kind of fill that gap. And the same challenges that we talked about, if we turn it into the goals of a feature engineering platform, they should be solving those challenges. And then first one that can be solved is with the unified processing of streaming a batch. So if you don't want to have different queries and different data across your online and offline stores, then you like the best way to go about is that if you have a same query and the same processing logic for your streaming as well as the batch sources. Second one is that you don't want your data scientists to go about and worry about infrastructure. Like to them, it is completely agnostic. They go about writing their logic and then forget about how it is being spinned up and how the jobs are getting executed and what are the SLAs of it, right? They should not be worrying about any of those pieces. And next one is that elastic infrastructure. You don't want, if you have like a batch, let's say batch feature, you know, if you have a batch job that is computing features and dumping into a store, you don't want infrastructure to lie down like after that job is finished. So you want to have the elastic infrastructure as part of your feature engineering platform. And I think this is still like if achievable goal, but like if you can have standardized and reusable way of how feature engineering is being done. One example could be is that if there is a same logic that is being used across multiple features, let's say computing S2 IDs from latitude and longitude, right? So you don't want all your data scientists to recompute or write that logic again and again. And you want some reusable ways to actually have those computations stored and being used by everyone. And the last piece is that I think you don't want any added skill for people to compute the real-time features. If they can do it into the standardized way, it's always better in productivity. So we at Gojek kind of have this Dagger as a platform, which we call stream processing made easy. And that allows people to basically transform, aggregate, and enrich data within ease of operation and reliability. So how Dagger works is basically it can pull data from multiple sources, your batch sources as well as your stream sources like Parquet, which is the batch source, or your Kafka, which is like your real-time streaming source. And then Dagger allows you to basically write your logic, test it, monitor it right there. And the deployment of that is handled behind the scene from data scientists, either on Flink cluster or on Kubernetes clusters. And then it can send the data to multiple sinks. One of those being our feature stores, but it can also send it to your streaming sources if you want to put it back. But like a lot of people, data scientists use it to directly send it to feature store. So how does that ML pipeline look like with Dagger, right? So you have raw data coming from events or microservice or warehouses, and then usually that goes into your event streams like Kafka, and then Dagger pulls it from Kafka, and then it puts it into your feature store. So your data now after feature engineering computations is into the feature store. And from there, your training and then deployment pipeline can go. And then once the model are serving the inferences, the same log can be pulled back into event stream, which Dagger can utilize for more monitoring and then other use cases that we will talk about. So if you look at a slightly bit into the architecture of the Dagger, so it has like first piece is the consumer one, where it takes care of the consuming the data. Then it has pre-processor concept. So before even people start to write their logic in SQL. And if they want to have some pre-processing done through user-defined functions or other ways, or they want to pull data from asynchronous source, they can do it in preprocessor. Then there is main execution where people write their SQL query for transformation or feature engineering. And then they can, if they want to do after that, if they want to kind of talk to some external service or do post-processing, they can still do that. Like enrichment and such kind of things can be are capable in that case. And then final piece, it sends the data back to your sink. So certain key features of Daggers are, one, it's SQL first. So it does not ask people to start writing a lot of custom jobs on using Flink or any stream processing framework. People can simply come and write SQL queries. Another aspect is that it's not just standard SQL. So you can extend that basically by writing your user-defined functions and then using those functions into your SQL queries. So if you have a very complex logic that you can't achieve directly into SQL, you can write it with Python or Java, and then you can basically enrich that SQL using that UDF. Another one is like stream enrichment. So what basically that means is that if you have let's say message coming from Kafka and you want to reference some external source with it to enrich your stream, simple example could be is that let's say you have a booking order coming as an event and you want to attach the pricing from a particular model with that event. You can do the stream enrichment, call that particular external source, attach the pricing with it, and then pass it to forward. Next is the self-service. So people have this complete unified interface where they can simply come and write their feature engineering job, and it asks for you what data sources you want, what sync you want to send, and it shows you all your logs, output results, monitorings if there is any exception, if you want to start and stop your job, or any templates, right? So entire processing or the job and then overall experience is packaged into the complete self-service platform. So for the people who, let's say, are not so fan of UI and then they have so many jobs kind of to manage, then like Dagger also provides a GitOps way where you can write a simple YAML file and then you can just do the apply, and then that basically schedules that entire job. And after that, if you want to monitor the logs, you can still go to the UI, but it allows you people to basically simply write a YAML and then start basically executing their stream processing job. Yeah, so I think why SQL, right? So in terms of Dagger. So I think what we realized is that when people or data scientists start writing their feature transformation logic or processing of that, 95% of the use cases can be easily covered in SQL. And then whatever 3 or 4%, whatever is left, people end up writing, basically data scientists end up writing the UDFs and then still achieve with it. So I think what it still covers the 99% of the use cases, but makes the overall process much simpler. It's much easy to reason about. And then in a self-service platform, what also allows it is that people are not going to come and write their crazy jobs and then consume all your compute power, right? They're still writing SQL, which is kind of Turing complete in a key way. Another main thing is like UDFs. So we provide Python and Java, two programming languages, and people can come and write there. So for example, here you are looking at is that there is a GeoHash UDF that someone has written, which takes 3 parameters like latitude, longitude, and then it converts that entire thing into a GeoHash. Now, once this function is written, you can write it into SQL, and then anyone can start using it. Now, once single data scientists write this function, it's available for everyone to start consuming. So another thing that we kind of achieve and then data scientists achieve with the feature Dagger is that data masking. So let's take example, you have the production data coming in, and now you want to train your models into staging and then deploy it into the staging. So you don't want the production data and PII data to go into staging environment right away, right? And that's when you're doing your feature engineering. So what Dagger allows you to do the data masking. So there is one transformer in that where someone has written, let's say this transformer is hash transformer. So you can specify which column you want to mask, right? So if I'm going to say that, okay, mask all the email IDs or mask all the phone numbers, while I'm doing my feature transformation, I can simply specify this configuration along with the SQL query, and then Dagger basically take care of masking it. What that allows is that people to train their data directly onto the production data, but still making sure that no security or no PII data or sensitive fields are exposed to users. Another thing that we talk about is like the Dagger feature provides is the hybrid data source. So what we've seen is that I think in our case, a lot of feature engineering was done on stream processing data, right? A lot of things are coming in event, and most of the online models are working on the stream data. But for quick feedback, people still want to process data from, let's say, last 5 months or 4 months or 6 months, like that, right? So in that case, what ended happening is that they write the batch query, let's say something on top of BigQuery, or let's say on GCS data, cold storage data. They write that logic, and then when they're basically deploying their model on production, they end up converting that query into SQL Dagger query, and then deploying their model for basically online serving. What challenge it created is that people are writing 2 different queries in 2 different mechanisms on that. So what we ended up doing to solve that problem is introducing this hybrid source. So what you can do is you're writing your SQL query. It's the same exact query for batch data as well as for your stream data. But instead of working on stream or batch, it can work on hybrid, which basically means you can take today minus 4 month data to today minus 10 days data from your batch source, like let's say Parquet source. And from today minus 10 to up to today and going forward, you can start consuming from Kafka in real time. And Dagger behind the scene take care of switching this automatically. As soon as the batch data is consumed, it starts to go into stream data automatically without people worrying about changing their logic or doing anything. They just have to specify these 2 sources. That's it. So as I think some of this I already talked about. So for example, in this case, people are simply specifying one source type is the bounded one, which is your batch source. And then type of this is basically Parquet one. And second is your unbounded, which is Kafka source. And that's it. And apart from that, everything else remains the same. Their query remains the same. And people are actually able to backfill their historic data and then even join multiple stream across for complex use cases. Next, I think is stream enrichment one. So this is another feature that Dagger provide for making life of data scientist a bit easier. So let's say the pricing example I was talking about, right? So if you want to say that there is one booking event came in a stream job, in a streaming event, and I want to attach pricing or something else or surge pricing with it, and the surge pricing reference data that I need, it's stored in some Elasticsearch or let's say some other XYZ sources. So you can specify your external source and you say that Elasticsearch is my external source, and you specify the endpoint, and you can say, okay, map customer profile to this particular case, right? And what it allows you is to enrich that entire thing. So for example, you go to the booking and you want to add and attach customer ID or customer data with it, or even do the inferences from your model, you can do those kind of things. So basically same SQL query, just a bit of JSON configuration, and you can enrich your entire stream. So if I look at high level, how this looks is that, okay, you're getting data for your input to prediction model from Kafka, and then you get into Dagger. Dagger pulls the online feature from a feature store, makes a call to the model, fetch predictions, and enrich that output, enrich basically this prediction model input with the predictions and send back to Kafka. It can send back to other sources also. And then rest of the consumers can start to basically pick it from there. Right. So what it allows is basically people to do this stream inference and enrichment right out of the box without anyone else or data scientists or data engineers coming into the picture. So in terms of overall adoption at Dagger, so we have some 300 plus Dagger jobs running for purely feature engineering, which data scientists are writing on their own. And we have more than 50 data scientists spread across different teams who are writing these jobs to it. And overall Dagger, I think on the daily basis kind of presses around like 10 plus terabytes of the data. I think just a bit high level on Dagger. So Dagger is overall part of Open DataOps Foundation. And what Open DataOps Foundation is basically, it's a suite of products that allows people to discover, transform, analyze, and secure data. So we have different products as part of this. And Open DataOps Foundation is, I think, is built with a slightly different approach where it's not about what tool you are using, but how people want to use it, right? So first piece is that anyone joins your organization, they want to discover data. And that's the first step. Second step is that once they understand what data exists, then they want to understand it. How's the quality? How's the lineage? And third is that they want to process on it. And then Dagger is basically fits into the process part where people are processing, transforming, and analyzing data. And then last is you take it back to your business and apply. Same, yeah. So it's a bunch of tools put together, and then that's what we call as an Open DataOps Foundation. So these tools are kind of categorized in 3 major categories. One is around data lifecycle. So let's say, for example, one is for data ingestion. Dagger is what we talked about today, which makes data scientists' life super easy to do the feature engineering and feature transformation and enrichment. And then there are other tools around transformation as well as around data management, and then basically overall reliability and schema management. So Open DataOps Foundation and Daggers are already powering like large data platform teams. Like, for example, Gojek, Mitrans, Mapan, and Mocha. Some of these companies and organizations are already using these tools that I just talked about. And all of these things are open source with Apache 2.0 license and in a vendor neutral space. And we have like somewhere around 200 plus contributors, and then it's growing with 80% growth. And in last year, we had around like 2000 plus commits into it. And then like across GitHub and Slack, we have like 1000 plus community members overall for it. So I think at last, I would love to kind of take feedback on what all we talked about and what all we discussed and how we're solving these problems. And then, anyone have any questions, feel free to get involved by checking out GitHub organization for this. And also feel free to join the Slack community and then let us know for any questions. That's all from my side. Thank you so much for having me.
Brilliant, Ravi. Thanks very much. That's a fascinating talk. And it's great to see innovation continuing, particularly where we see, Gojek, who were obviously involved in Feast, one of the first feature stores as well, and that you have a whole suite of products that are helping people put data into production. Okay, great. So the next talk we have now, and drop over, and if you have questions for Ravi, please put them on Slack. So next talk is Greg Kuhlman. He's the co-founder and CEO of Sumatra. And previously, Greg has been at Apple, where he led the anti-fraud data science team for the App Store and Apple Pay. And he's going to talk about designing featured domain-specific languages. And we had this as earlier in the day, we had a panel about domain-specific languages primarily. So it'll be interesting to hear your take on this, Greg.
Yeah, thanks so much, Jim. Yeah, so like he said, I'm Greg Kuhlman. I'm co-founder and CEO at Sumatra, and we provide a feature platform that specializes in use cases with really strict latency and freshness requirements like fraud, security, personalization. And yeah, there's been some great discussions so far about DSLs, and I hope in the next 10 minutes I can contribute something useful to that conversation.
Great. Do you want to try and share your screen? And you're great. You're good to go.
Am I good? Okay, great. So the way I think about the feature engineering process is it really starts with an idea for a pattern or a signal in the head of a data scientist, who then needs to implement it in some way that captures that intent correctly before they can evaluate whether there's lift from that signal in their model before putting it finally into production. And so as we as a community get better at supporting data scientists from that research to production step, there's great opportunities for us to support them earlier in the process as well. Which is really a question of developer experience, and language is not the entire developer experience, but it's a really kind of critical piece of it. And so, when I've looked around at feature languages out there, you really see a really wide variety of things, from config files to interpolated queries to a lot of Python. I've even seen Clojure. And for us to have a good discussion about this, we kind of have to break it down in terms of what kind of transformation we're talking about. And so there's really different situations depending on whether it's batch streaming or on demand. And in particular, in the batch world, I think this is where DSLs get a particularly bad rep. And I think it's for good reason. It's because there's just a really wide variety of transformations we want to be able to do. It's completely open-ended. We have the luxury of time. And there's often like existing pipelines that you want to be able to reuse. And so the kind of general interface that we've come up with as a community is to think of those transformations happening in some process that then eventually through a data frame API makes its way into the platform. And that's certainly how we built our own platform as well. And so not to say that DSLs couldn't potentially have some place there, but really where I have found the most interesting use for them is on the streaming and on-demand side of things. And so in particular, something that is a little different about the way that we approach things than other people is that rather than thinking about streaming as batch that's just going faster and faster and faster, kind of coming at it from the other angle of thinking of streaming as on demand, but with state. And so, as I'll show, there's some really nice things that you get from thinking about the streaming problem that way. But when you do, there's a lot of advantages to taking the streaming and on-demand transformations and thinking of them as having one representation, one unified language for expressing them. And so, how are we to say if a feature language is good or bad? It really comes down to how are we empowering a data scientist to do their work as much as possible without having to, phone a friend to an engineer to save them because of some platform shortcoming. And if we look at some concrete examples, so here's an example of a YAML, simple definition for an aggregate. There's a lot to like about this. It's concise, it's in the language of the domain, it's declarative. And then on the other end of the spectrum, we have something like this. This is an example taken from the Feast docs, and there's a lot to like about this as well. It's very flexible, general purpose. It's, has the full expressiveness of a general purpose programming language. And so we can kind of think of these as occupying different ends of a spectrum, from a high level of abstraction to a low level of abstraction. And so when we think about how do we make a good choice here, is it really just a matter of thinking how constrained our domain is, thinking about the skill sets of our users and just sort of picking a spot on the spectrum? But I think we can do better than that by thinking about what are the things we can push on to try to get the best of both worlds. And so, one way that I've thought about approaching this and how we've kind of arrived at where we have is to, you can look at an example like the Feast one again and think about kind of what lives above the def and what lives below the def, right? So above the def, we live in what I would call, feature utopia, like feature land of where great things happen, right? There's it's declarative, it's well typed, it's amenable to static analysis and optimization and all good stuff, right? Whereas, below the def, it's opaque to our system, right? I mean, you can stick infinite loops in there if you want, right? And you have to worry about the, whether pandas in your critical path is going to be, fast enough, and package dependencies, all this kind of stuff that we don't necessarily want the data scientist to have to think about. And so the path forward that we found is really to just try to do as much as we can in feature land as possible. And so one of the mindset shifts that we have to make is to, from the batch world where we think of features as these like precious artifacts that, for good reason, they are the result of like expensive processes that we've arrived at to come to this thing. If we shift away from that to think about features as things that are a little bit more lightweight, right? Things that are composable, it makes more sense in the streaming and on-demand world. So rather than giving someone a new black box to put their transformation into, we can think of it as giving them a bunch of components that they can compose together to produce their final feature transformation that they want. So I'll make that concrete with the language that we've developed and are continuing to develop that we call Scowl. So here what you're seeing is a line from our language where we are doing a streaming join between our current stream and the login stream to find, for this particular account ID, when's the last time they logged in. And from that, we get a login feature, a last login feature. And then we can take that login feature and compare it to the current event time, convert it to minutes, and now we arrive at another feature, the time since. And then we can keep doing this again and again with a bunch of different transformations to achieve our goal. And so if we make these transformations simple enough, it gives us that flexibility to do whatever we want. Whereas at the same time, we also want to be able to get that level of abstraction that we're getting from some of those more concise representations. And for that, we have the ability to create abstractions on top of these features, right? So then you can take something like this minute since login and apply it in multiple situations where you can create multiple features depending on what entity you're passing in. And so you may be thinking, this is nothing special, like, lots of languages have functions, what's the big deal? But you have to notice here that what we're doing is we're actually introducing abstraction in the land of features with all those nice properties that we have, right? And further, it kind of takes us from this, from a feature reuse perspective, rather than thinking about feature reuse as sharing a global variable that I made, you're actually thinking about sharing the computation itself, which is a really powerful thing to be able to do across a team. So making features ubiquitous is partly about going deep, like I just mentioned, but I think about it also as going wide. And so what I mean by that is, if we look at the standard way of thinking about feature transformation, in most systems, it's entities come in and features come out, right? And these are different things, not to be confused with one another. But if we kind of look at what's at the margins of this, after feature transformation, feature extraction, we would have like what we might call transformations, things like one-hot encoding, imputing a missing value, stuff like that, which eventually leads to our model. And so there's been some great discussion about exactly where that transformation should live. Should it be part of the model in that pipeline, or should it be part of the feature store? Well, if we start to view this entire thing as one big pipeline, we don't necessarily have to make a particular choice about where we're going to draw that line. We can think of this entire thing, including the model inference itself, as just a series of transformations from one set of features to more and more features. And in the space of use cases that we deal with a lot, especially in fraud and security, after model scoring, there's typically a bunch of business rules that are applied after the score. So things like whitelists, blacklists, other kinds of business logic that ultimately arrive at your decision. And we can think of that as a transformation as well. And we can even push to the left and say, even before the entities, we don't necessarily get every entity that we want from the calling service to our feature service. And data scientists can be really creative in terms of constructing their own entities that they want to aggregate over. You can take something like an IP and extract the CIDR block and concatenate that with a user agent, and now you have like an ad hoc device ID that you can track. And so we want to be able to bring that into that same pipeline. And so to confuse things further, sometimes this isn't a clean path from left to right always. There's often interleave steps of stateful, stateless transformation, aggregation, and so on, that ultimately turns this entire thing into just one giant DAG, right? And so if we think about it this way, as just like one big DAG of transformations, we can do some cool things with this entire DAG. We can say, hey, now we can statically type check the entire thing end to end, right? Feature versioning now becomes something where we can just look at our dependencies, and when they're updated, we implicitly can recognize that our feature has a new version as well, right? All the investment we've made in logging and monitoring that has applied to features now applies to this entire DAG. And when it comes to online-offline consistency, which is something that we as a community focus on a lot, rather than just focusing it narrowly on this one part of the pipeline, it allows us to extend it to that entire pipeline. And so it doesn't mean that we always need to include every step of this in every process, but there's something really powerful when you can do that. And so you can run really interesting counterfactual experiments where you can change entities or features early in the pipeline and take that all the way through to the end of the pipeline to see what effect it will have on the ultimate decisions that you make. So from what I've said so far, very little of it has had to do with the syntax itself. So for us, it's made sense to actually invest in a full language with a compiler and parsing and all that in order to be able to support the other parts of the developer experience as well. So things like syntax highlighting and autocomplete. We've even made a REPL where you can take expressions written in the language and bring them directly to the data that you have to be able to see in real time what changes to those features make in terms of how they change the feature value, so that you can get to that correct implementation as quickly as possible. So there's lots more cool things that can be done here. Tons more things we can talk about in terms of what makes for a good feature language. Things like type inference, what these things are very amenable to. Being able to support embeddings and JSON natively means like supporting lists and structs. Missing values are such a common thing in the feature world that we want to be able to speak them natively. So if you want to see how we've taken some of these ideas and incorporated them into our own language, our docs are public, so I encourage you to go check those out. Want to give a quick shout out to a few folks who are really helpful to me in thinking through how to present this material. And if you want to geek out on programming language stuff, come see me in the Slack. Thanks.
Great stuff, Greg. It's a fascinating talk, a very holistic vision for how we should build end-to-end machine learning pipelines. Thanks very much. You can reach out to Greg on Slack as well, and if you have any more questions. So our next speaker is Sarah Wooders from UC Berkeley. And Sarah is a third-year PhD student. and she's advised by Jan Stoika and Joe Gonzalez, and her work is focused on data systems for machine learning, including accuracy-aware scheduling for feature stores and cross-cloud data movement. And you have this very interesting way of copying data between buckets in S3 across different regions to save a lot of cache, I believe, Sarah. I read a post about it. It was very fascinating, but I think today you're going to talk more about Ralph. Can you hear me?
Yes, actually. Can I share from my
screen? Go ahead and share your screen if you can.
I'm having a bit
the big green button at the bottom of
Yeah.
Zoom, if you're not familiar with Zoom. So there's a green button. If you move your mouse over, it's a green button.
Yeah.
Green.
Okay.
Great. It looks like we're good to go.
Okay, can you see my screen okay?
Yeah, we're good. Thanks.
Okay, great. I will try to go through this quickly since I know we're low on time. So hi, everyone. Today I'm going to be talking about basically optimizing computation and data movement for fresher features. So I'm actually going to talk about two projects today. They're both sort of about data or feature freshness. One is, so if we think about like what actually causes data or features to be stale. There's first computational bottlenecks. So basically, you might have some new data and it hasn't been processed yet to actually be reflected in your feature values. So the first project I'm going to talk about, Ralph, is about optimizing this computation. And then the other bottleneck that we often have is data movement bottlenecks. So because data is slow and expensive to replicate, we end up having stale data or stale features. So this is relevant to the second project I'll talk about, which is Skyplane, which is optimizing data movement for faster, cheaper data replication. So first, Ralph, if we think about what a typical feature store setup is, we might have something like a news application, which is sending a query stream to a model, which is using these features. And then these features are maintained by a clickstream going through some kind of transformation pipeline, which is doing the feature maintenance. So one challenge here is that this feature maintenance step is often very computationally expensive. So this means that we can't necessarily process every single click if we have a very expensive transformation due to limited resources. But at the same time, if we don't process updates fast enough, like with a streaming system, and maybe we only compute things once a day, then this can actually often lead to model performance degradation as a result of features being stale. So I think some other speakers have mentioned this problem, and there are sort of solutions to it as well. So fundamentally, there's sort of this trade-off for pre-computed features, where on one hand, you can have these very real-time, high-quality features that immediately ingest new data to update the feature values. But then you also have these sort of lower quality, but more cheap feature computation systems. So things like batch systems that maybe just update features in daily batches. So we have this trade-off here, and for any system, we want to be able to figure out basically what's the right point on this trade-off curve. So what we did for this Ralph project was actually trying to figure out, like, can we do better than this trade-off by having more intelligent scheduling? So basically, a lot of features are actually never queried. And so then we can actually save a lot of money by our resources by not bothering to update things that are never queried. And also a lot of features, they might have new data come to them, but the feature values themselves may not actually change in any kind of meaningful way. So in these cases, we also don't want to update, basically waste resources updating features, since the staleness isn't going to actually affect the model, downstream model accuracy, which is what we actually care about. So at a high level, this work basically introduced a scheduling policy where we basically try to minimize something that we call the cumulative regret of a feature. So basically, as the model makes predictions from some incoming stream of queries using the features, we track what is the eventual error that we observe for those predictions. And so for every single key in the feature store, we basically track like how much error have we seen that's been resulting from this feature. And then basically on the feature maintenance side, prioritize what keys that we update based off of which ones has the highest cumulative regret. And then we set that back to 0. And so it sort of ends up balancing resources to prioritize the most queried or the most rapidly changing features. So this is a very high level view. I'd be happy to email the paper draft to anyone who's interested. And the overall result of this is we basically can achieve higher accuracy for the same cost. So by basically prioritizing the features that are the most important to update or the most frequently queried, we can improve the cost accuracy trade-off and basically for the same amount of resources, be able to get higher quality features. So the second project that I'm going to talk about is Skyplane, which is fast, cheap cloud data replication. So part of why we started looking at this project was actually because for a lot of applications, data movement is actually the bottleneck, not compute. So for things like feature publishing or serving, moving all that data can actually be a huge bottleneck. So this happens in cases where maybe you have a single model that needs to access data or features that are spread across multiple regions or clouds, or maybe you have a single set of features that need to be served to different applications or different models that are spread across, again, different regions and clouds. So the reason why this is challenging is because in general, data transfer is very slow. So if you're trying to move data from maybe like one application or one user on one side of the country with like GCP to maybe the other side of the country in a different region on Azure, it can actually be really, really slow. As a result of this, we can end up having stale data if we have geo-distributed applications or applications across multiple clouds. So a 70 gigabyte data set can take up to 1 hour to transfer with existing tools. And on top of that, we have very, very high egress fees whenever you try to move data between regions or cloud providers. So the cost of moving a 70 gigabyte data set can actually be equivalent to running 34 like M5 large instances for an hour. So this data transfer cost can be really, really problematic if you're trying to move data to keep like all your data sets or features fresh. So the reason why slow transfers are very problematic is because for a lot of real-time applications, slow transfers can mean you have worse accuracy. So for example, if you're maybe like Uber and you're trying to do ETA prediction, as you get new data, you ideally want to be able to process those updates, create new features, train a new model, and then deploy that as quickly as possible. But at each stage, if you're having some kind of bottleneck because of the data movement, especially for something that's as geo-distributed as Uber, this whole pipeline is going to take a lot longer just from waiting for the data to transfer. So Skyplane is basically a project on trying to solve the problem of managing data transfer across regions and across clouds being very slow and expensive. So we basically have a simple CLI tool that looks a lot like the AWS CLI, except you can transfer between any of the 3 major cloud providers, and it's a lot faster and cheaper. And so, yeah, overall, our results show that Skyplane is up to 113 times faster and up to 3.8 times cheaper through doing compression and bandwidth tiering. So yeah, Skyplane is open source, so you can install it with pip install Skyplane, and then also this QR code will take you to the GitHub URL. So I'll just very briefly go over why transfers are slow in the first place and some of the techniques we use to get around this. So first of all, there's often congestion along the direct path. There's poor peering between providers, and there can also be packet loss from the physical layer. So one of the techniques that we do for this is that basically in cases where the direct transfer between 2 regions is very slow, we can often find overlay regions. So basically some other third region, where if we go through this region instead, the transfer ends up being a lot faster. So here we went from about 2 gigabits per second to about 4 gigabits per second. Another technique we use is striping transfers for large files. So if we have some very large file, we can actually subdivide it and then parallelize it across multiple VMs for the transfer. So this gives us some of the biggest improvements. And then finally, we also use a couple techniques, including compression, to basically compress data as it's being transferred to basically save you egress costs. So altogether, we have up to about like 110x speed up for large files in particular, which can bring transfer times from 2.5 hours to just a few minutes. And then we also save on costs. So if you compare to AWS Data Sync, which is going to charge both for egress fees and also service fees of the service, you will actually go from like $7.27 to $1.17 using Skyplane instead. So all the techniques that we use are covered in the NSCI paper that we have. So I'm happy to email this to anyone who's interested. And yeah, that's the end of my talk. And thank you everyone for listening. And please let me know if you have any questions.
Thanks very much, Sarah. And there may be questions on Slack, so you can go over to that to see if there's anyone interested in both of these fascinating two projects. And congrats on the NSTI paper. Okay, so we have our last talk of today, last but not least, of course, is by Lu Mian, and it's on OpenMLDB. And Dr. Lu Mian is a system architect and manages the database and HPC teams at 4Paradigm. And before joining 4Paradigm, he was a staff engineer in Huawei. He obtained his PhD in Hong Kong University. So over to you, Lu. Hopefully everything's good to go.
Yes, let me share my screen. Yeah, can you hear me?
Yeah, we can hear you fine. Just go ahead and try and share your screen.
Okay.
Yeah, looking good. Oh, our first PowerPoint of today. Brilliant.
Okay.
Go for it.
Great. Let me get started. Yeah, thank you very much. Yes, I'm very pleased to share our project at this Feature Store Summit. But actually, you know, we usually do not call our project the Feature Store. Usually we call it like a database. Yeah, this is like the difference between like a KV store and a relational database. This is because our project not only focusing on the store, but we also really focusing on the real-time the feature processing on demand. Yeah, so today actually I would try to really focusing on this unique features, how we deliver the real-time features in milliseconds. So this is first we introduce a little bit background of the OpenMDB. So OpenMDB actually is initialized by the 4Paradigm, and 4Paradigm is a company from China. It's offering the plentiful-centric AI solution. Then OpenMDB is integrated with the 4Paradigm's commercial product. It's called Sage. It is used in the Sage to define and compute real-time features. Then last year, we have decided to open source OpenMDB. Then the community also can benefit from this project. So the OpenMDB actually is a young, for the open source, it's a young project, but actually it already has been developed and deployed in many applications for 4 to 5 years. Yeah, before open source, it's already have been deployed in more than 100 applications. Then after open source, we also receive quite a lot of feedback and users from the community, like some tech giants from China, like Huawei, like Jingdong, also like the Pelaku it is in fintech company from Indonesia. So now let me talk about some background of this, the technical background of this project. So why we really need the real-time features for real-time decision making. So from our understanding, real-time features mainly refer to 2 points. The first one is the real-time data. That is, we really need the fresh data. We need to do the decision making based on the fresh data, not the data from the last year or not the data from last month. Probably it's just the last data, the latest data happened in the last few seconds. And the second thing is we need to do on-demand real-time processing. And this real-time processing really needs the low latency. In our requirements, or from the requirements from the customers, actually they really needed low latency, like the milliseconds. So this is like the example. The table is like an example of one of our users. This is like one bank for the application of anti-fraud. So they really needed the real-time feature processing like in less than 20 milliseconds. So actually we can see today in the market, we have quite a few solutions to do the feature processing. But actually we see that most of them are based on batch processing or streaming processing, like the Spark and Blink. But actually even for the Blink, actually we saw the latency actually will be very high. It's like hundreds of milliseconds or even seconds. But there is really few solutions talking about the hard real time that is like a few milliseconds to do the real time processing. So this is actually we need a better solution to this. This is actually what OpenMDB will do. So now first thing, let's see what is the challenges of computing real-time features, why it is so difficult. So let's think about if we want to implement a machine learning application, let's say in practice, okay? So what we do, so first thing is the data scientists will go to the project. The data scientists, they have the background of machine learning. So they know how to define the features, how to do the model training, right? So basically, they have the knowledge of the machine learning. So the data scientists, they like the Python, they like the AFCU to write the feature script. Their job, as long as the model can achieve high accuracy, their job is done. They don't care how the performance of the feature script online. So actually, the feature scripts written by the data scientists cannot go online directly because like the low latency, like the high throughput, like the high availability, all these requirements actually usually cannot meet. So at this point, usually we have another engineering team. So the engineering team, what they will do is actually they will try to rewrite the feature script written by the data scientist using some other tools, like the database tools, like C++, to rewrite this program and make it really fast online. So their program can meet the requirements like the low latency, high throughput, and high availability. So actually, at this point, we already can see the cost to implement a machine learning application actually is really high. We need 2 teams, and we also need 2 systems, right? But actually, this is not the end. Another very important point is we need to do the consistent verification, that we need to make sure that the script written by the data scientist is consistent with the program written by the engineering team. So this verification actually costs a lot. Based on our experience, if you are trying to implement a larger, a really big machine learning application, it will take months to do the consistent verification. So actually, we can see the major challenge is one is the correctness. We need consistent computation logic between the offline and online features, and without data leakage. And also, we need to achieve efficiency. That is computing real-time features just in milliseconds. So how OpenDB tackles these challenges? So basically, we will look at this very high-level architecture. We will see inside the OpenDB, we have 2 engines. One is the batch secure engine. This engine actually is modified, improved based on Spark. Actually, we have done a lot of source code modification based on the community version to enhance the performance as well as to extend the secure syntax. And the other secure engine is the real-time secure engine. So this is really the key to deliver the high performance. Actually, we built this real-time secure engine from scratch. We really think about the performance improvement, performance optimization, and based on the really focusing on the time series data, and also optimized for the feature engineering workload. So based on this the real-time secure engine, we can really deliver the milliseconds latency. And between this, another very important thing is we have a unified secure plan generator. This plan generator actually is the key to ensure the consistency between these 2 engines. So based on this architecture, so as long as data scientists, they can write the secure script, so their secure script can go online directly. So we can see that we can achieve this target. That is, data scientists do the offline development, and then they just use one command to deploy their secure to online. And then we just prepare the real-time data stream, and then that's all. Your service is on, so you can do the real-time. You can do the on-demand real-time request to do the feature engineering. So let's recap. So the OpenDB in trying to tackle one challenge is to provide the consistent features for training and inference. And another thing is that we can compute the real-time features just in milliseconds. So let me just quickly go through some highlights of this project. The first one, as I mentioned, is that we have a secure plan generator to ensure the consistency between the offline and online engines. This is actually we do some we have developed this secure plan generator can translate the logic plan to physics plan to the offline engine and online engine, and also keep and ensure the consistency. And also we share some unified computing libraries between these 2 engines. So we can we can through this secure plan generator to guarantee the offline and online consistency and without data leakage. The second thing is very important is we can deliver these real-time features in milliseconds. This is actually we build this real-time engine from scratch. We have two very key optimization techniques. The first one is we have an in-memory double-layer skip list. This data structure is really optimized for the time series data for the feature engineering workload. And the second thing is we have some pre-aggregation techniques. That is, if your time window is very large, actually we can do some pre-aggregation to speed up your performance. So actually we compare with some these two figures. Actually we compare OpenMDB with other commercial in-memory database. Actually one is the SAP HANA and another one is a single store. We can see that for time series data for the feature engineering workload, OpenMDB can outperform these two databases a lot. And this one, the second row is the figure about the optimization with the pre-aggregation. Actually, we have a paper. We have a paper at the top database academic conference, VLDB. If you are interested, you can look at the technical details, how we achieve these real-time features. Yeah, of course, there's a part of the technicals. And the third thing is we want to emphasize this enterprise-grade features because this OpenMDB has been deployed in many enterprise applications. So we have introduced quite a lot of these enterprise features, like high availability, like horizontal scaling, like the smooth upgrade, like the monitoring and the multi-cluster. And also we are trying to develop more features for these enterprise applications. Okay, this is like a use case of our OpenMDB, and Aqualak is the first users from after open source. So they are trying to build the ML ops platform and also to deliver the real-time features. So they choose OpenMDB as the key component. So the result is like they do the real-time processing for orders with a day. And then usually for a day, they have like 1 billion orders per day. So now as a result, they can achieve the real-time feature processing like 4 milliseconds. Okay, I think that's pretty much about my talk. If you are interested, please join our community. And this is also our Slack workspace, and you can contact me and try our OpenMDB. Thank you very much.
Thanks very much, Lou. And that's it. That's the last talk in this year's conference. Thank you, everyone who's stayed this long. I'm going to, I think I'm sharing my screen, am I? Let me start sharing my screen. I think someone else is, FS someone is sharing it. So just a wrap up. So we're the featurestore.org. We have a meetup. We have a newsletter. We even have a Medium blog where you can submit posts to, and we're available on LinkedIn. You can reach us on LinkedIn and Twitter. And of course, we have the Slack that many of you have been active on this evening. I'd like to finish by thanking the organizers. So I'm one of them, but we have Caroline, we have Alba, we have Lex and Mariana who led the organization of this. Without this great group of people, this would never have happened. So a heartfelt thanks to those for their fantastic work in making this event happen, and for the community, and also for all of you who've attended, and particularly those of you who stayed to the end. Thanks very much. So we'll meet us back again at the next meetup. So we'll have the FeatureStore meetup regularly. If you're curious, there's also a course that we're sponsoring called Serverless ML. If you Google it, you'll find it. You can take it whenever you want. And that's it for this year. Thanks very much for tuning in, and all the best. I hope you learned something and came away inspired to make a difference in machine learning. Thanks very much and have a great day.